Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the R-PYQ. We'll continue with the R-PYQ series, and this video will be regarding power system analysis. So we will cover complete power system analysis, mostly the questions. Okay. So for concept revision, so make sure if you're watching this video, before watching this video, watch do these things. Okay. Because in this video we will mainly solve questions, all the most important questions covering most of the topics: transmission distribution, power system fault stability, load flow analysis, then power system protection and generation, right? So before watching this video, make sure you cover, if you want to revise quickly, you can revise through our revision X notes. It is present on the website. You can go and download this for free. It is completely free. Go into the website, free courses, there will be revision X. If you want to know more about this, make sure you just search on YouTube revision X notes by PrepFusion. You will get the complete information, right? If you want to revise quickly, everything is there mentioned. Most of the key points are mentioned in the short notes. Now if you want to study power system, right? Now power system comprehensively is not covered on YouTube, but the important parts are covered on YouTube: fault stability, unsymmetrical faults, all this is covered on YouTube. Then power system performance of power system performance of transmission lines, that is also a very important part in PSA1, that is also covered on YouTube. So these are the marathons that has been covered. So you can watch these marathons if you want to learn learn a particular concept from scratch. Okay, so these are the resources that you can follow. After following these things, then only come back and watch this video. If you directly jump onto this video, you will not be able to understand most things, because I will not explain everything from scratch. Few things I will, certainly I will, but not everything. So I expect that you cover these things first and then come back. And of course, if you are enjoying this R-PYQ series, make sure to hit the like button, hype the video, comment down below whichever part you feel more interesting, and you can also let us know what you want next. So we will always try to bring those initiatives on YouTube. And yeah, with that, let's begin our first chapter, that is three-phase systems. Let's begin with the first topic, that is three-phase systems. So this is the first question, that actually in gate IN as well, three-phase system is included. So make sure you study it, don't ignore it completely, because it will be coming in gate IN examination as well. So 400 ohm resistors are connected in delta. Okay, so we have 400 ohm resistors that are connected in delta. Okay, and powered by a 400 volt RMS 50 Hz balanced symmetrical three-phase 3-wire system. So it's a three-phase 3-wire system. So basically it's kind of a delta, and whenever this voltage is given, right, it is always the line voltage. So the line voltage is 400 volt RMS. Now the RMS value of the line current would be, so what will be the RMS value of the line current? So it is a balanced system. So the resistance is 400 ohm and the voltage across the resistor is 400 volts. So the current through the resistor would be 1 ampere. The current through the resistor would be 1 ampere. Okay. So current through the resistor is 1 ampere. This is the phase current, but they are asking me what is the line current. So line current will be, because it is a balanced system, the RMS value of the line current would be, this is the RMS value of the phase current, because it is the RMS voltage. So root 3 times the RMS value of the phase current, that is root 3 only, that is 1.73. So this will be your round off to 1 decimal places. So it will be 1.7. That would be your answer for the question. Pretty simple. In IN, if something is coming, right, that is supposed to be in EE, then it will be very simple. The topic will be very simple, because IN has their own syllabus. They have to study something else as well, different stuff as well. So that's why if something is coming in IN that is supposed to be in EE, the question will be 90% of the chance very easy. Let's solve the next question. So this is the next question, where the circuit shown RMS value of the voltage across the 100 ohm resistor would be. Okay, what is the RMS value of the voltage across the 100 ohm resistor? Now the thing is, now the system is not balanced. Okay, the system is not balanced, right? The system is not balanced, because like for the whole system to be balanced, right, both the supply and the load, both of them must be balanced. This I have taught in power system in the first chapter, that is three-phase systems. There I have told regarding unbalanced system, and I have discussed, most of us only understand this. Okay, if supply is balanced, then I will do 400 by root 3 and it will work. But no, you have to check the load as well. Make sure your load is balanced, then only the overall system will be balanced. Otherwise, what will happen? The current distribution will not be symmetrical, and if the current distribution is not symmetrical, the voltage drop also will not be symmetrical. So here system is not balanced. Then how will you solve? How will you solve? So here, right, you will have to draw the circuit. So this is your phase voltage, right? So your phase voltage is like this. So remember, sorry, this voltage always, it is a symmetrical balanced system, and 400 volt is always they say in terms of line. So it is always discussed in terms of line voltage only, right? So you can draw it star equivalent, because it is a balanced system, right? You can assume star or delta, it will not change your answer, but I will assume star. Why? I will explain. So if I assume star, I will get a neutral point, and that neutral point I will connect to this, because those two neutrals I can connect. Hold on a second. Can I connect them together? Yeah, I can connect them together. Okay. So this will be coming here. $400. Remember, this was supposed to be line voltage. If I am converting into star, this will be phase voltage, right? Okay. No, I don't think we can connect the neutrals, because if they are not balanced, you cannot connect the neutrals, right? No, you cannot. Okay, what is the? So you will have to solve accordingly. Symmetrical RYB means, okay, so you cannot connect the neutral. How will you solve then? No, you cannot connect the neutrals, right? You cannot connect the neutrals. So if you assume this to be a star system, and you cannot, because it is unbalanced, right? If it was balanced system, then actually you could have connected the neutrals, then the voltages would have been symmetrical. But as it is not balanced, right, you cannot connect that. Sorry, I'm sorry, just a brain fade from my end. You cannot connect the neutrals. So let me connect the load here. So voltage across the 100 ohm resistor, right? What will be the voltage across the 100 ohm resistor? So this would be here, here, and here. This will be connected here, RYB. So R is there, then Y is there, then B, right? So RYB. So first rate phase, that will have angle 0, then yellow, that will have angle of minus 120, and then your blue, that will have angle of plus 120, right? Correct. And this blue will be connected at the end. That's all. I'm just drawing it roughly. So ultimately, what is your task? Your task ultimately is to compute the voltage across this 100 ohm resistor. That is your task, correct? So if I find out the current across this resistor, will that be enough? Yes, certainly that will be enough, right? If I am able to compute the current across this resistor, I will be able to compute the voltage, because current into the resistance will be the voltage. So let me use Thevenin's theorem. Can I use Thevenin's theorem? Yes, you can use Thevenin's theorem, right? So if I use Thevenin's theorem, what I will do, I will just remove this 100 ohm resistor, then I will draw the equivalent circuit, right? Now if I draw the equivalent circuit, this circuit is simplified very much. If I draw the equivalent circuit, right? Okay, this circuit is simplified very much. Now what is the open circuit voltage? Okay, if you see, right, if I remove this 100 ohm, then this load becomes balanced. supply was already balanced. So then the circuit becomes very simplified. Then what is the open circuit voltage? Open circuit voltage in this case across this particular resistor will be 400 by root 3. That's all, because you can connect the two neutrals now. That is valid. You can connect the two neutrals, that is totally valid. Before that you wouldn't have been able to connect the neutrals. Now you can, right? So what am I doing? Simply I am calculating the open circuit voltage or the VTH. So if I calculate the VTH, so I will have to remove the resistor RL. If I remove this, ultimately this becomes a balanced system. If it becomes a balanced system, what is the voltage across these 2 points? Because here I have to compute the open circuit voltage, that is nothing but 400 by root 3. It is nothing but the phase voltage. So VOC is equals to 400 by root 3 angle 0. Okay. So I got my open circuit voltage. Now what is the equivalent resistance? What is the equivalent resistance? So for calculating the equivalent resistance, you will have to short your supplies, right? If you short your supplies, so if I short my supply, all this will be shorted, and then what will happen? Then this is connected here, so all these three will be in parallel, right? That is what I'm guessing. Just give me 1 second. So if I short this, what will happen? This so if I short this, right, then what will happen? Essentially, no, I cannot connect them. Then essentially what happens, this is connected here, okay, connected here, this is connected here, right? So these two points are same, okay, the other point is also same, so these two are in parallel. Basically these two are in parallel, right? Because let's say this is point A, this point A, this is also point A, this is also point A, correct? And this is also point A, but and let's say this is point N. So between point A and N, what is the impedance that I am observing? So the impedance will be this whole divided by 3. That is the impedance that I am observing. So all of them are 300 ohms. So the impedance that I am observing between point A and N is 100 ohms. Correct? That is the impedance that I am observing between A and N. Now we can, so this is my RTH. Now we can draw our equivalent circuit, right? So what is my VTH? VTH would be your 400 by root 3 angle 0. Then you will have your RTH, and then you will have your RL, correct? And if I know the current, right, what is the current here? I would be equals to 400 divided by root 3. It is what, like these three are in parallel, right? So simply 300 by 3, right? Because each of them has resistance of 300. That's how simple it is. So this divided by, that's why this is 100, right? This is nothing but 300 divided by 3, because three of them are in parallel. So this will be, I would be equals to this divided by 100. So I would be 4 by root 3. Sorry, this divided by 200. So I would be 2 by root 3. That is my current through the 100 ohm resistor. Now what is the voltage drop? If I know the current, I know the voltage. So voltage drop would be voltage across the 100 ohm resistor would be current into the resistance, that is 2 by root 3 into 100. So this will be 200 by root 3. That is equals to, remember, there is angle here, don't forget, this is angle 0. All these are phasor quantities, don't forget that. Although it won't make a difference because we're ultimately computing the magnitude, but we'll have to be careful. So 200 divided by root 3, 115.47. And trust me, if you try to solve with KVL KCL, this will be so difficult. Trust me, this will be very difficult if you try to solve with KVL KCL. And actually, just the previous question, I told you that generally if a question is coming from iron, right? If it's in the topic of EE, it should be easy, but I was wrong in the second question itself. This question is actually pretty good. This question is pretty good. Right? You have to think of the Thevenin. So whenever you have to compute the voltage or current across any resistor, always think about Thevenin's theorem, because that will help you out, because the circuit is very typical, very difficult to solve. If I try to solve with basic KVL KCL here, right, first of all I will not be able to connect these two dots, because the circuit will be unbalanced. You will not be able to do it. I was able to connect these two dots. Why? Because the circuit became balanced when I tried to compute the open circuit voltage, because I removed the 100 ohm resistance, then the circuit became balanced. So that's why the calculations became very easy. But otherwise you will not be able to connect these 2 points, and then you will have to use KVL KCL to solve it, which is definitely solvable. It's not like difficult. That also will not be difficult, but you will have to work with phasors and stuff. Not that tidy. And in examination hall, this is the best way to go about this, right? So your answer would be 115.47. Let's solve this question. A three-phase balanced voltage is applied to load as shown. Okay, the phase sequence is RYB. The ratio IB, magnitude of IB upon magnitude of IR would be. So they are asking me, okay, the system, the three-phase balanced voltage. Okay, we are applying a three-phase balanced voltage. What will be the ratio of the currents? That is what they are asking me, right? So if I am applying a three-phase balanced voltage and the phase sequence is RYB. So let's assume this. So my VRY, let's assume it is V angle 0 degree. As it follows RYB, so my VYB is equals to V angle minus 120, and BR would be equals to V angle plus 120 degree. Okay, that is what my VBR is. This is how the phase sequence is told to us. Now what happens? What is happening? We have to compute the magnitude of the current IR upon magnitude of the current IB upon magnitude of the current IR. So what is my IB actually? If you notice one thing, so this is my R phase, this is my blue phase, this is my Y phase, right? So here I am applying VRY. Here, VRB, right? So this is VRB. So actually I should write this the other way around, because what will happen basically, your VRB, right, will be opposite, basically will be minus of VBR. I hope this part is clear to you, right? Because what is your VRB? What is your VBR? It is VB minus VR, right? I hope this point is clear to you, right? So VRB would be just the opposite, negative. All this I have taught in the full course, so you might not want to go there and watch it. I will not explain over here. Now what is happening? What is happening? What is happening? Yeah. So one thing you will notice that your VRB is nothing but this voltage only, right? So basically voltage across this capacitor. So basically your IR is equals to VRB by minus J10. Okay. And what is your IY equals to? So your IY, if you see, this will be, if I write here plus, so VY will come first, then VB will come. So your this will be what? VYB. Why? Because plus sign is with the Y phase. That's why VY minus VB. That's why it is named as VYB. Okay. So your IY actually is equals to VYB by J10. Why I have written here plus or minus? Because the current direction is like this and load can only absorb power. So if plus is there, right, current can only flow into the positive terminal because it is a load. It can only absorb power, it can never deliver power. So your IY would be VYB divided by J10. IY is equals to VYB over J10. Okay. So now now we are in a very good state, so we can actually comment what. So what are they asking? They are asking me the ratio of IB over, okay, they are asking actually, oh, they are not asking IB, okay, they are asking IB, okay. And what is your IB actually? Do you know what is your IB? So IR plus IB plus IY is equals to 0. So IR plus IB plus IY equals to 0 if I apply the KCL at this particular node. So your IB or so your IR I already know, I already know, IB. So your IB would be equals to minus of IR plus IY, correct? So let's solve it basically. Remember, you cannot just simply take the ratios, you will have to solve it because there are phasors involved. So your IR will be equals to, let me write this first. This will be equals to, in terms of angle and voltage, this will be VRB is what? VRB is nothing but negative of BVR, okay? And negative of VBR, right, will be what? This will be, if negative sign is at the coefficient, then what I can do, I can add or subtract 180 with the angle that will consider the sign of the coefficient, right? So this will be V, because it is already plus 120, I will subtract 180, does not matter. So all I did was subtract 180, right, and that will consider the negative sign. I hope you know these basic things regarding phasors. So minus 60 is here, okay, cool. So this is V angle minus 60, right, and this is 10 angle minus 90. So this would be equals to 0.1 V angle 30°. Okay, that is my IR, that's all. And so magnitude of IR would be 0.1 V. Yes, magnitude of IR would be 0.1 V. Angle does not matter, but here actually angles will matter in this case. So to calculate IB, I will actually need this. Hold on, there will be negative sign here as well. To calculate IB, I will need the value of IR as well as IY. So what is IY? IY is equals to VYB. What is your VYB? VYB is equals to V angle minus 120. So V angle minus 120 upon 10 angle 90. This will be equals to V so 0.1 V angle. This would be minus 210 degrees, right? Minus 210 degrees. Or what I can do, I can add 360 just to look good, make it positive. So this can be written as, so we can add and subtract 360, right? So if I add 360, this will be 150 degrees. Now we will have to provide, so this will be, if I take the minus sign common, this will be minus IR plus IY. So my IR is 0.1 V in 30 degrees. So it is somewhere here, right? And my IY is 0.1 V 150. 150 would be somewhere here actually. right? 0.1 V, 150, and between them, what is the angle between them? 120. Now I have taught you this thing. How to remember also I have taught you that if I have two vectors of equal magnitudes and their uh, angle is also 120, then the resultant addition will be the intersection of them bisector, that is at 60 degrees from the uh, base. So if it is 60 degrees from the base, right, actually it will be 90 degrees exactly from the reference 0 degree, it will be 90. So 90 degrees, and its magnitude also will be same 0.1, and its phase will be 90 degrees. Basically why 90? Because it will be 60, like 60 from the lower side and 60 from the other side, basically angle bisector. This I have taught how to understand this. So if I have a balanced system, so one angle 120, so if I add these three numbers up, 1 plus 1 angle minus 120 plus 1 angle plus 120, d is equals to 0, right? This is a balanced system. So from here I can see the addition of two vectors whose magnitudes are same, and opposite vector, if I take this on the other side, will be negative of this. So this is 1 angle 120 would be somewhere here, negative of this would be here. Okay, that's the derivation. So I'm not telling you the exact things here, but you are smart, you will be able to figure out even if you have not studied. So this is what you are missing out if you have not studied from our courses. Okay, just a bit of promotion we have to do once in a while. So this is what you are missing out on. So yeah, another property is there. If two vectors, right, they have the phase difference of 60 degrees between them, right, and the magnitudes are same, then the resultant would be again angle bisector, that is 30 degrees from the lower side, and its magnitude will be root 3 times whatever was the base magnitude. Okay, these are few things that you must keep in mind. So yeah, this value, right, IR plus IY would be 0.1 angle 90. This would be minus 0.1 angle 90. Again I have told you, right, to include the negative sign, what can I do? I can either add or subtract 180. So I will subtract 180 because I don't like numbers greater than 180. That's why I will subtract. So this will be 0.1 angle minus minus 20. Okay, so yeah, angle minus 90. So now if I compute the ratio, right, I need to compute magnitude of IB over magnitude of IR. So magnitude of IB would be 0.1 volts divided by 0.1 volts. Okay, one mistake. Answer is correct. One is correct, but this is not volts, right? This is not volts. This is amperes. Okay. Oh no, this is okay. This is not even volts. This is 0.1 V. V was the magnitude basically. So 0.1 V would be cancelled. So 1 will be your answer. 1 is the answer. And trust me, you see in any of the big coaching institute PYQ books anywhere else, right? You will see they have given the answer as root 3, 1.732. Okay. So just be careful. And I was also amazed. I solved and then I checked it is 1. How are they giving root 3? Then I checked the answer key, it is 1, the gate answer key, official answer key. So they did not even check the official answer key, they just solved it. So just be careful regarding all this. Yeah, let's solve the next question. So this is the next question where in the circuit shown below, a 3-phase star connected, it is a star connected unbalanced load is connected. This is an unbalanced load, right? So you cannot simply connect N and N dash, you cannot connect that. Okay, is connected to a 3-phase balanced supply of 100 root 3 volt with phase sequence ABC. With phase sequence ABC, the star connected load has ZA equals to 10 ohm. It has a ZA equals to 10 ohm. And it has a ZB equals to 20 angle 60. the value of the ZC for which the voltage difference between node n and n dash is 0. Okay, so what shall be the value of ZC? So that the voltage difference between node n and n dash is 0. So effectively they are shorted. When are 2 points shorted? When they are in same potential. So if there is same potential, there will not be any potential difference. Basically, that voltage difference will be 0, and if the potential difference is 0, the 2 points are at same potential, so they can be shorted. So assume that they are shorted, and for that assumption calculate the value of ZC. So your analysis will be much easier. If I assume it to be shorter, I exactly know what is the voltage across ZA, that is EA. What is the voltage across ZC, that is EC. What is the voltage across ZB, that is EB. That's why this question will be much simplified. So if I know the voltages, right, what can I say? Okay, what else can I say? If yeah, one thing is there that they are at same potential. So whatever is the voltage here, Vn, same voltage I have at here, right? But this is like a virtual short. They are at same potential. This is like a virtual short, but physically they are not connected. Physically they are never connected, right? So if physically they are never connected, if I add all this current, so there will be some current IA, there will be some current IC, there will be some current IB. What will be the addition of IA, IB plus IC? It has to be 0 because there is no outgoing current, right? It is open circuit, so it has to be 0. So IA plus IB plus IC is equals to, so it has to be 0, right? There is no outgoing current there. I hope you are correct, right? So yeah, that's the thing basically that you have to figure out over here. So virtually there is short, that is certainly true. Virtually there is short. It is just like open virtual short. Actually there is no connection, right? But virtually they are at same potential, certainly, but actually there is no connection. Okay, so I hope that part is clear. So this virtual short was done just to compute the voltage. As soon as I got the voltage, now your work is done, you go away. Now I want to calculate the current. Okay, so that's how humans are. They are very selfish. So yeah, we know the, so what is the IA current? So I know if I apply KCL, IA plus IB plus IC would be equals to 0. So yeah, so what is your EA? So let us assume that I will write the voltage later on. We don't even need the voltage, trust me, we don't even need the voltage magnitude. Let's assume that EA is at some angle, magnitude of E, angle 0 degree, and EB, so it is as it follows a phase sequence of ABC, so EB would be at an angle of magnitude of E at an angle of minus 120. Magnitude of E would be angle 120. EC would be angle of magnitude of E, angle 120, right? So yeah, that's how you will calculate. So your IA would be magnitude of EA. So magnitude, sorry, EA by ZA. So EA is magnitude of E angle 0 upon ZA. ZA is basically 10 ohms. ZA is 10, right? What is EB? EB is magnitude of E angle of minus 120 degree divided by 20 angle 60 degree. Plus magnitude of E angle plus 120 divided by, this is what I have to compute, this will be equals to 0. So magnitude of E I can anyways eliminate, that will go away, right? So ultimately this will be, the magnitude of E is just a constant number that can be cancelled. So it is just a magnitude, it can be cancelled. So this will be, yeah, your 1 by 10 plus 1 by 20, this will be angle minus 180 equals to
minus 1 angle 120 by ZC. Okay. So this, right, what is angle minus 180? It is nothing but the negative sign. It represents the negative sign. So this is actually 1 by 10 minus 1 by 20, which is equals to 1 by 20 itself. That is equals to, now this negative sign again I can take inside with angle. So either I can subtract 180 or plus add 180. I will subtract 180. So if I subtract 180, this will be 1 angle of minus 60. That is equals to by ZC, right? So 1 by 20 is equals to this. So ZC would be equals to 20 angle minus 60. So trust me, you are observing the three-phase system and you think the calculations will be very complex. But if you solve everything in a tidy manner, the calculations will not be that complex. It will be very simple. So your solution would be 20 angle minus 60. That is your ZC impedance. So option C is the correct answer in this case. So you are observing, I hope, that they are asking a lot of questions from three phase. Every year a question is coming from three phase. So three phase is actually an important topic. You cannot just leave out three phase. Okay. Two balanced three phase load are connected, as you can see. One is in delta, one is in star. The voltage is this, Z1 is this, Z2 is this. The ammeter reading would, what is the ammeter reading? So basically they're asking me what is the line current, right? So let me convert everything into star. Let me convert this Z1 also into star, because then it becomes very simpler to compute the, okay, does it become very simpler? Yes, because this is a balanced load. These are all balanced loads, right? So ultimately I can do the conversion. That is, if this is the line voltage, I can compute the phase voltage as 100, right? So let me convert everything into star. Then it will be much simpler for me to compute the line current. Oh, okay. Or what you can do, you can compute this to delta as well, whichever way you find easier. So let me compute this to delta. Okay. The other thing you will do, and you will verify your answer. So let me convert Z2 into delta. So if I convert Z2 into delta, right? So we are doing delta, sorry, we are doing star to delta. Star to delta. If I am doing star to delta, what happens? Then I will do summation. So in the formula, summation will come. Okay, there is a formula for conversion from star to delta and delta to star. So I will use the summation formula. So your Z2 delta would be equals to actually, basically what happens, there is Z1 plus Z2 plus Z1 Z2 divided by Z3, something like that. So if I have a impedance like this, or let me name this as ZX, ZY, ZZ, right? And let's say I want to compute this value. If I want to convert this star to delta, so what I will do is, this will be ZX plus ZY plus ZX ZY, basically the impedances that it is connecting, divided by the opposite impedance, that is ZZ. That is the formula for conversion from star to delta. So ultimately here everything is same value, so it will become 3Z2. So 3Z2 would be basically 18 plus J24, which is same as Z1 only. So Z2 delta is connected in parallel with Z1 and which are of same value. So basically if two impedances are connected in parallel of same value, what will happen? Equivalent would be Z1 by 2. So ultimately, if I draw the per phase model, I will have impedance that has a impedance of Z1 by 2, that is 9 plus J12. 9 plus J12. Now what are they asking? They are asking me the ammeter reading. So ammeter would read the magnitude of the current. So voltage is what? So remember, this is in delta, right? So what is the voltage across these 2 points? 100 root 3. It is not the phase voltage, it is the line voltage, because I have converted everything into delta, because I want to compute this line current, right? Okay, hold on a second. Hold on. Okay, I should not have done this. Yeah, now that I am thinking, this, right, will not yield me the line current, this will yield me the phase current. I am extremely sorry. So I will do the reverse. Okay, so what I will do, I will convert this Z1 into star. Okay, what I was thinking originally. So if I convert into star, it will just be the opposite. So you will have to divide your Z1 by 3, right? So your Z1 star will be Z1 divided by 3, that's all. So Z1 divided by 3 will be 6 plus J4, sorry, 6 plus J8 which is again same. So essentially your star impedances will be same, so they will also be in parallel. So just a bit of change of plans. So we do change of plans. So this will be 6 plus j8 divided by 2, right? 6 plus j8 divided by 2, because I have this z1 converted to star, and already z2 is there whose impedance is same, 6 plus j8. So this will be 6 plus j8 divided by 2, and now I will write the per phase voltage. What is the phase voltage? That is 100 root 3. This is the line voltage. Phase voltage would be 100 volt. 100 root 3 divided by root 3, that is 100 volt. Why I did it? Because in star the phase current and the line current are same, but in delta the phase current and line currents are different. So although it does not matter, because ultimately you find out the phase current, you will multiply root 3, you will get the answer. So you can do it, okay? So but I'm more comfortable, so I do it like this. So yeah, I got the phase voltage, I got the phase impedance. Three plus j4, right? So your current magnitude would be 100 divided by 5, that is 20, right? Basically this magnitude is 5 ohms, so 20 amperes is the phase current, and it is a line current as well, because we are considering everything in star. So 20 would be your answer for the question. Okay, let's solve this question. I think yeah, this is the last question that they asked in three phase. Recently they have not asked, but they can ask, right? You can see that there are a lot of questions from three phase. So a balanced delta connected load is there. Okay, this is the delta connected load. Okay, and this is the source inductance kind of thing. And what is the telling? Having inductance of this, as shown in the figure, considering the change in the supply terminals, voltage to be negligible, the magnitude of the voltage across AB point. What will be the magnitude of the voltage across AB? Okay, interesting. They're asking me what is the magnitude of the voltage across AB. So this is in series with all of this, right? Not exactly actually. So this is connected in delta, correct? So this connection is in delta, and this is directly in series. So let me convert. Can I convert, because it is a balanced load, I can convert this into a star system. That will be, I think that will be easier for me. So currently it is delta connected. So if I convert this into star, so I will here have a Z impedance. Here I will have a Z impedance. Okay. And here I will have a Z impedance. So delta like right. Now it becomes much easier for me to compute the voltage drop, voltage between AB. So this is my point A, this is my point B, and this is my point C, right? So what I will do essentially is I just converted this thing, right? This is connected in delta, right? So if you see the A point is connected to the C point, then C point is connected to the other side of B point. So that's how we know it is delta connected. So yeah, we got the star connection. Now what essentially I will do is, of course there is a supply here, right? So this supply is 415 volt RMS supply. So it is a line to line voltage, 415 volt. So I have a voltage here, 415 volt RMS line to line. Okay, so it is always line to line. Now I can convert this into phase voltage. Can I convert this? Yeah, I can convert this into, because it is a balanced system, right? Load is balanced, everything is symmetrical. So if load is balanced, so I can say this voltage will be 415 by root 3. (415 by root 3). Okay. So yeah, now I think you can do it. Is ultimately what you have to compute. So you'll have to calculate VAN, right? Because if I know VAN, I will be able to comment what will be the VAB. I will just multiply this by root 3. I will be able to compute my VAB, right? So I just need to compute this VAN. For that I converted the supply voltage to per phase voltage. Now what I will do, simply it is a voltage division, correct? It is a voltage division. I will compute VAN, right, with respect to this reactance, and then if I know VAN, what I will do, I will do root 3 times VAN, that will be equals to VAB. Why? Because it is a balanced system, that's why I can do this. Otherwise I will not be able to do this. Okay, because only because it is a balanced system I can do, I am able to do it. Cool. Okay, so yeah, let us actually compute first of all this in the delta format, Z delta, right? What is Z delta? It will be R plus one plus j omega C, R plus 1 plus j omega C. So R is 15 plus 1 by j omega. Omega is 2 pi f c, right? 2 pi f c, c is 212.21 micro. So this would be equals to, let me compute this, pi into 50 into 212.21 into 10 raised to power minus 6. This inverse, it is almost equals to 15, right? So this is 15 minus j15. Now remember, this is delta, right? And I want to get to star. I want to convert this into star. So what happens? Delta to star means division. Delta to star, D comes first. That's what division is for. The formula for delta to star is simply Z1, Z2 or Zx, Zy divided by Zx plus Zy plus Zz. I will not explain here. I hope you know this. So I will not explain. So this will be divided by 3. So that's why this will be 5 minus j5. That is your star equivalent. So this impedance actually is 5 minus j5. What about the inductance, inductive reactance? So it is 31.83 millihenry. So if I convert this, right, 2 into pi into 50 into 31.83 into 10 raised to power minus 3, that is 10. Okay, I'm just making sure that, yeah, it is 10. Yeah, so this is actually equals to plus j10. So this reactance is actually equals to plus j10. Now something interesting will happen, you will see it. So what will be the voltage VAN? So VAN would be it is just simple voltage division rule. So this would be 400 divided by root 3 into the impedance, load impedance 5 minus j5 upon the overall sum, that is plus j10 plus 5 minus j5, which is actually 5 plus j5. Okay, 5 plus j5. So if I compute the magnitude, this magnitude is 5 root 3, this magnitude is also 5, sorry, this magnitude is 5 root 2, this magnitude is also 5 root 2. Both the magnitudes are same. So actually phase will be different, but VAN magnitude would be simply 415 by root 3. So we got our VAN magnitude. So our VAN, VAB, capital VAB would be equals to 400 by root 3, 415 by root 3 into root 3, which is actually 415. So your answer comes out to 415. And in the exam hall, you will be very confused. You'll just really same voltage. How is it possible? How am I getting same voltage or not? So yeah, your answer would be 415. Now we will start with the next chapter, that is symmetrical faults. Let's begin with symmetrical faults. So this is the first question. A 50 MVA 10 kilovolt 50 hertz. So it's a 50 MVA. Hold on. Yeah, 50 MVA. S is 50 MVA. V line to line is 10 kilovolts. 50 hertz. Star connected, right? Star connected. Uh, so it is star connected. Unloaded three-phase alternator has a synchronous reactance of 1 pu. So does not have a resistance. Synchronous reactance is a 1 pu. And a subtransient reactance. So X double dash of S as 0.2 pu. If a three-phase short circuit occurs close to the generator terminals, okay, so a three-phase short circuit is occurring close to the generator terminals, the ratio of the initial and final values of the sinusoidal component of the short circuit current would be. So basically, right, whenever my alternator is there, okay, alternator is here, right, and it of course has a ZS. What happens is they're telling me that there is a short circuit at the terminals of my alternator. So this is grounded. So at the terminals would be somewhere here. Here there is a short circuit fault to ground, obviously. It does not matter if it's to ground or not ground. So LL, triple L and LLG fault are same. This I have derived in my full course. So they are the same thing. So here, right, if some short circuit is occurring, you will say you will have some voltage EG, and your short circuit current, fault current would be EG upon ZS. Now there is a derivation that what happens is your current, right, it is a combination of DC into e raised to power minus alpha t plus a sinusoid component. Sinusoid component. This is obviously derived. We will not derive it. So what happens? This sinusoid component, right? The RMS value of the sinusoid component, short circuit current, that is nothing but the voltage, terminal voltage, that is EG. If I consider it as reference, it will be 1 pu. So this sinusoidal steady state current would be 1 upon XS, that is 1 pu only, right? Magnitude I am talking about. So it is J, I am talking about the magnitude, that is the current at steady state, sinusoidal steady state current, that is 1 pu. It is not DC, remember, it is a sinusoidal quantity. All we are talking about is the RMS value. Okay, it is 1 pu. Now, what happens is actually this is the sinusoidal steady state component, right? There is a DC component as well. Due to that, our current is actually higher initially. This is called as a transient current, right? That's why just at the point of short circuit, the impedance changes. We assume the impedance to be subtransient reactance that is given to here. The reactance has been lowered, so the current will increase. So that is what they mean by the ratio of the initial and final value. So initially the current, right, will be derived by the subtransient reactance, right? It will be derived by the subtransient reactance. So that will be 1 divided by magnitude of J point 2. That is equals to 5. That is equals to 5, right? That is your uh, uh, initial current. So what are those? The ratio of the initial to the final values. So initially I have 5 pu amount of current, finally I have 1 pu. So ratio would be I initial upon I final would be 5 upon 1, that is 5. So 5 would be your answer for the question. Let's move on to the next one. So this is the next question. A cylindrical rotor generator has a steady state synchronous reactance No, remember what are they telling us? Steady state synchronous reactance. So steady state synchronous reactance is 0.7 pu. Sometimes I will write J 0.7 pu. Sometimes I will write only only 1 or 0.2 pu. So you will have to understand it is reactance, right? So it will have that imaginary term. You can write it or you can choose not to write it. It's up to you. So if I write plus J or minus J, it should be understood it is reactance. So I can write it anyhow I want. So the steady state reactance is J 0.7 pu and the subtransient reactance is your XS double dash is J 0.2 pu. It is operating at 1 plus J0 pu terminal voltage with internal EMF of this much. So basically what is happening, the terminal voltage of the generator, it is operating at steady state. Here is my ZS. The terminal voltage, if I just draw the per phase model, this terminal voltage is 1 plus J0 and they are telling me that this generator voltage EG is 1 plus J 0.7. So can you tell me what is the current that it is delivering right now? It is exactly equals to 1 pu. At what power factor? At unity power factor. How? Because what will be your terminal voltage VT? Your VT, simple KVL, it will be EG minus IA into ZS. So what is your VT? VT is given as 1 pu. EG is given as 1 plus J 0.7. IA is I don't know, and ZS is J 0.7 pu. That is a steady state reactance. So from here, IA would be equals to 1 pu. Okay, that is what your IA is equals to, right? And now what they are asking me, this is the initial current. Following a three-phase short circuit fault at the terminals of the generator, the magnitude of the subtransient internal EMF would be. They are asking me what is the magnitude of the subtransient internal EMF if there is a three-phase solid short circuit fault at the terminals of the generator. So the terminals of the generator, if there is a fault, what will be the subtransient induced EMF? Okay. So what happens is there is a fault at the terminals. So what will happen is this will be your ZS double dash, because we are talking about the subtransient. So I will replace my ZS with ZS double dash. This will be my EG, correct? And they are asking me what is the short circuit fault, the magnitude of the subtransient internal EMF. Now, do you understand what is subtransient internal EMF? So subtransient internal EMF is the EMF just before the fault has occurred. Okay, if so, my subtransient internal EMF, right? So in this case, it is EG double dash. It will be the EMF of generator just before fault has occurred with all the with pre-fault currents and subtransient reactance. So we will have to consider the subtransient reactance. We cannot consider the normal reactance, steady state reactance. So actually our circuit will look something like this. Okay, so this will be EG double dash. So just before the fault, right? Just before the fault, what was the state? So I will replace my reactance with subtransient reactance, that is J 0.2, and just before the fault, there was no fault actually. The terminal voltage was 1 angle 0, right? This is grounded. Now what you'll do, you can do ground to ground KVL. So this is just one angle 0 to ground. So if you do ground to ground KVL, and of course the current will not change, it will still be the pre-fault current. Okay, this is the definition of subtransient EMF. That's all. That's the definition. So what is the what was the pre-fault current? That was in this case it was 1 angle 0, right? That is what we calculated. This is 1 angle 0. So the pre-fault current would be 1 angle 0. That's all. Okay. So with this you can calculate your EG double dash. EG double dash would be equals to 1 angle 0 into the reactance, that is J 0.2 plus VT, that is 1 angle 0. This is just the definition. That's how your subtransient internal EMF is defined. So you will have to go with the definition. So this will be 1 plus J 0.2. EG double dash. So this will be magnitude would be, so they have asked the this subtransient EMF, right? So 1 square plus 0.2 square under root, that is 1.02 almost. So 1.02 would be your answer for the question. Okay, that's how the definition is. You have to go by the definition, and I have discussed about this in detail in our full course. It is also present on YouTube, so you can actually watch those videos as well, because PSA 2 is completely covered on YT. So you can cover complete the most conceptual part and most scoring topic from YouTube itself. You can go there and watch from YouTube. Okay, let's now start with the unsymmetrical faults. So in symmetrical, like mostly these kind of questions come and you will be able to solve. For symmetrical fault, you will just have to use the per unit method and you will be able to solve most of the questions. Let's solve few unsymmetrical fault questions. A 30 kilovolt 50 hertz, this has positive sequence, x1 0.25 pu, x2 to be 0.15 pu, x0 to be 0.05 pu. Okay, the neutral of the generator is grounded. It is star connected and neutral is grounded. Okay, cool. With a reactance, so that the fault current for a bolted LG fault, that of a bolted three-phase fault are equal. Okay, so here is my generator, right? And the generator has some terminals obviously, but the important point is its neutral is grounded with a reactance of Xn, and they are telling me that this fault, so whatever the fault current that I get, right, if there is a fault at the generator terminals, if it's a LG fault, then the fault current, and if it's a three-phase fault, basically LLL fault, the currents are same. So do you know what is the fault current in LLL slash LLLG fault? It will be same only. It will be IF would be equals to, so it's, I will assume this to be my reference, so I will assume the EMF to be 1 pu, right? In per phase analysis, it will be 1 angle 0 divided by the positive sequence impedance. So there will not be any zero sequence current, so none of it will flow through the neutral. It will be all positive sequence because it is a balanced fault. It is a symmetrical fault. So x1, and in our case x1 is 0. J, remember it is J, right? So either I write J here or I directly write J here, it does not matter. Okay, ultimately you know it is a reactance. So this will be 1 divided by J 0.25. So your current would be minus J4. That is your fault current in 3 phase. And what happens in LG fault? In LG fault, all my sequence network is in series, right? So my, what is the positive sequence network? I will, first of all, positive sequence network will have a EMF, positive sequence EMF of 1 angle 0, right? And of course it will have its positive sequence reactance. Okay, so this will be J 0.25 pu. Okay, and then of course all the sequence networks will be in series, the positive sequence, negative sequence and zero sequence in LG fault. So I have negative sequence. So negative sequence don't have a voltage, it only has a reactance, that is J 0.15 pu, and zero sequence. So 0.5 pu, and of course ultimately what happens if it is grounded to neutral with the reactance Xn, right? So the all of the fault current will flow here. So what happens, because it's a zero sequence fault current, this will be replaced with 3xn. This concept I've discussed in full course actually. Actually what happens, the 3xn is drawn here itself with the positive sequence network. No, it is not drawn here actually, sorry, it is drawn here. It is drawn here. Okay, J 3xn, and of course they are discussing it is a LG bolted LG fault. Bolted LG fault basically means that to the fault, right, there is no reactance, it is directly faulted to the ground, directly short circuited. One of the line is directly short circuited to the ground. So that's why, that is what we mean by bolted. So all of this will be in series, and ultimately this is your zero sequence current. Remember, this is not your fault current. Okay, this is your zero sequence current. Your fault current will be 3 times this. Okay, all these concepts we have learned in the full course, so I will not explain here. You can go, the videos, YouTube videos are there, so you can go and watch that. So this is your zero sequence current. Your fault current would be 3 Ia naught, so that would be equals to 3 upon J 0.25 0.15 plus J 0.05. Okay, and of course we have plus J 3xn. Okay, so this will be equal to my 3 phase fault current, that is minus J 0.4. So minus J is also here, right, if I take the J common. So ultimately your equation comes out to be 3 by, if I add all this up, this will be 0.3.45 plus 3xn will be equals to 4. So if I take that, so this will be 0.75 is equals to 0.45 plus 3xn. So from here my xn would be equals to, this is 0.3, so it is equals to 0.1 pu. Remember, there will be a J, but they are asking just the, okay, the grounding reactance in ohms. So in ohms they have asked, okay, they have not asked in pu, okay, they have asked in ohms. So this is obviously J is there, but ultimately will report the magnitude. So I will have to convert this into actual value. So we know actual is equals to x pu into x base. So simply I have to multiply 0.1 with its z base. What is z base? If you remember, z base was your VB square upon kVA. Okay, VB is what? It is line voltage. You might have a doubt, sir, it should be phase voltage. Yes, it should be phase voltage, but in the bottom also it should be phase power. But are you writing phase power? No, you're writing three phase power. So what happens? So this is actually root 3 into phase voltage upon 3 into single phase power. 3 will be cancelled due to this square. So it will be phase voltage upon phase power, something like that. So because your so I will not explain here because that is already explained in the full course. So just a bit of intuition I gave you why we will write line voltage here. So what is your so this, right, whatever number they decode report here, it is all line voltage. This is three phase power. So this is 30 kV square. So 30 kV becomes MV. So it does not matter. I will not have to change anything. So 30 kilo becomes mega. Upon I will write mega only, and mega will be cancelled. So it will be 50. So this will be equals to 30 square divided by 50 into 0.1. So this will be 1.8 ohms. Okay, this will be 1.8 ohms. So yeah, let's solve the next question. So this is the next question. Suppose IA, IB, hold on, let me check whether, yeah, everything was correct. Yeah, suppose IA, IB, IC are set of unbalanced current, and 0 seconds component of IB is given, and phase current IA is given, and phase current IC is given. What is the phase B current, right? That is what they are asking me. So they are set of unbalanced current. Okay, cool. IA, IB, IC are set of unbalanced current. So I know IA. So what we know this thing, right? So if I have IA, they should have also provided the phase sequence, but they have not provided the, okay, IA. So assumption is ABC is the phase sequence. So if ABC is the phase sequence, right? So IA will be IA naught plus IA1 plus IA2. Your IB would be IB naught plus IB1 plus IB2. Now the thing is that if my phase sequence is A, then B, and then C, sorry, this will be B and this will be C. So between these I have a phase difference of minus 120, right? And we know that our alpha operator, so all this has been taught in the symmetrical components, is 1 angle 120, or you can take it minus 120, it's up to you. I will take plus 120 because that's the standard. So I have to move negative 120 because after A, B is lagging by 120, right? B is lagging by 120. So I have to move negative by 120. Hence, it will be alpha square. All these things have been taught in the full course that is present in the YouTube itself, like only the PSA 2 part. So all this has been explained there. So actually, what happens? So this is the positive sequence component, right? So I will follow the same sequence. So it will be A after B, then C. So this will be actually alpha square into IA1. All these things has been taught, so I will not explain much here. And this is just the opposite, right? Because it is a negative sequence, so the phase sequence will change. This will be ACB. So it will be alpha into I2. Okay, then we have IC. IC is, so IB naught is what? IB naught is nothing but I naught. So these things are equal, right? Zero sequence components, everything is equal. So this will be IC naught plus this will be just the opposite, because if you see, your C leads A by 120. So this will be alpha. into IA1 plus alpha square into IA2. Okay, just the opposite. Now what we are concerned about is if I see that your IC is combination of this and this, right? So IC 0.1 is already present, that is IC naught. IC naught and IB naught are same, 0 sequence components are same. So IB naught and IC naught are same. So ultimately, right, your IC is known. IC is what? One angle, that is nothing but 1 angle 120 is nothing but alpha. Alpha is equals to alpha plus 1, right? This is 1 angle 0. Sorry, alpha was 0.1 angle 0. Alpha is 1 angle 120. So this will be equals to your IC naught, that is 0.1, that is same as IB naught plus alpha into I1 plus alpha square into I2. So from here I get a very good relation, that is IA1 plus alpha. I take the alpha common, right? Into IA2 is equals to 1. Okay. So IA is also given to me, that is 1.10. So this also I can solve actually. Here if I see IA is 1.1 angle 0, that is equals to IA naught. IA naught is 0.1 plus I1 plus I2, right? So I1 plus I2, from this equation I get I1 plus I2 equals to 1. Both of them are 1. So what happens is I can equate these two. What will happen? I1 will be cancelled. So essentially your alpha into I2. Okay, hold on. What is happening? Something is going wrong. Okay, if both of these summations are equal, okay, how is it possible? Both of them are 2 0. Am I doing this correctly? Certainly yes. Okay, alpha into and what is three-phase system? IC is this, IB naught is that. This would be 1 angle 0. Okay. So this is equals to 1. So I1 is cancelled. Give me 1 second. I1 is cancelled. This is alpha into I2 is equals to I2. When is it possible? When alpha into I2 is equals to I2? When your I2 is 0. So your I2 is actually 0. Okay. So what am I doing is I'm equating these two equations. Correct. If you equate these two equations, what happens? You get I1 plus alpha into I2 equals to I1 plus I2. So I1 will be cancelled. So alpha into I2 is equals to I2. So I can take the I2 on the other side. So this will be alpha minus 1 into I2. Now certainly equals to 0. Certainly alpha is never equals to 1, right? Alpha is not equals to 1 because alpha is equals to, I know, alpha is equals to 1 angle 120. Right? 1 means what? It is 1 angle 0. It is certainly not equals to 1 angle 0. That is the definition of alpha that I have defined. Right? So this is certainly not possible. Alpha will be this. Okay. So if alpha is this 1 angle 120, then what can I say? What can I say? So yeah, certainly IA2 has to be 0. So IA2 is 0. And if IA2 is 0, then certainly from here I can get IA1 to be 1. And with that I will be done with my answer because I have to decode IB. IB is IB naught. IB naught is 0.1 angle 0 plus alpha square into IA1. IA1 is 1. So it will be alpha square into 1 and alpha square is 1 angle minus 20. Right? 1 angle minus 20 plus alpha into IA2. IA2 is 0. So it is actually 1 angle minus 120 plus 0.1, okay, which is present in option D. So option D would be your correct answer for this question. Okay, so yeah, let's move on to the next question. So this is the next question. The valid the valid positive negative zero sequence impedance respectively for a fully transposed three-phase transmission line would be. Okay, if a line is fully transposed, the valid positive negative zero sequence the valid positive negative and zero sequence impedance would be. If the line is fully transposed, then its positive and negative zero sequence will always be equal, and if it's a transmission line, right, then its zero sequence impedance will always be higher than the positive and negative sequence. So we see all three are equal, not possible. We see the zero sequence component is less than the positive sequence component, not possible. So what happens is the positive and negative sequence components in generators is higher. Okay, positive sequence components in generator is always higher, positive and negative sequence components, because they use on the principle of three phase currents. They use the principle of three phase currents, that's why they are higher. In transmission line, the zero sequence components are higher. The zero sequence, not component, sorry, zero sequence impedance or reactance is higher. So in transmission line, the zero sequence reactance will be higher, that is present here. And obviously in transmission lines, if it is fully transposed, then as it is symmetrical, so its negative and positive sequence impedance will be equal or reactance will be equal, that is present in option B. You see here again your reactances are not equal, and again your zero sequence is less than negative sequence, again not suitable. So option B is the most suitable answer. Option B would be your answer for the question. Let's solve the next question. The two bus power system is shown in the figure 1, and the positive negative zero sequence diagrams are shown. Okay, all reactances sequence diagrams are in PU for a bolted line to line fault. So we have a line to line bolted fault, so there is no fault impedance, it is directly zero. Fault impedance is zero basically. They have also mentioned in the bracket between phases B and C. Okay, so between phase B and C there is a fault. The magnitude of the fault current from phase V to C would be magnitude. So basically the phase current IA is 0, and after derivation what happens, your sequence net the positive and negative sequence networks are in parallel with each other. Okay, and zero sequence network is not connected, right? So what happens is you will have your positive sequence impedance, and okay, positive sequence network is this, right? So what you do, you convert this positive sequence network, zero sequence network, and all this to a singular network. Okay, so but before that I have to check at what exactly at what place fault is occurring. Fault is occurring at bus 1. So if fault is occurring at bus 1, right, so I will compute the VTH and ZTH from bus 1, okay, for all the networks. So what is the VTH here? The open circuit voltage, right, at bus 1. So if fault is occurring at bus 1, right, so fault is occurring here, so open circuit voltage would be, first remove this point and then calculate the VTH between here and here. So for that I will need the help of EG. Okay, have they given us anything regarding EG and EM? 2 bus power system, 1 alternator supplying network through positive sequence. Okay, so assume that the pre-fault condition they are all in 1 angle 0, right? These voltages are 1 angle 0 if nothing is mentioned. Now if these voltages are 1 angle 0, you're very lucky, right? Because this voltage difference is same, what will happen, there will not be any current flow. Okay, they have not mentioned anything, right, regarding the pre-fault condition. So I will have to assume that I will have to assume that both of them are at 1 angle 0, right? Anyways, if the voltage between this bus and bus, there should not be any phase difference. So here also ultimately we will get 1 angle 0. So your VTH is 1 angle 0. Okay, VTH is 1 angle 0, right? And what about your XTH? What is your XTH? So for XTH, I'm only talking about the positive sequence network now. So XTH, if I compute the equivalent reactance from here, what happens? This is grounded, right? You assume this to be grounded, common reference point. So this point is there, and the voltage sources will be short circuited. So ultimately, what will happen? These two will be in series. This is only by its own, and ultimately at node 1 to ground, I have j.2 and on the other side I have j.3. So these two are in parallel. So it will be j.2 plus j.3. Sorry, basically what will happen, the xth1 will be j.2 into 0.3 upon 0.5. So they are in parallel. I'm doing this in a fast manner because I'm expecting that you already know all these things, right? So this will be equals to j.2 j.3 upon 0.5. So j 0.12. This will be your j 0.12 pu will be your equivalent reactance. Positive sequence reactance. What about negative sequence reactance? So negative sequence, there is no voltage in negative sequence, only we have to calculate the reactance, right? So voltage is 0 basically. So if I see again the same thing, j 0.1 will be in series and this will be in parallel with j 0.3. So ultimately your negative sequence reactance, equivalent reactance is j 0.12 only, and your negative sequence EMF is 0. There is no voltage source. What about a zero sequence? You don't need to worry about the zero sequence since a line to line fall, right? You don't need to worry about that. You can calculate the equivalent z naught. What will be the equivalent z naught? So again, assume this to be my reference 0. So your z naught, right, or your xth0 would be equals to j 0.06 plus j 0.09. So that would be equals to j 0.1 pu. Okay, that is equal to j 0.1 pu, 15 pu, right? So that is what your xth0 is equals to. So we got our xth0, we got our xth2, we got our xth1, right? So yeah, that is what we got. Now okay, so how are the sequence networks connected? So here I will have, there is no neutral reactance and it does not matter actually in this case. So I will have my jxth1, I will have my vth1, then actually here I should have connected the fault impedance, whatever was the fault impedance, but it is 0 because it is directly bolted to that line, right? So I have phase B and phase C, those are directly shorted, that's why there is no fault impedance. So this will be directly, I will connect this in parallel with jxth2, and then this equivalent xth0, it won't matter actually because this will be anyways not connected. This will be jxth0. Now what is your fault current? So this current, right, whatever we get, this is actually the, so this is my IA1 current, right, and this is my, so what actually happens is, this is supposed to be my, hold on a second, let me just check. So IA1 fault current, yes, yeah. So so IA2 current is supposed to be like this, it should come out of the network, but it will be negative. It does not matter for us. What I am concerned about is IA1. That's all what I am concerned about. Okay, so IA1, right, is not the fault current. Remember, I will tell you what is the fault current, but what is the positive sequence current during double line fault? During double line fault, we know the negative sequence and the positive sequence networks are in parallel, and the zero sequence networks is disconnected. Basically, it won't matter. Okay, so what is the IA1 current? IA1 current is equals to VTH1 upon J XTH1 plus, hold on, J XTH1 plus XTH2. Okay, This is my positive sequence current. Now, do you know that what do I have to find out? I have to find out the fault current, and we know I have three phase, right? And in three phase, phase B and C are shorted, and phase A is open circuited. That is what happens, right? Phase A becomes open circuited. That is what my double line to ground fault is. So that is what my, so not double line to ground, sorry, that is what my double line fault is. So we know that your IA current is actually 0 ampere, and your fault current, right, it will be equals to, because they have asked me the current from B to C, so they are talking about this current, that is equals to the IB current itself. So my IB current is I fault, and what is IB? IB is equals to, IB is equals to, sorry, IF is equals to IB, IB is equals to IB naught plus IB1 plus IB2, and I have already told you that what is my this relation, right? This in the previous question we have discussed, IB is equals to alpha square into I1 into alpha into I2, right? Alpha is 1 angle 120. I have discussed regarding this in the previous question, so I can directly use this. This thing can be directly used. Okay. So this is my fault current, and in this case what happens, your IA naught is 0, right? There is no, so because it is open circuited, right, so there is no 0 sequence component of current, so IA naught becomes 0. Okay, IA naught becomes 0, and what happens, your IA1, so IA2 is supposed to be outgoing from the network. Okay, so IA2 is nothing but minus of IA1. IA2 is nothing but minus of IA1 if you apply the KVL properly. Okay, so I should actually not draw this direction. So the current should always leave the sequence networks, correct? So your IA1 and IA2 are negative of each other. Although they are in series, I can see that, but you should represent your sequence current coming out of the network. Okay, so your IA1 and IA2 are negative, so I can replace this IA2 with minus IA1, and I can replace this with 0. So actually your fault current will be converted into this. This will be alpha square I1 minus alpha into IA1. Okay, so trust me, no one will explain you all this, right? They will directly solve directly with the formula. That is what happens in most of the coaching institutes. So now what you will do is, you will you can take IA1 common, right? So IA1 would be alpha square minus alpha. Okay, so alpha square, right? Alpha is 1 angle 120. Alpha square would be 1 angle plus 240. Okay, and alpha is, hold on a second, this is 1 angle 120 only. Alpha square would be some, so this is my reference, right? 0 degree. Okay, so alpha square, that is 1 angle plus 240 or 1 angle minus 120 would be here, right? This is my alpha square, and your alpha is somewhere here, but I have to represent minus alpha, that would be somewhere here, right? So this is your alpha, but I will have to represent minus alpha, that will be exactly opposite. This is my minus alpha. So what happens is, this angle is 180 and this much difference is 120, right? So this is the difference, that is 60 degrees, and we know magnitude of both of them is 1, and if they have a phase difference of 60, the resultant is the angle bisector, whose magnitude is root 3 times the previous magnitude. Both of them have equal, that is 1. So it is root 3 and it is a bisector. So it is actually, in this case, it is minus j root 3 because it is at minus 90 degrees. So this will be actually minus j root 3 into IA1, and that is how this derivation comes. And in everywhere else, in all the solutions, they will directly jump to this equation. Yes, you can remember it. Of course, you can remember it, right? But if you don't want to remember, you can derive on point, on spot, on the examination hall. So you should have the capability to do that. correct? So I got my ia1 is this value, right? So ultimately what I'm concerned about the magnitude. So let me replace my ia1 is vth1 minus j is there, vth1, so root 3 into vth1 divided by xth1, so plus j xth1 plus xth2. Okay, so j and j will be cancelled, so this will be equals to this, right? So yeah, so your answer would be root 3 into vth1 is 1. So I'm concerned about the magnitude. Vth1 is 1, so root 3 into 1, so magnitude of if, right? Root 3 into 1, and this would be xth1 plus xth2. Xth1 is 0.12, xth2, sorry, both are same, right? 0.12, 0.12. So I'm only concerned about the magnitude, right? So it will be 0.12, 0.12, so plus 0.12 into root 3, 7.21, 7.217 pu. Okay, that is my magnitude, right? They have asked the magnitude of the fault current. So magnitude of the fault current is 7.21 pu. You can actually exactly compute the phase as well. All those things, if you take consider, you will be able to compare, because actually what will happen, this will be minus j actually. So answer will be minus, but I am concerned about magnitude, so it will be 7.217. That is the answer for this question. Very good question actually, good question. Now let's solve the next question, right? This is the last question that they asked from unsymmetrical faults. So for a two-phase network, the phase voltages are given. So it's a two-phase network, right? Are expressed in terms of V alpha and V B like this. Okay, VP and VQ are expressed in terms of sequence voltages. Okay, VP and VQ are expressed in terms of sequence voltages V alpha and VB, V beta. The possible options for the matrix S is okay. So they are represented in terms of sequence voltages. So basically, right, VP and VQ is a two-phase network. VP and VQ is a two-phase network, right? So VP is equals to what? VP is equals to, let's say, so it's, I can observe that it's a 2 cross 2 matrix, and it has to be, otherwise matrix multiplication would not be possible. So let me name the elements S1, S2, S3, S4. These are my elements. Okay, so my VP is equals to VP is equals to S1 into V alpha, right? S1 into V alpha plus S2 into V beta, right? Am I correct? S1 row into column, yeah. And your VQ would be equals to S3 into V alpha plus S4 into V beta. Okay. Now something interesting will happen. Remember, they have told options, so it's a MSQ. It's not a MCQ. So yeah. So what will happen here? That if I assume this particular equation, right? If I assume this particular equation, so your VP is V alpha plus V beta, and your VQ is only V alpha. Will that be possible? So basically, if it's a two-phase system, right? If it's a two-phase system, the phase difference is it is one is V angle 0, another one would be V angle minus 180. Okay, that is what we mean by two-phase system, right? Yes. So this is unbalanced actually. Uh, that is fine. Uh, okay, hold on. But this has to be balanced. V alpha and V beta. So essentially, a balanced two-phase system is basically same magnitude, opposite sign. So it will be plus V minus V, correct? So if it's plus V and minus V, I can replace my V alpha and V beta to plus V and minus V, right? So basically, what are these? These are my actual voltages that are what do you call it? That are not balanced. And this alpha and beta is a two-phase balanced system. I can multiply these coefficients to make it, to add them up, to add the balanced system to compare to the unbalanced. So that is what we do in the symmetrical components. That is what we are doing. So essentially, your Vp would be equals to S1 V minus S2 V2. Okay, and your VQ would be equals to S3 V minus S4 V only. It will be V only, right? So I'm just thinking something. So in okay. So what can be my S? So if my S matrix is all ones, if it is all ones, right? If my S matrix is all ones, then what will happen? Then Vp and Vq will be same. Correct? Vp and Vq will be same. That should not be correct. Okay. So all ones is not possible. Okay. But next, another thing is you cannot choose 0. If you choose 0, then basically what happens? Then essentially you say that your VQ is equals to uh, if you say this last element to be 0, right? Your VQ is equals to only S3 into V. Okay, it does not have the other phase component, it only has this component. So you will not be able to define all kinds of system with this, right? So basically your V is a positive number, right? V is V angle 0. S3 is also here, it is positive. So only you will be able to define positive voltage for VQ. You will not be able to define negative voltages, correct? Not be able to define negative voltages, right? So which is again in a two-phase system there can be negative. So this is V of minus 180, right? It can be negative voltage. So like you cannot define the phase 180 with this. So that's why 0 is not possible. 0 is gone. These two are possible. Okay. These two are possible. How? So you can check that whether these matrices are, first of all, any element 0 is not possible, that is point 1. Okay, then after eliminating that options, you can check whether my rows are linearly independent or dependent. My rows must be linearly independent, so that I will be able to write my Vp and Vq in terms of V alpha and V beta independently. That is the procedure basically to check it. So how to check it? Just check the determinant. If the determinant comes out to be non-zero, that means all the rows are independent. So here if I check the determinant comes out to be non-zero. So yeah, this is a valid solution, and this one also is a valid solution because the determinant comes out to be non-zero, because and hence if it comes out to be non-zero, then I can linearly write my V alpha and V beta. Sorry, then I can write linearly my Vp and Vq in terms of V alpha and V beta uniquely. Okay, that is the purpose of checking the determinant. So the rows must be linearly independent. This was a good question that got asked in 2024. So option A and D are the correct answer for this question. Now we will move on to power system stability. Let's begin with stability. So this figure shows the single line diagram of a power system with a double circuit transmission line. So we have a double circuit transmission line. The expression for electrical power is 1.5 sin delta, where delta is the rotor angle. Okay, the system is operating at stable equilibrium with a mechanical power of 1 pu. Okay, if one of the transmission line circuits is removed, so one of them is suddenly removed, the maximum value of delta as the rotor swings is, so delta critical or delta m is 1.21. radian. If the expression for electrical power with one of the transmission line removed is P max sine delta, then the value of P max in PU is. So they are asking me what is the value of P max. So this is a very big question. Okay, so they should have also properly mentioned that this is supposed to be motor or the load, and this is my transmission line, this is a transformer, and this is the generator. They should have actually properly mentioned it. They did not, but that's fine. So if I have a double circuit transmission line, what will happen? So if I draw the single line diagram or the reactance diagram, so I will have a generator here which will have its own reactance xg. Now I don't know whether I need to assume the xg or not. Maybe the best thing that I can do is I can actually, hold on, if one of the transmission line is removed, P max and delta maximum. Okay, let me think about this. So then what are they asking? They are asking me the, if one of the transmission line is removed, then what is the P max? Okay, so let's assume that the generator has some reactance. Actually, they should properly mention whether the generator has a reactance, whether the transformer has a reactance xt. So don't forget there will be J as well. I'm not writing it, but you understand that, right? All these are inductive. So then there is a double circuit line xtl, xtl, and then ultimately there is the motor or the load connected. Right here, the potential is 1 angle 0, and I don't know the potential of the generator. It will be something Eg angle delta. Correct? I don't know what is the exact potential. Now in this case, can you write down the expression for power transfer? It's very simple, right? So power developed, electrical power developed will be Eg into Vt. Vt is 1 into the angle between Eg and Vt, that is delta minus 0, that is delta divided by xg plus xt, whatever is the reactance between the two voltages, right, plus xtl by 2 because they are in parallel by 2. Okay, this will be sine delta actually. Correct? Yes. And which is actually the expression for electrical power is given to us, that is actually equals to 1.5 sine delta. And of course the load, right, Pm is 1 pu. So this is the electrical power developed by the generator, that is what it is delivering. Correct? Now this can be written as, let's say, some P max 1 sine delta. Correct? So my P max 1 is equals to what? Now if nothing is mentioned, I will have to assume my Eg to be 1 pu. Okay, you assume your Eg to be 1 pu because they have not mentioned anything. So you will assume your Eg, the voltage, to be in 1 pu. Okay, nothing is mentioned. You have to assume it. Otherwise, you will not be able to solve this question. So magnitude of Eg would be 1 pu. Now you might say, if this is also 1 angle delta, this is also 1 angle 0. How is power transfer happening? Yes, power transfer is happening because there is a angle difference. That's why. So this will be coming out to be 2 by xg plus xt, right? So I can assume my xg plus xt to be some unknown variable, xg plus xt to be some unknown variable capital X. Okay, so this will be capital X plus, hold on, this will not be whole divided by 2, right? I'm extremely sorry. Only xtl will be divided by 2. Xtl will be divided by 2. Okay, capital X plus xtl divided by 2, that is equals to sine delta, and this expression is actually equals to, hold on, this will be 1 only, right? This expression is actually equals to 1.5 sine delta. So from here I get a relation between, so this is the developed power, right? So this will be equals to 1.5 equals to, or 3 by 2 is equals to 1 by x plus xtl divided by 2. So x plus xtl divided by 2 is equals to 2 by 3. Okay, this is one relation. Now what happens when the circuit, one of the circuit goes out of operation? So one of the transmission line goes out of operation, right? Now if one of the transmission line is suddenly removed, then they are telling me that the electrical power developed, if the expression for electrical power with one of the transmission line circuit removed is P max sine delta. Can you tell me if this transmission line is removed, then what will happen? Essentially the circuit will be converted into this. So we'll assume this to be 1 angle 0. So what will happen? Basically this upper transmission line will be removed. So this will not be there. So now what is the expression? This will be PE will be equals to 1 into 1 sine delta upon xg plus xt, that is capital, that is equals to x only, plus xtl, and this is equals to my P max sine delta. Okay, so they are asking me what is the value of P max, right? So P max actually is equals to 1 upon x plus xtl. So I need to calculate this. For this I need the value of x and xtl both. Okay, now actually you don't need to do all this, I'm just explaining you the question. Actually what will happen? Actually we will use this relation. We will use this relation, that's all. So what happens according to the equal area criterion, if I plot the electrical power developed with respect to delta PE, right? So initially this was my, so if you observe one thing, that this is my P max in the case 2, and in case 1 this was my P max, right? This was 1 by x plus xtl by 2. So the denominator has reduced in the case 1. So the overall number will be higher in the case 1. So overall electrical power developed in the case 1 would be higher. Basically the peak of the sine delta would be higher. P max 1 will be higher, right? So P max 1 was actually equals to 1.5. If you see, it was actually equals to 1.5. P max 2 would be smaller because the denominator has increased. So this is my P max 2 basically, which will be somewhere here. Now what is happening essentially, obviously the peaks will occur at the same time, is I have a drawing is not up to scale. Let me make it this. So I can solve this in a very fast manner. That is fine. That is not the purpose, right? I want to explain the concept as well. So this is my PM naught or P mechanical power, that is constant, and that is 1 pu. Okay, drawing is not up to scale, right? So initially everything was in steady state, and this is my P max basically. P max 2 to be specific, but they have named this as P max, so I will name this as P max only. So initially everything was in steady state, so the intersection was here. I was in steady state, I was in stable operation, so delta will be less than 90, so I will be lying around here. Why it will be less than 90? If you don't understand, you have to go and watch the full course. Power system stability completely has been covered on YouTube. Please go and watch that. It's a very good concept. Okay, so this will be less than 90, so it will be some delta naught. Now what they're telling me, suddenly what happened, the line got disconnected, one of the transmission line got disconnected, so the electrical power developed is this now. So what happens is the mechanical power developed is here, right, and electrical power developed is here. So there is some sort of deacceleration. If you see what will happen if I draw this properly up to scale, let me draw this more up to scale, right, that will be easier for us. Okay, it is not a very good sinusoid, but I hope you get the point. This is nothing but the sinusoid only from 0 to 180. That is what I am doing. I should actually have properly drawn the sinusoids. So this is actually 180 degrees here, right? This is pi in radians. So what happens is, it tells us that once the line has been disconnected, so my electrical power developed does not follow this relation, it follows this one, and we see my PM naught is greater than P, So what will happen? There will be some deacceleration. There will be some deacceleration. So the motor speed will reduce. If the motor speed reduces, the delta naught also will reduce. Okay, and there will be some to and fro action. So essentially what happens is we get this negative area, right? So there will be some negative area, there will be some positive area, and at critical condition, right? So because again it comes into contact here, right, somewhere here, like basically this line and this line intersects at this particular point. So this is the point where the motor will reach the steady state again. So but for that we have to calculate. What do we have to calculate? They were asking me so they have told me that as the motor swings, the maximum value of delta as the motor swings is this. Okay, so basically what will happen, the motor will swing from here to here. So because the motor now follows this curve, so motor will swing. Sometimes there will be some deacceleration, then again there will be some acceleration. Due to that, motor will swing, and the maximum value of delta after the motor swings is 1.2 1.212 radians, correct? So 1.212 radians would be somewhere here. If you could not understand the concept, you will have to go and watch the you will have to go and watch the stability chapter. Okay, you will have to go and watch the stability chapter. So what happens is there is a concept known as equal area criterion. Okay, so what does equal area criterion tells me? Equal area criterion tells me that the maximum swing is delta m. So what happens if this is my PM naught, right? So we compute the for a, so it is delivering a constant load, right? Yeah, electrical power. So for this particular generator, it will be PE minus PM. That will be my hold on a second. The input, sorry, the system is operating as stable equal to the mechanical power. Okay. The mechanical power is equals to 1 PU. Sorry, this PM, right? This is the mechanical power input to the motor. Okay, sorry, what I'm talking about. So this PM naught is the mechanical power input to the motor in the shaft. Okay, in the shaft. Let me again explain you. Like I just misinterpreted something. So PM is the mechanical. This is not the this power, right? This is not this power actually. PM is the mechanical power input to the motor. Okay, and it is delivering some constant power. We don't care about that right now. Now what happens is, once if this transmission line is here, the electrical power follows this relation. If the transmission line is removed, the electrical power now follows this relation Pmax, and which will be lower than the previous Pmax. That is established. Now if this is established, what will happen is the electrical power has reduced, the output power of the motor has reduced, and the input power is still PM naught. That is what I am providing. I am rotating the machine, right? So I am providing some PM naught amount of power, that is 1 PU, and the electrical power output is PE 2 now. Okay, PE2. PE2 is the case 2. So if you see here, I just explained the graph wrong. I will explain it again. So if you see PM naught is greater than PE, so what happens is this is greater than PE, right? So what is this? This is nothing but this is equals to M alpha, right? All this has been derived in the full course, so not going to it too much. But what happens essentially is that alpha is positive because PM naught is greater than PE2 at this particular point at delta naught. So there will be some acceleration. If there is some acceleration, what will happen? If I am lying here, the angle will increase, and it will go till delta max that is provided in the question. If it goes till delta max, then what happens? Then again there will be some deacceleration. Why will be there some deacceleration? Because if you see in this region, my electrical power is greater than the mechanical power. So if electrical power is greater than the mechanical power, so M alpha is negative, so there will be deacceleration, and this will keep on happening, but ultimately it will reach the new steady state here. This will be the new steady state. Okay, this will be the new steady state, but I am not concerned about the new steady state. So what equal area criterion tells me is that if I am swinging from delta naught to delta m, whatever was the positive area, I will get the same negative area, or the overall area under this curve, right? Overall area under this curve, PE, PM naught minus PE2 integration with respect to delta would be equals to 0. Okay, that is what my equal area criterion tells me, and with this I will be able to calculate the relation of P max. That is the purpose of this question. That's all. I could have directly used this relation here and solved it, but that's not the purpose. The purpose is to explain you, so I am going the extra mile. If you could not still understand, you will have to go and watch the full course. So what is happening here? PM naught is never changing, right? It is always 1. And what is P2? P2 is basically the electrical power in the case 2. Case 2, it is basically P max sine delta, right? It is P max sine delta. So it will be P max sine delta, and I will integrate from delta naught to delta m. So delta m is provided to me, that is 1.221 radians. Delta m is 1.221 radians, and delta naught, what is delta naught? So delta naught basically is the initial rotor angle. How do I compute the initial rotor angle? If you observe, initially this line and the green line are intersecting each other. That means initially it was at steady state, so there will not be any acceleration and it will follow this curve. So initially your PM naught will be equals to your 1.5 sine delta naught. Because it is a steady state, there will not be any acceleration. So the electrical power developed and the mechanical input power are equal. So this will be equals to PM naught is 1. So ultimately your delta naught, if we compute from here, this is equals to 1 PU. Right? So ultimately this will be 1.5 inverse sine inverse, that is 41.41 degrees, 41.81 degrees, or what can I say, into pi divided by 180. So or 0.73 radians. Okay, it is 0.73 radians, that is my delta naught. So I will solve this now. I'll simply solve this now. So this shall be equals to 0. So if I integrate this, this will be delta m minus delta naught. This will be actually plus P max cos of delta m minus cos of delta naught. Okay, equal to 0, right? Equal area criterion. So ultimately your P max, people will directly use this formula. They will not even explain you this much. So P max would be equal to delta m minus delta naught, right? Delta m is 0. So P max is equal to delta m minus delta naught by cos of delta naught minus cos of delta m. Okay, this is the, like they will directly say you this is the formula, that's all. Remember it, but they will not derive it. So this will be delta m minus delta naught. So delta m is this much, delta naught is hold on, delta naught was what? Sorry, this is delta naught. Sorry, this was delta naught. Sorry, this was delta naught, and delta m is 1.221. So this numerator comes out to be 0.491 divided by cos of delta naught. Cos of delta naught. So cos of delta naught would be 41.81. Let me keep it in radians only. So make sure you are very careful with the radians and degrees. So 0.73 cos is 0.745 minus cos of 1.221. So that is actually equals to 0.342. So this denominator comes out to be 0.410 into 0.491. So this is actually 1.22. Okay, PU. So your P max comes out to be 1.22. So I don't need to explain all this actually. In the exam hall, you already know these things will happen. But because I'm explaining you the question, that's why I'm explaining this much. You already know that P max will reduce only, it will not increase. Okay, you already know these things. Okay, so yeah, let's solve this next question. This was a pretty good question, conceptual. People will use this formula just, but we don't, obviously we don't just use the formula, we try to derive as much as possible. Let's solve the next question. A 3-phase 2-pole 50 Hz synchronous generator has a rating of 250 MVA. So its rating is 250 MVA. Okay, and its power factor is 0.8 lagging. Okay, the kinetic energy of the motor, kinetic energy of the machine at synchronous speed is 1000 megajoule. So from this I can get my inertia constant H, that is actually equals to kinetic energy of the motor upon the rating in MVA. So that will be 1000 by 250. This will be 4 unit will be in seconds, and from this I can actually get my M will be GH upon pi f. Okay, so I'm just writing all these things down because I tend to forget. So if they will be used, I will directly copy this formula. Okay, yeah. Now what they are asking me, the machine is running steadily at synchronous speed and delivers 60 megawatt power at power angle 10 degrees. So it is running, so omega r, the rotor speed is same as synchronous speed, and it is delivering a power P of 60 megawatt at a rotor angle of 10 degree electrical. It is electrical degrees. If the load is suddenly removed, assuming the acceleration is constant for 10 cycles, the value of the power angle or the rotor angle, actually power angle is same as rotor angle only, does not matter. Okay, just the difference is basically power angle is measured in terms of electrical degrees and rotor angle will be measured in terms of mechanical degrees. That's the only difference. Okay, but sometimes they go hand in hand. Be very careful. Okay, so the value of the power angle after 5 cycles. So we know this formula actually. This I have derived in my full course. That is, it is nothing but similar to a acceleration formula, right? So you remember this formula, right? Uh, S equals to S naught plus half ET square. This was a very good physics formula, displacement and with respect to acceleration and time. So similarly here also in curvilinear motion we have delta t, delta of t. If the acceleration is constant, we can use this formula, will be equals to delta naught plus half. Now everything is in angular, right? So A is linear motion, so we will have alpha. Alpha is for angular motion, and T is obviously does not matter, T is linear or angular, so it will be T square only. So ultimately we have to compute alpha. And do you remember what is alpha for a generator? For a generator, what comes first? We first provide the mechanical power, and from that there is some opposing effect, that is the electrical power that it delivers to the load. So Pm minus Pe will be equals to my M alpha. How to remember this? All this has been taught in the full course, right? So this actually defines the acceleration equation. This is the acceleration power, Pm minus Pe. If I provide more mechanical energy, the rotor will accelerate more. From this we can get our value of alpha. So remember, everything is in electrical degrees. Hold on a second. Yeah, everything is in electrical degrees, right? So I will write everything in electrical degrees only. Okay, if everything is in electrical degrees, I will write everything in electrical degrees only. So alpha will be equals to Pm minus Pe by M. Now they have told me that suddenly they have removed the, if the load is suddenly removed. So what was the initial load? Obviously it is at steady state, there is no acceleration. So your Pe will be equals to Pm, because there is no acceleration, alpha is 0. If alpha is 0, Pe will be equals to Pm. Now suddenly your load has been removed, so Pe has been suddenly 0. So if Pe is 0, input power is still 60 megawatt. It will not suddenly change. Mechanically, I will not change my low input suddenly. So there is some acceleration. What is that acceleration? It is 60 megawatt upon M. Okay. So let's calculate M in terms of mega and degrees. Let's make this in degrees, because if alpha is in degrees, then this also can be in degrees. Okay, everything is in electrical degrees. So we already have computed what is H. H is 4. So H is 4 and G is 250. 250 into 4. Now remember, this was in MVA, right? So this is automatically converted into mega. So it is, the numerator is already in mega. I don't need to worry about it. Now denominator, this pi is in radians, but I want in degrees. I want alpha to be in degrees. So this m should also be in degrees. So this will be 180 degree. Okay, this is the only change that we'll do. This is the only change that we will do. If you make this m in degrees, right, this will go in the numerator, and your alpha also will be in degrees. If you want alpha in radian, electrical radian, you will not convert this pi into 180, you will keep it as pi only. All this has been taught in the full course. So 180, and it is present on YouTube. It's not like it is paid or something, it is present on YouTube. You can watch it. 180 into 50. So this would be 250 into 4 divided by 50 into 180. So 0.1111. This is your angular acceleration, 0.1111. What is the unit? It is electrical degrees. Unit would be electrical degrees per second square. Okay, because frequency has a unit of 1 by second, and this is degrees. So electrical degrees per second square, and this already had a unit of per second. And remember, mega is there, right? M has also a unit. Actually, sorry. Okay, there will be also this unit, right? Sorry, the unit, I have told you the opposite unit actually. This unit will be second square electrical degrees and mega. 1 second. Megawatt second square per electrical degree. That is the unit of M. Okay. Now, if you replace here, the numerator is already in megawatt, right? And this is already also has a megawatt. So mega will be cancelled. This electrical degree will go on the top, and second square will be in the bottom only, right? So I hope you know how to play with units. So your alpha would be 60 divided by 1.11. So not 1.11, sorry, 0.11, which is actually quite large. Okay. Okay, let me just compute this. So 60 divided by 0.1111, which is coming out to be 540. Coming out to be 540. What is the unit? Electrical degrees per second square. So now you can simply solve it. So this will be equals to delta naught. What was the initial angle? Initial angle was 10 degrees. Right, so initially it had 10 degrees plus half alpha, that is 540 into t square. Now they have asked me after 5 cycles. 5 cycles of what? 5 cycles of input. So what happens, like what is the duration of one cycle? That can be computed from the time period. So time period is 1 by f, that is 1 by 20, sorry, 1 by 50, that is nothing but 100 millisecond, or 0.1, sorry, that is 0.2, hold on a second, that is 20 milliseconds, right? That is what my one time period is, 1 by 50. So they are asking me after 5 cycles, so I will have to multiply 5 time periods, so it will be 100 milliseconds. So they are asking me what is the delta, the power angle after 100 milliseconds, that is basically equals to 0.1 second. So this will be 0.1 second, the time duration, that is what they're asking, whole squared. So now I am ready for the final solution. So this will be actually 5.4 divided by 2 plus 10, that is 12.7 electrical degrees. This is your delta of t after 5 cycles, and this is your answer. Okay, so let's solve the next question. So this is the next question. So a bus 1 with voltage magnitude V1 is 1.1 pu. Okay, this has a 1.1 pu voltage magnitude. And it is sending reactive power Q12 from here to here towards bus 2, whose voltage magnitude is 1 pu. So this has a voltage magnitude of 1 pu. Okay, through a lossless transmission line. So there is no lossless. It seems like it will be a purely inductive reactance. Okay, and we know if the line is purely inductive, then for reactive power to go from bus 1 to bus 2, there must be a voltage difference. That's all. Okay, keeping the voltage at bus 2 fixed at 1 pu, the magnitude of the bus 1 voltage is changed so that the reactive power Q12 sent from bus 1 is increased by 20%. So the reactive power sent from bus 1 to 2 has increased by 20%. That means it is 21.2 of the old reactive power. What will happen? That means I will have to increase my voltage magnitude here. Okay, so yeah, real power flow through the line under both. So what happens? So that the reactive power Q12 sent from bus 1 is increased by 20%. The real power flow under both the conditions is 0. That means if the real power flow under the both the conditions is 0, and for a, so this I have taught again, it is present in the full course, so I will not be able to explain everything. It is there on YouTube. Go to the playlist. Okay, how does the power flow happens? Everything is covered. Every single thing is covered. So what happens? For active power to flow, there must be an angular difference between the bus 1 and bus 2 if it is a purely inductive line or purely capacitive line. So if they're telling me that for both the cases there is no real power flow or active power flow, that means this angle, if I assume this angle to be, if I assume this voltage to be 1.1 angle 0, then this voltage also has to be in 1.1 angle 0 only. So if only reactive power is flowing, that means the magnitude must be different, and that is what we are observing. Right? Magnitude is different. Okay. Now what are they asking? The new value of the voltage magnitude V1 would be at bus 1. So basically there is a very basic thing, this I have taught, that for reactive power to flow, it solely depends on the, so it solely is proportional to delta V. Okay, reactive power flow is solely depends on the delta V, basically difference of the magnitudes of the voltage. So it will be equals to, this will be equals to Q12 will be proportional to magnitude of V1 minus magnitude of V2. Correct? Now we can take the ratio, right? So Q12 upon Q12 dash, this will be equals to magnitude of V1 minus magnitude of V2 upon magnitude of V1 minus magnitude of V2, all this will be dash. Now I want to give a very huge disclaimer here that this will always not be valid. It is valid only if my line is purely inductive or capacitive. Okay, be careful, this will not always be valid. This thing will not always be valid. This will be valid when my line is purely inductive or capacitive, and in most cases your line will be purely inductive or capacitive. So be very careful. I have discussed about the places where it will not work in the full course. This is out of scope of this particular video. So yeah, magnitude of V1, magnitude of V2. So now I know what is Q12. Q12 is Q12 only. Q12 dash is 1.2 of Q12, that is discussed. So 1.2 of Q12, that will be equals to magnitude of V1 is 1.1, magnitude of V2 is 1, magnitude of V1 dash I don't know, that is what I have to compute, and magnitude of V2 dash, they have told me that they are not changing. Magnitude of V2 is kept constant, right? Voltage, keeping the voltage at bus 2 fixed, so this is 1 only. Okay, so from here I can get, so magnitude of V1 minus 1 equals to 0.1 into 1.2 into this, so this will be 0.12. So magnitude of V1 would be equals to 1.12. Now there is a derivation as well, you can derive it. So basically what happens, the expression for your reactive power flow. So you know the expression for active power flow, right? You know the expression for active power flow. What is the expression for a purely inductive line? it is PE is equals to VS VR by X sin delta for a purely reactive load, purely reactive line. Okay, and similarly the reactive power transfer is actually equals to V1 uh, V1 by X, or let's say it is the sending end voltage into sending end voltage minus receiving end voltage cos of delta. This is the formula actually. And roughly what happens if there is no active, so this formula does work only when your cos delta is 1. So only when delta is 0. So yeah, another condition was there, only when there is no active power flow between the two lines, then only this thing will be valid. So in this case there was no active power flow, that's why we could have used this, right? Otherwise you can remember this formula, this will anyways be very helpful. So make sure you are remembering this formula. Okay, so in this case it is simply 0. So simply we can take the ratio now and you can compute what will be your VR. Okay, because your delta will be 0 because your active power is 0. Okay, active power is 0. Right, let's solve the next question. Let's solve the next question. Next question is this. In the figure shown, self impedance of the transmission lines are 1.5J pu each. Okay, and okay, so this is the answer basically, 1.12 pu. This is the answer. You can solve from here as well, you will get the same answer. Let's solve this question. In the figure shown, the self impedance of the two transmission lines are 1.5J. So the self impedance is 1.5J, 1.5J. Okay, 1.5J, 1.5J. And Zm is this, which is the mutual impedance. The bus voltage is shown as below. The maximum steady state real power that can be transferred in PU from bus 1 to bus 2. Okay, what is the maximum voltage that can be transformed? Okay, so we have never discussed when if two coils are in parallel, what will be their equivalent reactance. So this thing actually, unfortunately, what happens? So if I see from both the coils, if I assume a current direction, right, this is the current direction, from both the coils current is leaving the dot. If both the coils current is leaving the dot, then the effect of mutual inductance would be same in both the coils, which would be opposing, if I am not wrong, right? Because it is leaving both the coils, so this would be opposing. So this will be L1 minus M, L2 minus M. Okay, so let's derive basically. So let's derive the expression. If I have two coils in parallel, okay, and we will derive it for both cases. Let's say for both the inductors, right, of course current direction will be this, and for both of them the current will leave the dot, correct? Let's assume that this is I1, let's assume this is I2. So what is it? It is the it is the additive connection. It is not the opposing connection, this is the additive connection, right? This is actually called as the parallel aiding connection. And trust me, no one will derive all these things, right? No one will tell you all these things. Okay, because next day a bit of difference will come in the question and you will not be able to solve it if you don't understand the derivation here. Okay, so this is parallel aiding connection. In parallel aiding connection, what happens? The flux increases due to the mutual inductance, overall flux will increase. So essentially they are connected in parallel, right? Just give me 1 second. They are connected in parallel. So what will be the voltage developed? V1, it will be equals to L1 di1 dt, and overall voltage will increase, right, because overall flux has increased, plus because it is additive, so it will be plus M because there is some mutual inductance into di2 upon dt. This is the additional voltage due to the flux developed by the mutual inductance, and it will be additive. What about V2? V2 would be equals to L2 di2 dt, and this also will be plus M di1 over dt. Now if they are in parallel, these two voltages will be same. If these two voltages are same, I can equate these two, right? So it will be actually L1 plus L2 into di1. Sorry, I cannot do L1 plus L2. I can do L1 plus M into di1 dt plus L2 plus M. Sorry, hold on. I'm equal. These two will be equal, right? So basically, what will happen? L1. So let me copy this. This will be equals to this. Correct. So this will be here we can say that L1 minus M into di1 by dt is equals to L2 minus M into di2 over dt. Okay, that is what we got, right? Now if I convert this into a single equivalent inductance, what will be the value of that? So what will be the voltage developed? V, that will be equals to L equivalent. So your V will be equals to L equivalent into di over dt, correct? And what is your I? Basically your I is this current, right? I is this current. This is the I current, which is divided into I1 plus I2. So I is equals to I1 plus I2. Okay. So yeah, just give me 1 second. I'm just checking a message. Give me 1 second. Okay. So now what can we do? What can be done here? So I want to convert this into this format, right? Okay. So what is my V basically? V is this value. The V is equals to V1 and V2. Both, all three are same, right? Everything is same here. V is equals to V1 and V2. So everything is same. So I can write okay, just give me 1 second. So I want to write in terms of I1 by I2, right? So what is my di1? What is my di2 over dt? This would be equals to L1 minus M by L2 minus M into di1 over dt. Okay, so what is V1? V1 is same as V, right? Because it is in parallel. V1 is same as V. So that will be equals to L equivalent into di by dt. L equivalent into di by dt. That is my V. That is equals to V1 because everything is in parallel. That is equals to L1 into di1 by dt. L1 into di1 by dt plus this value, right? M into this, because di2 by dt is this. That is just derived. That is this value. Now what I'll do? So I know I is equals to I1 plus I2. So di1 by dt will be equals to di by dt will be equals to I1 by dt plus di2 by dt. So your L equivalent, this will be di1 by dt plus di2 by dt, and di2 by dt is this value only, right? So I will replace it. So the derivation is typical, that's why no one derives it, okay, and no one even tells you the final result as well. So this will be plus this will be equals to L1 into di1 by dt plus M plus this value only, right? This will not change. So okay, di1 by dt is already here. L1 plus whatever is this value, into di1 by dt. So this and this will be cancelled, right? di1 by dt can be cancelled. Ultimately, I can get the value of L equivalent. So L equivalent would be equals to L1. This will be at the numerator, right? And at the denominator, I will have 1 plus this value. So all I have done is just taken common di1 by dt, right? So if I solve for this, it seems bit difficult, but it is not, trust me. So this will be L1 L2 minus m, right? Minus m into L1, and already here I have plus m into L1, that will be cancelled. Only I will have L1 L2 minus m square divided by L1 plus L2 minus 2m, right? This is correct. Plus minus, yeah. This is for series additive. So not series, this is for parallel adding. If let's say, if I now, that is your homework task. Your homework task is to derive the expression for L equivalent for parallel opposing connection. Parallel opposing meaning one dot will be here, another dot will be at the other side. Basically, for one of the inductors, current leaves the dot, for the other current enters the dot. If it is parallel opposing, I will directly write the formula, but you can derive it. Okay, you can come to the final expression. Your final expression would be the same thing, right? The numerator will not change, the denominator will change. It will become plus, that's all. Now how do you remember it? So how I can remember, right, is that first you think of it that your numerator will be same. Okay, L1 L2 minus m square, this will be same. What about the denominator? Whether it will be L1 L2 minus 2m or plus 2m. So if you remember, this expression is same as series opposing, and this is same as series additive, right? What is happening if I write here minus 2m? That means the numerator is reducing. That means your that means your denominator is reducing. That means your overall L equivalent is increasing. That means when the connection is parallel aiding, I will get more flux. That means the inductive nature will be more. That's why your L equivalent will be more. That is the intuitive explanation of this. And in parallel opposing, what happens? Your denominator, right, is higher because I have addition plus 2m. So denominator increases, so your overall L equivalent reduces. If your L equivalent reduces, what will happen? If your L equivalent reduces, that means the flux is reducing, that's why it has lesser inductive characteristics. I hope you got the point. So that is what we mean. That is the intuitive explanation of this formula. So if you have enjoyed this part, hit the like and comment down below. Like, okay, because no one will explain you all this intuitive analysis and all these things. They will just directly tell you the formula, that's all. So but here there is a difference. We try to explain each and everything. I'm just give me 1 second, just checking something. Yeah, so here we will try to give explanation of each and everything. Okay, so yeah, let's try to solve it. Yeah, let's actually try to solve our actual questions. This is the actual line inductance. So basically what will happen now, what will happen to your reactance? So this is your L equivalent, right? If I know L equivalent, your overall reactance will be omega into L equivalent. That will be your overall reactance. So I can compute that. So let's first compute our L equivalent. So let's come to the solution. What is our L equivalent? In our case, it is parallel aiding. So our formula will be L1 L2 minus m. Now the difference is, if you see, everything is given in terms of reactance, it is not given in terms of inductance. So what you can do, you can also write this expression in terms of reactance as well, right? So if I multiply omega, I will get the reactance. So let me multiply the omega here. If I multiply omega, this will be omega L1 into minus omega m square. Okay, the omega has been multiplied with the whole of the equation, right, to the numerator. But I see still the denominator is still in inductance format. So let me multiply by omega again in the numerator and in the denominator. So what will happen? This will be omega square. So I can write omega into L1, omega into L2 minus omega into m whole square divided by omega into L1 plus omega into L2 plus 2 omega into m. So ultimately, right, everything can be converted in terms of reactance. It does not matter. So all of these are reactants of the coil 1, coil 2, like the mutual reactants, and I hope you get the point. So what is the reactance of the coil 1 and coil 2? They are same, that is plus 1.J5, that is this coil, right? And what is the mutual reactance? It is J0.5. So your answer would be, obviously J is there, so I'm not considering the J now, right now. J I will consider at the end. We don't even need to consider in our case. So this will be equals to 1.5 into 1.5 minus 0.6 whole square upon 1.5 plus 1.5 plus 2 into 0.6. Okay. So yeah, what is happening is that this would be 2.25 minus, so let me compute this value. So this is my equivalent, x equivalent. Why am I interested in this? Because ultimately I will have to compute the maximum power transferred, and the maximum power transferred, right? So your electrical power transferred, if it is a purely inductive link, it will be magnitude of V by x, the inductive link, into the sine delta, right? And the maximum power transferred would be, when delta is basically 90, that is equals to magnitude of V by x, right? So ultimately I need this value actually. So magnitude of V and magnitude of V are unknown, but I need the bottom part. So this is actually 1 minute question, but I have to derive all this. That's why it is taking me so much longer. So yeah, so your answer would be, so that's why I need to calculate x equivalent. That was the purpose basically. I did not explain you at the starting. That was the purpose, to calculate x equivalent. So this will be 1.5 whole square minus 0.6 whole square divided by 3 plus 1.2. So that is 0.45. So your overall reactance is 0.45. Okay, that is what your, okay. Hold on, so sorry, this will not be plus, right? This will be minus. Why? Because it is series aiding, and series aiding, obviously it will be increasing, right? I am telling you the intuition, I'm writing the wrong formula. Okay, very bad. So hold on a second, into 4.2 divided by, so this will be 1.05. So your x equivalent is 1.05. So your P max is magnitude of E into magnitude of V by 1.05, right? So 1.05, so approximately it will be 1. So approximately it will be option A. So the closest answer is option A. So we will choose option A. Okay, actually exactly it will be, okay, sorry, this point J 0.5, right? What am I doing? That's what I'm thinking. Why am I making this mistake? So this will be actually, okay, sorry. This will be 0.5. I think it will be exactly, it should be coming out to be exactly 1, right? So this will be 1.5 whole square minus 0.25 divided by 3 minus 1. Yeah, it is exactly coming out to be 1. Sorry, it is exactly coming out to be 1, right? So your answer would be this by 1. So your P max is magnitude of E into magnitude of V. That is your answer. Option A is your answer for the question. Very good question, very beautiful question, right? So I think this is the last question from stability. No, there are more questions. Actually, they have asked a lot of questions from stability. So this is the next question. A 20 MVA 11.2 kilovolt 4 pole has inertia constant. This inertia constant is what? My H. It is written in seconds, right? The unit is in seconds. So 15 megajoule per MVA, that is in seconds. If the input and the output powers of the alternator, so input power of the alternator, that is the mechanical power input PM to the alternator, is 15 megawatt, and the output power, electrical power output of the alternator is 10 megawatt. The angular acceleration in mechanical degrees would be, so they are asking me angular acceleration alpha in mechanical degrees. Okay, very careful in mechanical degrees. So we have to be very careful here, right? So what is how do I calculate alpha? Alpha would be equals to the, so we know this equation, right? Pm minus P is equals to m alpha. This equation we know. Pm minus P is equals to m alpha. Okay, so Pm is 15, P is 10, so this will be 5 megawatt by m, that is equals to alpha. Now what is this m? M is actually equals to gh by pi f. Now remember, if I write there pi, right, then this unit is actually, so if I put here pi, then your angular acceleration unit will be coming out to be in electrical radian per second square. But I don't want that. I want this to be in mechanical radian or mechanical degrees. So if I write this as gh by 180 degree into f, so your unit will be electrical degrees per second square. But I don't want that. What they do they want? They want this to be in mechanical degrees. So if they want this to be in mechanical degrees, so if, what do we know? We know theta electrical is equals to p by p by 2 of theta mechanical. So what is 180 degree in mechanical degrees? So if my theta is 180 degrees in electrical, what will be mechanical? So how many poles I have? 4 poles. It's a 4 pole machine. So this will be 4 by 2 into theta m. So your theta m, right, will be 90 degrees mechanical. So instead of writing here 180 electrical, I can write mechanical. And if I write here mechanical degree, then this, right, then this angular acceleration alpha would be mechanical degree per second square. So that's the beauty of this question. You need to understand how to do the unit conversion. Okay, because 180 degree electrical is same as 90 degree mechanical. So you have to write your answer in mechanical. So you will convert this 180 into 90. Why? Because this is the relation between electrical angle and mechanical angle. So now I will calculate the value of m. So what will be m? Everything else is fine. Other things are in unit. So it is G. G is 20 MVA. Generator rating 20 MVA into H. H is 15. H is 15. Okay. H is 15. And H is 15 divided by 90 degree into F. F is frequency, that will not change, it will be 50 only because it gives the unit of 1 by S, that is not a problem. So from this I can actually, so yeah, I can directly put this in this equation, right? This is already in mega and already G into H, right? This will also be in mega only because G has a unit of mega. So mega will be cancelled. So you should be very comfortable with playing with units. Okay, so alpha will be equals to 5 upon 20 upon 15, right? So this will be 300 into 90 into 50. So this will be 5 by 6 into 90. So alpha would be equals to 5 by 6 into 90. So 6, right? 330 by 2, 30 by 2, 15. 15 into 5 would be 75 mechanical degree per 75 mechanical degree per second square. Okay, that's the beauty of this question. You should be able to tell how to convert this. Actually, what you could have done is simply, first of all, so what you could have done is not do the conversion here. Okay, you could have written your answer 180f and you could have calculated your alpha. Alpha would have came in some electrical degree per second square, and then you can do this conversion. Then you, if it is in electrical degree, then you will say in mechanical I will just have to multiply p by 2. So in electrical it will come out to be 150 electrical degree per second square, and in mechanical you will just have to halve it. That's the thing basically. That's how you solve it. Okay. Yeah, let's solve the next question. This is the next question, right? A single line diagram of a lossless system is shown in the figure. Okay, the system is operating at steady state at equilibrium, power output being P max sine delta, and delta is the total load angle, uh, and the mechanical power input is 0.5 P max. So at steady state initially the mechanical power input Pm naught is 0.5 P max, and the electrical power output in the case 1 is P max sine delta, but delta is the power angle or the load angle. A fault occurs at line 2 such that the power output of the generator is less than 0.5 P max. So a fault is occurred at line 2, and due to which the power output becomes bit less than the actual previous power output, because the line reactance obviously will remove. If I remove this, right, if I remove this line, the overall reactance will reduce. That will increase, sorry, that will reduce the overall electrical power output. Okay, that is what we have seen in the one of the previous questions, correct? So this will be some P max to sine delta. After the fault is cleared by opening the line 2. Okay, so this was the case when the line 2 was still intact, and because there is a fault, what used to happen is there is a short circuit, and due to the short circuit what will happen, the overall uh, reactance will reduce by a large amount. Then if they clear it, what do they mean by clearing? So there will be some circuit breakers that are connected that will open the circuit, that will open the faulted part, so that only line 1 is intact, line 2 is not there. Okay, we will then service the line 2 later on. So after opening the line 2, the power output of the generator is P max by root 2 sine delta. So basically it is the case 3. After the fault has been cleared, the power output of the generator is P max 3, that is equals to P max by root 2 sine delta. If the critical clearing angle is pi by 2, so I hope you have studied what do they mean by critical clearing angle. It is a critical angle before which we need to clear the fault, otherwise the generator will never regain synchronism. Okay, this is the definition. It is pi by 2. If you want to study, go into the YouTube playlist, everything has been discussed there. The accelerating area on the power angle curve would be, what is the accelerating area? So what is happening? So if I draw the electrical power output with respect to delta, so this is the curve 1. Okay, let me draw it properly now. This time I will draw it properly. Okay, so this is the curve 1. In the curve 2, because there is a fault, the overall power will reduce. Overall power would reduce. Okay, let me color this curve. And in the curve 3, what will happen, as the fault is clear, again the power will be increased, but not to the previous level, but it will be increased. I mean, the power output will be, electrical power output characteristics will increase, but not obviously to the previous level. Right, and this is my initial PM naught. Okay, so I will not explain everything in the graph here. I will only explain whatever is the important part for solving the question. If you want to understand everything what is happening in the graph, you will have to watch the full course. You will have to watch the YouTube video. Okay, not possible to explain everything here. So this is the mechanical power, that is 0.5 Pmax. Let me write this as 0.5 pm, and this is the first graph, right? That is pm only, and this is the second graph where I don't know what is the peak value. I don't know it. So this will be PM2 basically. The peak value of the second case, I think it is written as PM2. Yeah, this is written as PMax2, and in the third case, the peak value is Pmax by root 2, and it will be certainly higher than the first case. Okay, it will be certainly higher than the first case, right? Yes. Sorry, it will not be higher. It will be lower. Right? Pmax2 would be lower. This will be higher. I think. Yeah, just one thing. Because after the fault will be cleared, there will be some deaccelerating area. I'm sorry. So yes. Yeah. So I'm lying here. My curve is here, and okay, but it has to cross it somewhere, right? Because I'm lying here, there will be some mechanical power output will be still higher than the electrical power. Sorry. Oh no, sorry. The previous graph was correct only, right? What I'm doing. So mechanical power would be much lower. And I will be lying somewhere here. I will explain. Just give me 1 second. Okay. So yeah, this is the scenario, because they have told us, right? What they have told us, that during this fault, when the fault occurs at line 2, the power output of the generator is at a fault occurs at line 2 such that the power output of the generator is less than 0.5 Pmax during the fault. So power output of the generator will be less than 0.5 Pmax, right? So if it is less, so this top will be lying somewhere in the bottom. Okay, so this is the second graph. This is my 0.5 Pmax, and power output will be somewhat less, so I will be lying somewhere here. Okay, and during fault, the power output of the generator is very low, because fault is a low power phenomena, high current, low power phenomena. So electrical power output of the generator will be very low. Okay, so this is the case 1 when everything was in steady state. This is the case 2. This is the case 3. Okay, so yeah, so yeah, now if I solve it, they are asking me what is the deaccelerating area. When will the deaccelerating area will be? So sorry, they are asking me what is the area accelerating area. What do they mean by accelerating area? So basically, right, so this is the point. Let's say this is the intersection between the curve 1 and my mechanical power input, which is constant throughout. So here is the point of intersection, first intersection, right? That is my delta naught. Okay, this is my delta naught. So what happens essentially is that after this delta naught, then some fault occurs. So I'm at graph 2, my electrical power output will be this, and fault is cleared here, exactly at pi by 2. That is delta CR, that is equals to pi by 2. And after clearing of the fault, we follow the curve 3, the electrical power output, because line 2 has been totally removed. So what is happening is, then again it will regain back to its steady state. This is the steady state point, right, for the curve 3, wherever there is some intersection. So what will happen, this area, so what area are they talking about? So if I compute what is my accelerating power, that is responsible for acceleration of the rotor, right, it is equals to Pm minus P. Pm minus P. Okay, so it is equals to Pm minus P, right, it is equals to Pm minus P. Now what is happening in the, if you see, when the fault occurs, your Pm is here and your Pe is this, right? So Pm minus Pe is essentially this, which is negative, because sorry, which is positive actually, which is positive, right? If it is positive, what is Pm minus Pe? That is equals to m alpha. So your rotor is actually accelerating. So this is what they mean. So during this whole period till the point fault is cleared, your rotor or motor, sorry, your generator is always accelerating. If it is accelerating, what will happen? Basically, your rotor angle will increase, keep on increasing, right? Now they just want what is this accelerating area? How do I compute this accelerating area? Now we know if the critical clearing angle is this, we know that what is the equal area criterion? Equal area criterion is accelerating area is equals to deaccelerating area. Okay, if delta is equals to delta CR, right? If the fault is cleared, then always this will be followed. Accelerating area will be equals to deaccelerating area at critical condition when my delta is equals to delta CR. Correct? So if they are asking me accelerating area, it is actually a bit difficult to calculate. Why? Because I know my Pm. Pm is 0.5 Pmax. This is what I know. Pm is 0.5 Pmax. But I certainly don't know what is my Pe, because during fault condition, they have told me it is some unknown Pmax 2. It is something else. I don't know. It is less, but I don't know. So let me compute the deaccelerating area. What is the deaccelerating area? The deaccelerating area would be this. Okay, I will not go through each and every point here, but the deaccelerating area would be this. Why? Because now as soon as the fault is cleared, my electrical power output is this. At the same rotor angle, I will generate higher electrical power output, but mechanical input is still same. So now this is negative, that's why the rotor angle will reduce. So there will be deacceleration. Okay, so yeah, I will not go through everything, but I can compute the deaccelerating area. Why? Because I know what is my Pm naught. So I know what is my, I know what is my Pm naught. I know what is my what is my PE3. So it becomes much simpler, correct? Yes. Okay. So let me compute this thing. Let me just give me just 1 second. So the system is operating in steady state with power output being P max and delta delta and mechanical power input is this much. Okay. The accelerating area on the power curve is dash times P max. Okay. So they are very small. Let me first compute the accelerating area, then I will discuss. So show your accelerating area is equal to deaccelerating area for equal area criterion. So what is my deaccelerating area? It will be from delta CR, because this point onwards, whenever the fault is cleared, the rotor will deaccelerate. Delta CR till my stable point, right? Steady state point. What is the stable point? This will be delta 1. So what is delta 1? Delta 1 would be when this 0.5 pm intersects with this curve. So when 0.5 pm or P max is equals to 0.5 P max, 0.5 P max is equals to 1 by root 2 P max sine delta 1, right? Okay. So that's all. Okay. P max, 0.5 P max is equals to 1 by root 2 P max sine delta 1. Cool. Yeah, now you can solve it basically, because this follows the third curve, and in the third curve my PE3 is this value, that's why. So your delta 1 from this, right, if I compute, this will be 0.5 into root 2, hold on, 0.5 into root 2, that is 1 by root 2. So your delta 1 actually is exactly 45 degrees. Okay. So we'll start from, so we'll integrate from delta CR to, so this would be 45, right? Now here we have just made a slight mistake here, small mistake. What is that mistake? So basically, yeah, this is the area, but this is not the area that I was referring to. I was referring to this area. Okay. Why? Because let's say we cleared the fault here. So till this point, what was happening? There was some acceleration. The rotor speed was increasing. Alpha was positive. So my omega r was increasing. Omega s is always constant. It is dependent on the frequency. So once I reach this point, right, still my omega r is greater than omega s, and if my rotor speed is greater than omega s, so if you draw the phasor, so this is your omega r, this is your omega s. So if your omega r is rotating at a higher speed, this angle delta will not be constant. This angle delta also will still increase because omega r is greater than omega s. So actually we will still go on the right hand side. Every concept, whatever I am discussing, if you are not able to understand, you will have to go and watch the theory. Unfortunately, I will not be able to cover everything here. So what happens, this angle will keep on increasing, but this point what is happening, there is some deacceleration. As I mentioned, your PE is greater than PM, so there will be some deacceleration. So what will happen, your omega r, although your delta is increasing, but your omega r is reducing. Okay. Why? Let's assume a very basic example. Let's say our omega s is 1500 radian per second or 100 radian per second. Now due to acceleration, previously our omega s went from, because here it was at steady state, it was also at 100 radian per second, it was at steady state, but due to acceleration it reached 150 radian per second. Now if it reached 150 radian per second at this particular point, if I suddenly clear the fault, it's not like delta will not increase, delta will increase. Still my rotor speed is 150 radian per second. So still this will rotate at a much faster rate. So delta will increase. If delta increases, I will still move on the right hand side. if I still move on the right hand side, till what point I will move? If you clear the fault at critical clearing angle, I will move till the point of pi minus delta 1, where delta 1 is the steady state position of the curve 3. So all this has been derived in the course there. I will not be able to explain everything. So actually this is the first rotor swing. Okay, first rotor swing, and in the first rotor swing, the overall area should be 0. Overall accelerating area should be equals to 0. So if the overall accelerating area is equals to 0, then again this will keep on happening, because there will be some rotor swings. This is the first rotor swing, then again the rotor will swing, and slowly at steady state it will reach here, that is certain. At steady state it will reach here, that is certain, but that will take some time. But the first rotor swing, the accelerating area should be equals to deaccelerating area. That is my equal area criteria. So actually I should continue my integration from delta CR to pi minus delta 1, and delta 1 is 45. That is, I will integrate PA, and PA is what? PA is PM, PM is 0.5, 0.5 P max minus PE3. What is PE3? PE3 is this value, P max by root 2 sine delta into d delta. Okay, this should be equals to my accelerating area, this should be equals to my deaccelerating area. Okay, I'm talking about the magnitude only. Okay, cool. Yeah, so now we can solve it. So what is delta 1? Delta 1 is 45, so pi minus delta 1 would be 135 degrees, and delta CR is pi by 2, that is 90 degrees, right? And I can take P max common, minus 1 by root 2 sine delta d delta, and this will be equals to okay, this will be, so into P max is also there, right? And let's not write this in degrees, let's write this in radians only. So this will be pi minus pi by 4, that is 3 pi by 4. Because why? Because this is a constant number and we need to write in radians for this, that's why. And this will be pi by 2 basically. So let's solve this. This will be 1 by 2 into 3 pi by 4 minus pi by 2, that is pi by 4 only. Then this will be actually plus 1 by root 2 cos of delta. I hope we can perform the integration, right? 3 pi by 4 and pi by 4 into P max, right? So let me solve this particular thing. So this would be equals to 3 pi by 4. So this is pi by 3 pi by 4 minus pi by 2, that is nothing but pi by 4 only. So this will be pi by 8. Okay, pi by 4 into 1 by 2 is pi by 8, plus, let me solve this. So this will be cos of 3 pi by, so 3 pi by 4 is 135, cos of 135 is negative. Okay, certainly it will be negative, divide by root, right? So this will be minus 0.5. Okay, which will come out to be negative. I'm just thinking, I hope I'm doing everything correctly, right? So this will be minus sine delta, I'm doing minus sine delta, PM minus P, right? Okay. So what happens is that the accelerating area plus deaccelerating area. So basically the accelerating area plus the deaccelerating area is equals to 0. So your one relation I made wrong, right? So the equal area criterion is the first swing, right? What is the first swing? I will start from delta naught and I will go till pi minus delta 1. That is the first swing. Integration of accelerating area d delta is equals to 0. That is what my equal area criterion is. Okay, this I can break down into two terms. One is the accelerating area, one is the deaccelerating area, right? This can be broken down into two terms, and the deaccelerating area will be negative of the accelerating area. Okay, so just a one slight change here. So if I want to calculate the accelerating area, I only have to calculate the negative of the deaccelerating area, and trust me, no one will explain all this, right? Because you will go and see the solution in the answers. There will be, basically you will see that it has simply uh, it simply has, they are writing this term first, then this term. You will not understand why they are doing it. Okay, you will not understand why you are doing it. I hope you got the point, right? So yeah, that's why this will be negative, and trust me, no one will explain you all these things. This will be negative, there will be a negative sign here. Okay, so this will be minus 0.5. If you still are not able to figure out what is happening, you unfortunately you will have to go back and watch our course videos. Okay, this will be minus 0.5. So this will be, if I solve this plus pi divided by 8 minus 0.1, so your accelerating area will be coming out to be 0.107 p max. So don't forget, it is p max. And what have they asked? They have asked me your accelerating area times p max, right? The accelerating area of the power triangle is something times p max, right? So what is the something? This 0.107 times p max. So your answer would be 0.107. Again, if you could not understand this question, you will have to, I'll just quickly give you a summary of what is happening. So initially there was no fault. So I was at this point, delta naught, right? Then some fault occurred, and fault is a low power phenomena. So the electrical power output will be much lower. So my generator will follow this curve now. And due to that, what happens? There is a difference between the mechanical power input and the power output. So certainly there will be some acceleration. Due to that, the rotor angle will increase. Now they're telling me that we're clearing the fault at critical clearing angle, that is delta CR. Critical clearing angle is pi by 2. If we clear the fault at critical clearing angle, then what happens is the then the fault then the motor will reach steady state. If we clear the fault less than the critical clearing angle, then the motor will certainly reach, sorry, not the motor, the generator will certainly reach steady state. Okay, and if you clear the fault at critical clearing angle, then the point at which the generator will stop its first swing will be pi minus delta 1, but delta 1 is the steady state angle after the fault has been cleared. So after the fault has been cleared, this is the steady state angle. So there are a lot of things here. Okay, so unfortunately you will have to revise a bit more. So now we know equal area criterion is that the integration of the accelerating area for the first swing will be 0, and with that we saw that we have a accelerating area, we have a deaccelerating area. Why deaccelerating? Because you see your PM graph input is lower than the output. So of course overall here area will be negative, and overall here area will be positive. Okay, so that's how you solve this. Accelerating area plus deaccelerating area will be equal to 0, and then you can solve this, you can get to the answer. This will be this, right? And remember, your accelerating area will be negative of deaccelerating area. Why? Due to this condition. You will see in many PYQs they will write this wrong. They will directly say accelerating area is equals to deaccelerating area. No, the magnitude of the accelerating area is equals to the magnitude of deaccelerating area. Of course, they cannot be exactly equal, because one is accelerating, so it will be positive, one is deaccelerating, it will be negative. But certainly magnitudes will be same, but signs will be opposite. So just be a little careful. Previously I was explaining a bit wrong there, because then I figured out, okay, this is what is happening, right? So let's solve the last question for GATE 2025 from stability. So in the system shown below, the generator was initially supplying power to the grid. The generator was initially supplying power to the grid, right? Now what they're telling me that there is a LLLG fault occurring at this point, very close to the circuit breaker 1. The reclose and restore, the circuit breakers open to isolate the line, the fault self clears, and the circuit breakers reclose and restore. Which one of the following diagrams best indicates the rotor accelerating and deaccelerating areas? So when the fault is occurring, right, circuit breaker will take some time to clear the fault. So we will follow, so our mechanical input power would be same, correct? But our electrical power output will be reduced, because fault is a low power phenomena, so it will consume less power. So it seems like this part is okay, this part is okay, and then as soon as the fault will be cleared, what will happen? Then again we will come back to our previous state. We will follow this curve. So again this will be my deaccelerating area. Is it correct? No, this is not properly correct, right? My deaccelerating area would be this, right? It does not include, so this is my PM naught, correct? So okay, let me reduce the width. So it only covers, so my deaccelerating area would be this thing as well, right? It did not include this part. So this also has to be included in the deaccelerating area. Here I see it includes this part, but it follows the second curve. No, it will not follow the second curve. Why it will not follow the second curve? Because, hold on a second. Okay, sorry. Hold on a second, right? So here they are telling me, just give me 1 second. Where is the fault getting cleared? So it seems like they are telling me that the fault, so I'm still following. So this part is anyways wrong. This thing is anyways wrong. So this is anyways not taking into consideration this particular area. So this is something else. So let's not look at this graph. Let's look at this graph. Okay. So if I look at this graph, I see my PM naught is this, right? That is the intersection. And initially, hold on a second. A triple LG fault occurs here. Okay. So one thing you have to note here, right? Here the fault was occurring where? The fault was occurring at line 2 after the transformer. So still there was some finite inductor, and your Pmax, right? It was not 0. It was less than 0.5 Pmax, but it was not 0. But here what they are telling me, that a temporary LLG fault is occurring very close to the circuit breaker 1, which is essentially at the bus 1. And if the bus 1 is faulted, that means this is grounded. And if this is grounded, that basically means the PE is what? EF Vt by XS sin delta. Vt itself is 0. So your PE is 0. So your fault, actually, when the fault occurs, your generator does not deliver any power at all. So actually these graphs seem correct because it is not delivering any power. So your PE is the line P equals to 0, right? P equals to 0. And your PM naught is still constant, right? It is, I'm still providing some input power. So still I will follow this. So still the accelerating area would be this. Okay. And then they tell me that after a certain time, what happens is the circuit breakers open to isolate the line. So after a certain time, the circuit breakers will open and isolate the line. Okay, they will isolate the line. Isolating basically means that they will open circuit this line. So then this fault will be gone and only this path will be present, and due to which there will be some finite electrical power output. So there will be some finite electrical power output after a certain stage, which I see at this point. Okay, let's name this point as point 1. So okay, let's name this point as point 1, where the fault occurred, and then at point 2 the circuit breaker isolates the bus from here. Hence if it isolates, so it will not, the electrical power output will not be same as the previous case, because now there are not two lines, there is only a single line. And if there is single line, the electrical power output will be reduced because the denominator will be increased, right? X reactance will be increased, because if two reactants are in parallel, it is x by 2. If one reactance is there, it is x. Okay, these things I hope makes sense. So now it is x, right? If let's say two reactants were there, this was x, this was x, right? Then overall reactance would be x by 2. But now what is happening, because I have isolated this particular line, so now only I have x. So your electrical power output is equals to EF Vt. Vt is still 1 V, because we have cleared the fault. Vt is still 1. We cleared this circuit breaker by x equivalent, right? So in the first case it is x by 2. So your PE is higher. In the second case it is x. So your PE is lower. That's why it will be lower. So in the second case your graph will always be lower. Okay. So at this point 2, the circuit breaker is isolated, and then after a certain point, what they're telling me, that the fault self clears and the circuit breakers reclose and restore the line. Again after this point 3, the fault, so the fault in the top line has been cleared. Has been cleared. Hence now we will follow this curve. Now we will follow this curve. This one, okay. Well, hold on a second. No, it will not. sorry, not this is not the point 3, right? This is not the point 3. Point 3 is actually this part. This is the point 3, because after this point the fault is actually totally cleared, and you see we are following only this graph. Okay, let's try to see the other graphs and see which one makes sense and not does not make sense, and we will eliminate the options. If I see, yes, this is my initial point, okay, and then they are telling me that at this point I isolate my line. If I'm isolating my line, right, so my PM naught is here, they're telling me that my PM naught is here, that is fine. This is my PM naught. If I'm isolating my line, okay, at this point, so then I will follow this curve. So yeah, this will be the area followed, and then after this point, right, I will clear the fault, right, I will clear the fault. This is the point 3. Point 3 is when I will clear the fault and I will follow the top graph. So I see I clear the fault, but suddenly the delta reduces and it goes to here. This is weird, right? No, this will not be possible. This will not be happening, because what is happening? So your delta will not suddenly change. It will not, basically at this point we cleared the fault, and you are saying that your delta will suddenly change, or you say that this is the point that you are clearing the fault, because here you see the area curve going from curve 2 to curve 1. Okay, so this seems not correct. Let's see this. So here we see that we have a fault. Here we isolate the line, correct, but this is something, so this is my PM naught, okay, this is my PM naught. Here we see that there is a fault, right, and at point 2 we are isolating the line 1, okay. What is happening? After isolating, we observe that we are following this curve, we are calculating this area. Is this correct? No, we will calculate this area, right, this curve, this area. We will not calculate the area with respect to this. You are saying this is some constant area. No, you're saying your mechanical, this graph essentially says that your mechanical input power has changed from this point to this point after clearing the fault. No, your input power has not changed, so this curve is wrong, okay. So essentially this is also wrong. I've already told you this is also wrong. So this is the correct one. How? So if we see from point 1 to point 2, input power is constant, your electrical power output is 0. So this is the area, accelerating power area, okay. And what about this part? Then what happens is, then we, at this point the line has been isolated, so from this point onwards I follow curve 2. If you see, I am following area of the curve 2, and then at this point onwards what is happening? Not actually exactly at this point, at this point, at this point my fault has been totally cleared, so then I am following this curve, the first curve, initial curve. So this is absolutely perfect, and this will be answer. This was actually a good question, so you will have to understand the graph, okay. So your figure 2 is the correct answer, okay, which totally indicates the rotor accelerating and decelerating area. So if you could not understand, please pause the video, try it again, otherwise you will have to go and watch the theory. With this we are done with stability. We'll now start with the other part, that is our load flow analysis. Let's begin with load flow analysis. So this is the first question. Consider a power system consisting of n number of buses. So I have a power system which has a total of n buses. Now it is categorized into a slack bus. So I hope you remember what is known in a slack bus. In slack bus, the magnitude of the voltage across the bus and the power angle delta is known to us. We have a PV bus, right? How many PV bus? They have not mentioned. Okay, only we have one slack bus. And of course, for a PV bus, the power and the voltage, magnitude of the voltage are known to us. And we have PQ bus. For a PQ bus, the power and the reactive power, the active power and the reactive power are known to us. Correct? Now, what is unknown? Now, sorry, not what. Let's read the question. Now, what they're telling us, that we have total NL number of PQ buses. Okay. NL number of PQ buses. So total number of PQ buses are NL. Okay. Now the balanced Newton-Raphson method is used to carry out load flow study in polar format. This, okay. So it is basic. It is the basic equation of Newton-Raphson method. That's all. Now it is broken down into submatrices. I will explain what are these submatrices. I will explain about this. All they are asking you is what is the dimension of M in the submatrix of the Jacobian matrix. How do you calculate that? So we know what is the dimension of Jacobian matrix. Jacobian matrix is a square matrix, certainly, and it is equals to, let me define a number nj. It will be equals to number of unknowns in number of buses in which voltage and power angle is unknown. Number of buses in which voltage, magnitude of the voltage and magnitude of voltage and delta are unknown. Okay, just writing this in rough, but I am just revising you. I am just helping you revise whatever you know, right? So your dimension of Jacobian matrix will be nj cross nj. I hope you know, right? So basically, how many unknowns I have in magnitude of V and how many unknowns I have in magnitude of delta. That's all. I hope you remember this part. Now, let's come back to the submatrix. So this I have taught in the full course, so I will not go through everything, but few places you will see that they will directly say, okay, as the row is matching with Q, so you will write the dimension of Q, how many total number of known Q I have, and then you will write the dimension of unknown V, how many total unknown V I have, because whatever is written in the left, right, it is generally the known parameter, and the right hand side parameter are the unknown parameter, right? I am finding out the value of delta and delta V, correct? So, but don't need to worry about that. There is a simple way to understand this. So let me write the equation first. So we write your delta P, delta Q equals to HSMR, okay, HS HSMR into delta delta V. Okay. Now, what happens is if I equate this row, right, then I see, so your M, right, M will be what? How can I understand what will be your M? So what happens, your delta Q, if I equate the bottom row, delta Q would be equals to M into delta del plus del delta plus R into del V. So what happens is, if I need, so I need to multiply M with del delta and I need to get the unit of delta Q. How will that happen? So your M, right, actually is equals to delta Q by delta del delta. I hope this makes sense, right? So this like intuitively I'm saying you, how can you remember it? So M will be delta Q upon del delta. So this and this will be cancelled and this will be here, correct? Hence the units will be same. So you can identify what will be your M with matching the units. That's all. Okay. Now, the simple thing what you need to do is, your Q is the number of known and your delta is the unknown thing, right? Because you see delta and V, while doing this Newton-Raphson analysis, we ultimately identify the voltage and angle at each the buses. That is our main task, because we know how much power each load is consuming, correct? Our task is to calculate the voltage and power angle, correct? So this will be number of unknowns in delta, okay, because always what happens, this is delta q, this is a function, right? So when we differentiate, when you say dy upon dx, so what happens, we say y is the known function, correct? Y is a known function that depends on x, and x is unknown, x can take any value. That's how you can remember it. I'm just telling you how can you remember it intuitively. So ultimately your m also will have a dimension where its x, right, basically number of rows will be dependent on the number of known q buses, and its number of columns will be dependent on the number of unknown delta buses, okay? So how many number of q buses are present, how many number of q buses are present, right? So number of q buses, how many I have? So if I compute, I need to compute how many number of known q buses I have. How many number of known q buses I have? How many number of known q buses I have? NL, correct? NL. So simply the number of rows of M matrix will be NL actually, and I see NL is present in option A and in option C. So either option A and C can be my answers. And what is in the number of columns? Number of columns would be the number of unknowns in delta. So how many unknown I have in delta? Certainly I have PQ, NL number of PQ buses, they have delta as unknown. Certainly I have PV buses, they have also unknown, right? So okay, let me just write few stuff. So how many PV buses I have? So what is the total number of PV buses? So total number of buses is N, then I have one slack bus, then I have NL load buses. Other than this, all other buses are PV. So I have to calculate how many delta are unknown to me, right? How many delta are unknown to me? So NL of certainly delta unknown, NL buses are unknown because it is load bus. Certainly PV buses also has delta as unknown. So it will be NL plus N minus NL. So this is the number of PV buses. So certainly your total number of unknowns in delta would be N minus 1. So you have N minus 1 total number of unknowns in delta. So this will be N minus 1. So your number of columns will be N minus 1, that is present in option A. Okay. So option A is correct, option C is incorrect. So that's how you solve this question. Yeah, I do agree. Few things you have to remember here, but intuitively if you solve, just like how I told you, you will be able to remember most of the things. Okay, let's solve this question now. So a 3-bus system is shown. Consider generators are ideal voltage sources. Okay, if they're ideal voltage sources, you can actually convert them into ideal current sources. That's the purpose basically. Y bus matrix correspond to bus 1, 2 and 3. So the Y bus network would be, what is the Y bus network? Very simple question. So there is a property of Y bus network, that Y bus network is always symmetrical. Okay, and I see it is always symmetrical about the diagonal, and for all of these matrices it is always symmetrical. Now another property is that, so what is this bus? Okay, there is no bus, right? This is just a connection to ground. Okay, this is connection to 0th bus. Okay, that is interesting. This bus 2 and this, okay, we will need to convert this, right? We will need to convert this into what? We will need to convert this into, so this is currently in star, so we will need to convert this into delta. Yes, because there must be connection between delta, so otherwise you will not be able to solve it. So let us convert this into delta. So currently this is in star, so if I have to convert from star to delta, I will not explain you the formula. Okay, I will use my trick. Whatever tricks you know to remember the formula, you can use it. So I have to convert from star to delta. So star to delta is nothing but summation, and all of the values are same. So basically it will be 3j, that's all. Star to delta is summation. What is the formula? It is basically z1 plus z2 plus z1 z2 upon z3. This is the formula for star to delta. So it will be z1 plus z2, that is jj, and j into j divided by j, that is j itself. So ultimately this network can be converted into this value. So I can directly convert this ideal voltage source into a ideal current source. Certainly I can do that. Then I have bus 2, then here I have j. Okay, and so here I will connect So this will be converted here, here. Okay, hold on a second. So if I'm converting this star into delta, right? So these 2 points will be connected, these 2 points will be connected, and these 2 points also will be connected. Okay, that is interesting. But the midpoint will go away, right? Midpoint, okay, midpoint will go away. That is fine. Midpoint will go away. But what will happen to this point? So this star point will go away, right? If I convert this into delta. Okay. Mm, okay. It's not that simple as I thought, as it would be initially. Okay. Ah. So I don't think we can solve. So let's solve in with basics. Okay, I thought of converting this into delta, but I'm not able to figure out that way. So let's try to solve it using basics. So this is the incoming current I2. This is the incoming current I3. This is the incoming current I1. Correct. And if you remember, your Y bus is actually equals to, so your I entering in the node or I incoming in the node equals to Y bus into V V node. So if I apply a KCL at this particular node, so let me assume this voltage to be Vx voltage. Okay. So if I apply a KCL at this particular node, this would be, so let me first apply a KCL at this node, right? So it will be Vx, KCL at node X, Vx minus V3 by J plus Vx minus V2 by J plus, basically it is simply V. So if you apply the KCL, okay, one more thing will be there, Vx minus 0 by J plus Vx minus V1 by J plus Vx minus 0 by J equal to 0. So ultimately the J will be cancelled. So your Vx, right? So it will be 4Vx equals to V1 plus V2 plus V3. So your Vx actually is equals to V1 plus V2 plus V3 by 4. Okay, and you will actually use it. So now I will apply KCL, let's say at node 1. Okay, if I apply KCL at node 1, and that will clear out everything. So if I apply KCL at node 1, what is the okay, let me apply node 1 is here, right? This is the bus 1. So I1 would be equals to incoming current, that is I1, that would be equals to the outgoing current, right? Outgoing current would be V1 minus Vx by J plus, okay, I think that's it. I think that's it. V1 minus, so there is only a single branch that is going out. V1 minus Vx by J. Okay. So I1 is equals to V1 into minus J. Right. Let me first write what is V1 minus Vx. Right. So V1 minus Vx would be 4V1. So let's just calculate V1 minus Vx, that is 3V1 minus V2 minus V3 divided by 4J. That's all. Okay, we got to our answer. So this would be equals to minus J 3 by 4 V1 minus, so this will be plus J V2 by 4 plus J V3 by 4. Okay, so minus J 3 by 4 is presented here, it is not present anywhere, plus J 1 by 4 plus J 1 by 4 plus J 1 by 4 plus J 1 by 4. So option A is correct, option C is correct. Okay, that is your solution. but I was trying to apply properties. Okay, I figured out, okay, I'm not able to apply any property here. Okay, I was stuck. So then I thought, okay, let me go back to basics. So always basics will always help you out. Okay, basics will always help you out whatever you do, correct? So let's solve the next question, right? So I only solved it for first row. Now as you know the process, you can obviously apply KCL here and here, you will still be able to solve it. This is the next question. Okay, the bus admittance matrix, Y bus matrix of a 3-bus system is shown. Cool. There is no shunt inductor connected to any of the buses. Which of the following is not true? So there is no shunt inductor connected to any of the buses. So there can be shunt capacitor, but there cannot be any shunt inductor. So I have a 3-bus system. So let me use this. So if I have a 3-bus system, bus 1, bus 1, okay. Let me just create the buses. So this is bus 2 and this is bus 3, right? Bus 1, bus 2, bus 3. So now if I want to solve this, right, what should I do to solve this? So so they have actually given us these values. Now they are telling me that there is no shunt inductor connected. So in the shunt inductor is not connected. Line charging capacitor of finite value is present in all the 3 lines, which is not true, they are asking. Okay, line charging capacitor is present in all the 3 lines. How can you verify that? So what happens? What is this first column? So what is this first element in the first row? The first element in the first row tells you that this is the sum of all the admittances connected at bus 1. That is what the diagonal element of a Y bus tells me, right? So diagonal element for the, let's say for the first row, is minus J15. So minus J15 is the sum of all elements present, all elements connected on that bus. Sum of admittances, right? Sum of admittances. And this, right, this tells me the connection between bus 2 and 3. So connection from bus 1 to bus 3 is the negative of this. Okay, it is the negative of this, correct? So here in between bus 2 and bus 1, I have a negative of this admittance connected. That is, between bus 2 and bus 1, I have minus J10 connected. Okay, bus 2 and bus 1 will have a minus J10 of admittance connected. So how can I represent minus J10 of admittance in terms of impedance? It will be plus J0.1. So between bus 2 and bus 1, there is plus J0.1 of admittance connected. Between bus 1 and bus 3, there is minus J5 of, between bus 1 and bus 2, there is plus J0.1 of impedance connected. Because admittance is known, you can calculate the impedance. I hope you know your admittance is nothing but basically this, right? Off diagonal elements represents the negative of the admittance connected between bus that corresponding bus. Okay, these are properties of Y bus. If you don't know, you have to revise that. So what will happen is that your between bus 1 and bus 3 there is an admittance of minus J5 connected. What is the impedance? Impedance would be J.2. That's all. Okay, we got the bus 1 and bus 2. Now what is the, so this is my bus 1, correct? Assuming it to be a current source, just for a second. Now we know that this represents the sum of all the admittances connected at this particular bus. So minus J15 would be sum of, so let's assume that if they are telling me that line charging capacitor of finite value is present in all the 3 lines. If I assume that in all the 3 lines line charging capacitor is present, okay, let's assume that. Okay, if I assume that in all of the 3 branches line charging capacitor is present, right? So in this particular bus, if I assume a line charging capacitor is present, then let's assume that here there is some line charging capacitor Yx, just for a second. If I assume that, so basically means that sum of the admittances connected at bus 1 all must add up to this particular value. That is a property, right? So it will be Yx, it is admittance, so it will be plus Jyx plus, what is the admittance here? It is already given here, that is minus J5. Remember, it is minus J5. So it will be minus J5, right? Because the impedance is J.2, admittance would be inverse of this. And impedance is plus J.1 between bus 1 and bus 2, admittance would be minus J10. This is equals to the value that is given over here, that is minus J15, right? That is the property of Y bus. Property of Y bus tells me sum of all the admittances connected at bus 1 must all add up to this particular number, the diagonal element of the Y bus. If I observe correctly, your Yx comes out to be 0. That means there is no shunt admittance connected at bus 1. The question tells me that there is no shunt inductor connected in any of the buses, and from the given information I can conclude safely that there is no shunt admittance connected in bus 1. I can conclude that safely. So there is no shunt admittance connected in bus 1, certainly I can conclude that, correct? So line charging capacitor of finite value is present in all three lines is incorrect. It is not present. A line charging capacitor is not present in bus 1. So this statement is incorrect, and they have asked me which is not true. So this statement will be my answer. Okay, and it is a MSQ. So multiple answers can be there. Certainly bus 1 does not have any admittance connected. Now let's do the same for the bus 2 and bus 3. Okay, for the bus 2 and bus 3, if I notice one thing, right, that, so what essentially happens, how do I know that there is no shunt admittance? If you add all the elements in a particular row, you will realize whether I have a shunt admittance or not, right? If it is 0, you will not have a shunt admittance. If it is non-zero, you will have a shunt admittance. You will have a shunt admittance. If you see here, if I add up here, right, we are getting a shunt admittance. If you add up all these numbers, you will see we are getting plus J.4. So there is a plus J.4 of admittance, sorry, not plus J.4, plus J.5 of admittance connected in what bus? In the bus 2. So there is actually a shunt admittance connected in bus 2. Okay, so its admittance Y20 is J0.5. And what about Y30? These are called as Y20 means admittance from bus 2 to ground. 0 is ground. Bus 3 also, if you add all these elements up, you will see you are getting plus J1. That means you will have admittance at bus 3 as well. Y30 will be equals to plus J1. Okay, so this is the Y bus diagram basically. This is a very, very important thing that you can draw the Y bus diagram. Let's not include current sources. Let's keep it as it is. Now, yeah, line charging capacitor of finite value is present in line 2 and line 3. It is correct. There is a line charging capacitor in line 2. There is a line charging capacitor in line 3. Certainly, it is there. So this option is correct, and they are asking which is not correct. So this is not my answer. Line charging capacitor of finite value is present in line 2 and 3 only, and a shunt capacitor of finite value is present in bus 1 only. Okay, this is wrong, right? Again this is wrong, but because there is no capacitor present in the bus 1, there is no shunt capacitor present in bus 1, that can be properly seen, right? So this option is again wrong, so this will be again my correct answer, correct option. Cool. Okay, now next what they are telling me, that line charging capacitor of finite value is present in 2 and 3 only, shunt capacitor of finite value is present in bus 3 only. Okay, shunt capacitor of finite value present in bus 3, line charging capacitor of line charging capacitor of finite value is present in bus 2 and 3, and shunt capacitor of finite value is present in bus 3 only. Now what happens is, actually they should have properly defined what they mean by line charging capacitor and shunt capacitor. So what happens is, we can break down our capacitor, right? This capacitor, whatever admittance you are measuring, it is like a combined effect. But if we do the pi model, then we will see that this line bus 3 will have capacitance present on both. So what happens is, okay, I have not even drawn the connection between bus 2 and bus 3. There will be some connection because these are all non-zero, so I'm not writing the values. You will be able to calculate the values. That is not the purpose. The purpose is, the capacitance that you see, right, it is distributed. Okay, it is distributed. Now what happens, that certainly there is line charging capacitor between bus 2 and bus 3, certainly there is. Okay, so if I consider the pi model, okay, if I consider the pi model, right, if I consider the pi model, and if I say this particular transmission line has an overall admittance of pi, sorry, y or small y, then according to the pi model we can divide the admittance, half of it here y by 2 and half of it here y by 2. Okay, because admittance is a distributed parameter, we can do that, right? So if I do something similar here, if I assume that overall the admittance of this whole line is j1, so half of it can be replaced here, half of it can be replaced here, that is j.5, j.5, and still my bus 3 will have some admittance left, right? So if I connect these two lines, then I can break this y30 in terms of a shunt admittance. So basically this can be a line charge. So line charging capacitor basically means the capacitor that is present in distributed form in the line. Okay, so I can use the pi model to model that. So there, here I will have y by 2, y by 2, although again I will say this, that they should actually properly mention what they mean by line charging capacitor. Also they should properly give the pi model, otherwise how you will have to assume the pi model, right? So if I have j.5 here, right, then I will have j.5 here, because it is a line charging capacitor, right? Both sides should have same value if I do the pi modeling. So if I have j.5 here I have to have j.5, I have to have j.5 because it is a line charging capacitor. Okay, certainly you will have to do it like that. So if you have some value here, let's say if you want the line charging capacitor to be okay, I will say this. So let's first do this. So if I have j.5 here, I can have j.5 here, correct? Then what you can do is, what is the overall admittance here? J1. I have only utilized J.5. So I can have another admittance, and this admittance is actually called as the shunt admittance, J.5, because overall admittance here was supposed to be J1. So this admittance is actually called as a shunt admittance, that is connected with the supply or with the bus, and this is the distributed admittance. Okay. So I can have a shunt admittance in bus 3, but I don't see a shunt admittance. I don't have any other option to put a shunt admittance here. So if you want to double down on this, that so from this, right, we can see that we will have a shunt capacitor on bus 3, we will not have a shunt capacitor on bus 2. Okay. So option D will be actually will be true. So hence we have to tick mark the not true. So option D will not be correct. But let's try to double down on this. Let's try to double down on this. So I will explain few things step by step. What do they mean by line charging capacitor? Okay, I will explain all these options step by step. Let me again re-explain the question. Okay. So all these things are drawn, these are fine. Now what do they mean by line charging capacitors? So line charging capacitors are these capacitors, okay, which are present in the line. Okay. And we can use our pi model to model it so that we can do our circuit analysis. That's why it is a distributed parameter. So we make it concentrated, half on the one side, half on the other side. Okay. So let's slowly break down. So let's say I have a 3 bus system. Okay. And certainly I know that here whatever shunt admittance will come, that sum will be 0. Certainly I know that. So if you assume for a second, just assume all the lines have a line charging capacitor. So line 1 2 has a line charging capacitor, line 1 3 has a line charging capacitor, line, so let me mark the lines 1 2 3, line 3 2 has a line charging capacitor. Let's assume that. So their whole line charging capacitor is line 2 3 CH. Okay. And between line 1 3 it is line 1 3 CH, and between line 2 1 is line 2 1 CH. Okay. So these are my line charging capacitors basically. Now if I assume this, so we know, because we can model it using pi model, so one half will be on this side, other half will be on this side. Correct? I hope you are correct. So this will be equals to so y21 CH by 2, right, y21 CH by 2, and this is my bus 1, and from the other half, other side, right, I will have this y13 CH by 2, correct, y13 CH by 2, and of course let's assume that line 1 has a shunt admittance as well. Correct? Line 1 has a shunt admittance as well. Let's assume that shunt admittance to be y10. Now can you tell me what shall be the sum of all of this? Because there is no shunt inductor. They told me there is no shunt inductor. That's why in the question they have mentioned there is no shunt inductor. There is no possibility of a shunt inductor here. So all these 3 must add up to 0 as established here. Correct? As established from the Y bus. So all these 3 must add up to 0. If all these 3 must add up to 0, right, then all these 3 has to be 0 individually, because all these 3 are positive numbers. If all, let's say if a plus b plus c is equals to 0, and all a b c are all positive numbers, then certainly a equals to b equals to c equals to 0 has to be the only solution. If a b c all are positive. Okay. Correct? You got the point? Right? So certainly we got to a point that our y21ch is 0. So y21ch by 2 is 0. That means y21ch is 0. So this is 0. Hence this is also 0 and y10 is also 0. So in the first option, what is that they're telling me? They're telling me line charging capacitor of finite value is present in all the 3 lines. This is wrong. Okay, I was already telling this is wrong from this particular statement only, because this does not have a capacitor connected at all. So this has to be wrong. But now I hope it is more clearer to you why this line charging capacitor statement is essential here. Okay, so there is no line charging capacitor, neither there is a shunt capacitor in the bus 1. So certainly first option is correct because it is not true. So but we got this information, our task is very easy, right? So y21ch and y31ch all are 0 and y10 is also 0. So on the bus 2 I will only draw the line charging capacitor due to y23. So here I will have y23ch by 2, and here I will have y23ch by 2. Okay, and obviously in between they have some admittance that I'm not concerned about right now. Okay, I'm not concerned about this connection between them. They have the connection that we already know, right? We are only considering the shunt parameters across the buses. Now let's assume that both of them have some shunt admittance as well. Let's assume this. Both of them have some shunt admittance. So let's assume this is y20. Let's assume that I have y30. Correct? So y20 and y30. Right? Now how to solve this? How to solve this? How to solve this? So this, if you want to solve, right? How do I solve this? This I want to solve. Okay. Now what more things we know? We know that the this 2 must add up to what? j.5, right? That is what we have established previously. So basically my y20 plus y23 ch by 2 must be equals to j, let's say 0.5. We are not considering the like that j term. We know it is admittance, so it will be plus j only, and from this we know this must be added up to j1, right? j1. So basically your y23 ch by 2 plus y30 must be equals to 1. Okay, okay. So if I solve for this, right, yeah, if I solve for this, we get, if I subtract this and this, what equation I will get? This will be y2, so y30 minus y20 is equals to j 0.5. Okay, that is what y30 minus y20 is equals to, right? And your y23ch by 2. Okay, if I, okay, this is the only relation that I am able to get right now. Okay, now what are they telling me? That line charging capacitor of finite value is present in line 2 and 3 only, and shunt capacitor of finite value is present in bus 1 only. Shunt capacitor, this anyways wrong, right? Shunt capacitor is not present in bus 1, so this is anyways wrong, so this will be correct. Let's read the last one. Line charging capacitor of finite value is present in line 2 3 only. That is certainly correct, that is certainly true. Shunt capacitor of finite value is present in bus 3 only. Okay, it is present in bus 3 only. That is what they are telling me, that it is only present in bus 3. So if I assume this to be only present in bus 3, that means this will be 0, and if this is 0, your y23 ch by 2 is equals to 1, is equals to 0.5, right? Okay, okay, let's assume that there is some shunt admittance. If there is some shunt admittance, let's say it is j.1, right? If it is let's say 0.1, so this sum will be 0.4, so that will actually make this to be 0.6. That is still fine. Yeah, so I was thinking that this is the only possible case, but I again brainstormed a bit. I think the question that they gave is, I feel it is wrong. So this is not a correct statement, this is an incorrect statement. Okay, I feel this statement is incorrect, so this also should be answer. I think gate they gave these two as answer, but I feel this also should be the answer. This is not correct. So because I was brainstorming, I only thought for this case, but as I uh, deep dived here, right, I got to this conclusion that yes, there can be more combination. Let's assume that y20 is non-zero, y20 is 0.1. If y20 is 0.1, your y23 ch by 2 would be 0.4. So this will be 0.4 and your y30 would be 0.6. Is there any problem? No. So if you know anything else, if you can think of it, right, let me know in the comments below. But according to me, answer should be A, C, D, because this is also incorrect. I was thinking about it. Initially I thought both of them will have j.5. That is what the gate examiners also thought. If I give both of them j.5, then there is no possibility of a shunt capacitor. So hence uh, option D is actually true. Hence option A and C will be my answer. But I feel now this is wrong. This analysis is wrong. Okay, I was also doing the wrong thing only, but I realized after I thought about it a bit more, then I realized no, this is the correct analysis. And one of our students actually in the group actually mentioned this. I remembered right just now. So he actually pointed out that option D also can be true. So option D also can be false. So if it is false, due to this statement, it is not present in bus 3 only, it can be present in bus 2 as well. Okay, not only. What they can certainly say is definitely bus 2, bus 3 always will have higher shunt admittance than bus 2, or higher shunt capacitor than bus 2. That is certainly true. But I cannot say bus 2 will not have any shunt admittance. That is what this uh, D option is telling me, that only bus 3 has finite capacitance, bus 2 does not have any capacitance. Certainly that is wrong. So I just corrected my I was just thinking incorrectly. I think now we are clear. Okay, so according to me, option A, C, D should be the answer, but gate answer key gave as A and C. I was not there to challenge, so I did not. So I did not knew about this. Now I am figuring out, yes, option A, C and D should be correct here. Let's solve the next question. This is the next question. So essentially they're telling me the system has a 3 bus system, which this supplies to P2 200 megawatt for 40 MVAR. Okay, this is the amount of power that this is applying. And here I know the voltage and angle of bus 3, and of bus 1 I know the voltage, I don't know the angle. Okay, cool. Okay, now what are they telling me? They're telling me that all these things are written over here. Now a variable current source at bus 1 is maintained at this much amount of pu voltage, and the phase angle of the current source is this theta 1 plus pi by 2, theta 1 plus minus pi by 2. Okay, and theta 1 is the voltage of this, correct? Theta 1 is the phase angle at the voltage bus 1. The three buses can be categorized for load flow analysis as. So certainly I can say bus 2, I know the power and reactive power at bus 2. Certainly it will be a PQ bus. Bus 2 will be a PQ bus, that is present in option D and option C. Certainly. Bus 3, I know the voltage, I know the angle, power angle. Certainly bus 3 will be my slack bus. So option C and D are matching. Now there is a confusion between option C and D regarding bus 1. What will be my bus 1? So in bus 1, certainly I know the voltage, right? So for it to be a load bus, right, we should know the power and reactive power, right? So do I know the power here? Do I know the power? So this is a controlled current source. I know the voltage here. I know the voltage here. I know the angle. Do I know the power? I don't know the power here. I don't know the power. So certainly I know the voltage, right? So it certainly cannot be PQ bus. Why? Because certainly I know the voltage. Okay. Certainly I know the voltage. So it cannot be hold on a second. It cannot be PQ bus. Correct. So it cannot be PQ bus because I know the voltage here, right? It cannot be PQ bus because I know the voltage. Okay. So it has to be a PV bus. It has to be a PV bus. First of all, it cannot be a PQ bus because in PQ bus the voltage is unknown, but I know the voltage magnitude. Okay. Now second point would be, so how do you know you know the power? How do you know the power? So if you observe one thing, right, the phase difference between the voltage and the current, right, at this node is what? Are you able to observe one special trait? What is the phase difference between voltage and current? It is pi by 2. And what is power? Power is Vi cos of theta V minus theta I. That is the phase difference between voltage and current. So theta V, the phase difference between voltage and current is what? Plus minus pi by 2. So it is Vi cos of plus minus pi by 2. Certainly it is Vi cos of plus minus pi by 2. Correct? Certainly this will be 0. So power is certainly 0. So power is known, voltage is known. So it can be characterized as a PV bus. Okay, that was the small trick involved here. Let's solve the next question. This is the next question. A bus impedance matrix is shown. A symmetrical fault through a fault dependence of this occurs at bus 2. Neglecting the pre-fault conditions, voltage at bus 1 during the fault is. Okay. So they are asking me the voltage at bus 1 due to a fault at bus 2. Correct? That is what they are asking me. So how do I calculate this? So we know this, right? So during fault what will happen? So how do I write my Z bus equation? So V bus equals to Z bus into I, entering current, right, in the node. Correct? So what will be your fault current? So basically, let's say a fault has occurred in bus 2. That is what they're referring to, right? A fault has occurred in bus 2. So if that fault has occurred in bus 2, this is my bus 2, right? Through a fault impedance of J 0.007, and they are telling me neglect pre-fault conditions. If they're neglecting pre-fault conditions, so assumption is your whole system is operating in no load. So if it is operating in no load, how do I calculate the fault current IF? How do I calculate the fault current IF? Right? So to calculate that, you need to find out the voltage at this node. So to do that, what we do? We calculate the equivalent Thevenin's circuit from this node. So from this node, what is the equivalent Thevenin's impedance? It is nothing but the diagonal element of that particular bus. So it is Z22. So its equivalent Thevenin impedance is J 0.093. Okay, that is my Z22. And of course, it is operating in no load. So its Thevenin voltage will be 1 pu, 1 angle 0 pu. So from this, you will be able to calculate the fault current due to this short circuit fault. Okay, symmetrical fault. So your fault current IF would be equals to VTH 1 angle 0 upon J 0.093 plus J 0.007. So this would be basically J 0.1. So this will be minus J10. That is your fault current. Okay. So minus J10 is your fault current, minus J10 pu. So this is minus J10. Now the point is I actually changed few definitions here. I had to take a bit of break. So we know that this, right, the definition of Z bus is basically voltage at a node equals to the entering current. Okay, that is the basic definition of a Z bus. So Z bus is used to calculate the voltages, correct? Now, what happens when there is a fault current? So when there is a fault current, the voltage due to that voltage at a bus I will be equals to the preload voltage, pre-fault voltage, that is Vi0 plus delta Vi due to the fault. How to calculate this delta Vi? How to calculate this delta Vi? It is nothing but done by this equation. So if I want to calculate delta Vi, what you will have to do is this will be Vi, right, delta Vi. Okay, yeah, so basically your delta Vi, so this is written as delta V into Z into the currents, okay, during fault. So change in the voltage into the equals to the impedance, Z bus impedance, into the currents during faults. So what is the entering current in bus 2? So what is the currents in the other bus during fault? So because they have told us to neglect any pre-fault loading conditions, so I will assume that there is no current in the other bus, that is bus 1 and bus 3. So there is only current during fault. Where is the current? It is only present in bus 2. That is equals to what? That is equals to IF. No, that is equals to minus IF. Why minus IF? Because here we write the definition as I entering. That is the definition. In Y bus as well, we write I entering. So this will be minus IF. This will not be plus IF. Okay. So all this will be minus IF, right? So yeah, this will be minus IF. Now we got to this answer. So we will now solve. So actually your delta V, right? Delta V in the bus 2. So if I want to compute, sorry, in the bus 1, what will be delta V in the bus 1? So I will have to expand with respect to first row. If I expand with respect to first row, this multiplied by this will be 0. This multiplied by this will be non-zero. This multiplied by this again will be 0. So actually your answer would be minus J minus J 0.61 into IF. So this I will add here. So pre-fault, what was the voltage? 1. Post-fault, this incremental change will be there. So now what is your IF? IF is this, right? Minus J10 PU. So actually what happens? This is minus J into minus J into 0.061 into 10. That is equals to, just give me a second, 0.061 into 10. This is actually negative, right? J square is minus 1 and minus minus is plus. So this will be plus 1. That is 0.39 PU. Okay. So this will be your answer. 0.39 PU would be your answer for the question. That's how you solve. So these things you have to take care of, or you can directly remember. Okay, either you directly remember or you can derive from here itself. Let's solve this question. During a power failure, a domestic household uninterruptible power supply supplies AC power to a limited number of lights and fans in various rooms. As per Newton-Raphson formula, UPS would be represented as what? Okay, so we see your UPS is delivering power only under certain conditions. Whenever there is a power shortage, right, it does not deliver power always. So it certainly will not be a generator bus, that is, it cannot be a PV bus. Certainly it will not be a PV bus. It certainly cannot be a PQ bus, because PQ bus is a load bus, it absorbs power, but here UPS is delivering power. It certainly will be a slack bus. So we have only mainly 3 types of buses, right? It certainly will be a slack bus. Why? Because slack bus, if you know, it delivers the additional losses throughout the power system under certain conditions. If and when required or some extra power is required, it will deliver, right? That is the task of slack bus, and UPS is exactly working as a slack bus because it is not always delivering, because once you have the power, you will get the power from the grid. But if there is a power failure, UPS is there as a backup. So slack bus is always there as a backup. So it will not always help you out, but when you require it, it will help you out. Okay, so UPS is working as a backup, so it is behaving as a slack bus. I have mentioned why it cannot work as a PV bus, because it is not always operating as a generator. No, it is not always delivering power. It is delivering only when there is a power failure, and of course it will not be a load bus. So option A will be correct. And with that, we are done with load flow analysis and with the first part of PSA. Now we will start with PSA 1, that is transmission line parameters. So let's begin with transmission and distribution of power. Uh, this is the first question. We have to consider a overhead transmission line. It is a 3-phase system, 50 Hz balance system with conductors located at the vertices of an equilateral triangle of length 1 meter as shown in the figure below. The resistance of the conductors are neglected. There is no resistance. The geometric mean radius of each conductor is given as 0.01 meters. Neglecting the effect of ground, the magnitude of the positive sequence reactance is. Okay, so basically they are talking about, so if they are neglecting the effect of ground, that means there is no capacitance, there is only inductance. So what they want me to compute the reactance, which comprises of the per phase inductance, right? So positive sequence reactance would be simply the per phase inductance into the frequency, right? Omega into L phase, that is the per phase reactance. Now L phase, there is this formula which you will have to use, which is 2 pi into 10 raised to power minus 7 ln GMD by GMR, Henry per meter. Okay, so they have given us, they have already asked in per kilometer, right? So make sure you see this. They have asked in per kilometer. So at the end, I will convert everything to per kilometer. So what is GMD? GMD would be the geometric mean distance, right? How many conductors I have? 3. So simply it will be the mean of the geometric mean of the distances between each of the conductors. Correct? 3 conductors I have. So it will be the geometric mean of the 3 conductors, that is D AB, DBC, DC. Okay. So that would be equals to 1 into 1 into 1, that is 1 only, that is 1 meter only, and GMR is already given, that is 0.01. So actually this will be 2 pi into 10 raised to power minus 7 ln GMD is 1, GMR is 0.01. So this will be equals to Henry per meter. This will be equals to, let me solve it, 1 upon 0.01 ln into 2 into pi. Okay, that is 28.93 into 10 raised to power Henry per meter. Cool. So this is my inductance, right? I need my reactance, which will be omega into L phase. That is what I am interested in. So omega is 2 into pi into F into L phase, that is 28.93 into 10 raised to power minus 7. So this would be equals to into 100 into pi, and now this is what, this is in ohms per meter. I want to convert this into ohms per kilometer. So what is 1 meter equals to in kilometers? It is 10 raised to power minus 3 kilometers. So this can be converted, right? This will be converted. I can write here 10 raised to power minus 3 kilometer, correct? And 10 raised to power minus 3 can go at the numerator to become 10 raised to power 3. So this will be actually 10 raised to power minus 4. This will be converted into 10 raised to power minus 4. And if I multiply 10 raised to power minus 4 with the product's resultant, this will come out to be 0.91 ohm per kilometer. They have asked us to round off to 2 decimal places, correct? Round off to 3, okay, 3 decimal places. So it will be 0.90909. Okay, just give me 1 second. I hope I am doing everything correctly. ln 1 by 2 pi. Okay, so I'm sorry, this formula is wrong, right? This should not be 2. This will be 2 into 10 raised to power minus 7. I'm sorry, there will not be a 2 pi, right? This will be 2 into 10 raised to power minus 7. So that's why, that's what happens when you remember the formulas, you can mess up. So actually there will not be a, just a small update, there will not be a pi. I multiplied a extra pi, so I will have to divide by pi. That will come out to be 0.289. So your answer would be, this would be 0.289 actually, 93. And hold on a second. What will be L phase? L phase would be this is my this, right? So this divided by 2 into pi into 50. So yeah, L phase would be 9 point, this would be 9.21 into 10 raised to power minus 7. That's all. Okay, let me just verify. 0.01, sorry, this is 100 ln into 2, yeah, 9.21 10 raised to power minus 7 Henry per meter. Okay, that is what your L phase is equals to, correct? Yeah, so we got this, we got our reactance. Make sure you apply the correct formulas. Okay, so this is our answer. So our answer would be, we have to round off to 3 decimal places, so this will be 289. Okay, so yeah, let's move on to the next question. This is the next question. Basically, a 3-phase 50 hertz generator supplies 3 megawatt power at 17.32 kilovolt voltage. So basically it is supplying a power at the receiving end. I am receiving as 3 megawatt at a voltage at the receiving end as 17.32 kilovolt. Now remember, whenever they discuss about this, right, by default they mention the line voltage, so I will obviously convert this into phase voltage. Okay, by default I will assume my system to be in star connections. So we have a balanced 3-phase inductive load through an overhead line. So we have a inductive load that is told to us. The per phase line resistance and reactance are given. So the line resistance and reactance are given to us. .925. If the voltage at the generator terminals, right, so basically the sending end voltage is 17.87, of course I will divide this by √3. Okay, and here I will have the load that is connected, and I will have the receiving end voltage, that is 17.32 by √3. Of course there will be some power angle delta. Let's assume this is a reference and it is taking 3 megawatt of power. The power factor of the load would be, what is the power factor of the load? Okay, so how do I calculate this thing? Okay, I'm thinking, like, of course there is a longer method that I know already. I'm thinking, can I make it a bit easier for us? Can I make it a bit approximation? Can I make bit of approximation here. That is what I'm thinking. So we know this thing, that our what is our magnitude of VR equals to, that is equals to cos theta. I is not 0, I is there, R is 0, theta is a inductive load, so that is not 0. Okay. Okay, what I'm thinking is, can I do something, can I do something, can I do something, can I do something? Hmm. So there is this formula, but I don't think we can make that formula useful for us. Oh no, we actually can. So there is this formula, right? So this is a very approximate formula. Okay, your sending end voltage is equals to magnitude of the sending end voltage is equals to magnitude of the receiving end voltage plus IR into R cos phi R plus IR into X sin phi R. Okay, like there we will use this method later, whatever I show in the second formula that we'll use, but let us first try to, I'm trying to do some approximation here. Let's see if we are able to get to some answer, because you see this, right, this X is much greater than R, so I think we will be able to use this approximation. We'll see. Okay, okay, that will be difficult because you will not be able to square it. Okay. No, we will not be able to use this formula because squaring it would be much difficult, right? Uh, but if I, so the approximation is, if I assume that my R is much smaller than X, right? So if I assume this is not there, okay, so if I assume this R, this multiplication will be much smaller, so if I assume this approximately equal to 0, then your equation, this formula, right, this equation will be magnitude of Vs, that is 17.87 by root 3 minus, this is 17.32 by root 3, remember it is in kilovolt, right, this is in kilovolt, equals to IR. IR would be what? IR would be, it is a three phase power, right? So okay, this is also in cos phi only. Oh, IR would be what? Root 3 VL IL cos phi. So basically what happens? Your root 3 VL IL cos phi R would be equals to your power delivered, that is 3 megawatt, correct? So your voltage is already in kilo, let's say line voltage is already in kilo, that is this 17.32, right? So this will be what? 17.32 is nothing but 10 into root 3, 10 into root 3, correct? So this will be 10 into root 3 times root 3, that is 30 itself, 30 kilo. So this will be actually, IL will be IL cos phi R, or IL would be 1 by 10 cos phi R kilo amperes. Okay, this is your line current, and in star, line current and phase current are same. So I can replace my IR with IL, right, because line and phase currents are same in star. So this will be 1 by 10 cos phi R kilo ampere into X. X is 3.925, the reactance basically, into sin phi R. Correct. I'm just thinking, can we do it even better? No, we cannot. This is the best way which we can solve. I'm just thinking of something. Is there any other way? I think there is. Okay, we will see all the ways. So what happens? This, right? This is nothing but tan phi R, correct? And kilo will be cancelled simply because this is kilo amperes. So kilo will be cancelled. Let me just simplify this thing. So if I solve this, right? If I solve this equation, let me just calculate these values. So this shall be equals to 17.87 minus 17.32 divided by root 3 into 10 divided by 3.925. Okay, and so tan phi r is 0.8, so tan phi r would be 38.97 degrees, and your cos, they have asked our power factor, right? So your cos phi r would be equals to 0.777. Okay, now I don't know whether this is in the range or not, but this is very risky. I think the answer approximately would be 0.8 actually, approximately. So still we are far off. So I will hardly, very rarely I will recommend you use this formula unless this you are using it in MCQ. So try to avoid using this formula if you are solving a question in NT. Don't solve a question in NT with this formula. Try to use MCQ or MSQ. Okay. There is another formula for Vs. This is the another formula, right? Magnitude formula. If you don't know, okay. So if I resolve this, if I again assume that R is negligible, then your equation will be simplified with this, right? And again, if VR, Vs, everything is in kilo and IR also is in kilo, so this will be mega, and kilo square is also mega. So units are fine. Let us solve this equation now. So this will be magnitude of Vs whole square, right? So magnitude of Vs whole square, that is 17.87 whole square minus 17.32 whole square divided by 3, that is 6.4515 minus IR into x whole square. Now, okay, IR is also a function of cos phi r, because we don't know IR, right? Now this becomes a problem to us. IR is also a function of cos phi r, right? This will become a problem to us. We will not be able to solve this question. I mean, with this formula. So I'm just trying to think. No, you will not be able to solve the question with this. Hold on a second. Hold on a second. Hold on a second. Hold on a second. So, okay, no, I think we will be able to solve this question. So this will become a quadratic equation. That's all. So let's assume that your IR is equals to 1 by 10 cos phi r, right? 1 by 10 cos phi r. Okay. Sorry. We will not be able to solve this question because this will be 1 by 10 cos phi r into x. This will be sin phi r by x. No. We will not be able to solve this question. Like, I mean, we'll not be able to solve using this equation. So this equation also does not work. So then ultimately you will have to move on to this particular formula, okay, because you will not be able to calculate the power factor from here, okay. So that's a problem to us, right? That's a problem to us. So we will have to use this formula. So we know the power transfer through a transmission line, right, with the help of ABCD parameters. And if nothing is mentioned, because we see that R is very small, right, and they have mentioned nothing, so this is just like a short transmission line, and the ABCD parameter for a short transmission line is this. It is 1Z01. That is the ABCD parameter for a short transmission line. What is Z? Z is basically the impedance, series impedance, right? It is R plus JXL. Z is nothing but, this is nothing but my B, right? B is equals to magnitude of B into angle of B. Okay. So that is what my Z is equals to. Correct. So yeah, let's solve this. Now Z will be magnitude of B. Magnitude of B will be R square plus JX whole square. So R square, so 0.25 whole square plus 3.925 whole square whole under root. So it is 3.933. Angle. What will be the angle? Angle will be tan inverse x upon R. That is the angle. Correct. So 3.925 upon 0.25. Tan inverse of this is 86.355 degrees. Okay, 86.355 degrees. Now what are they asking? They are asking me that if I know the power, okay, what is the power factor of the load? So power factor of the load is what they are asking me. Uh, okay. So A is 1 in this case, and VR I know, magnitude of VS I know the power transport, right? So, okay, what will be the power factor? Power factor of the load will be nothing but simply, if I am able to calculate QR and if I am able to calculate PR, then I will be able to calculate the power factor of the load. Okay, why? Because I know tan phi R would be the reactive power upon the active power, correct? So I will be able to comment on the power factor of the load, or also if you are able to find out this delta angle right from this equation, if you are able to find out this delta angle, then also we can comment about the power factor. How to remember this equation? Very simple. Like in derivation, it will be magnitude of Vs into magnitude of Vr divided by magnitude of B. You can understand this right with the help of synchronous machines. In synchronous machines, the power transfer was Vs, sorry, E, EF Vt by Xs into sine delta. And this is similar to this, that if I have a purely reactive line, purely inductive line, then this will happen. So if your B is Jx, then what will happen? This beta will be 90. So it will be Vs Vr by X into cos 90 minus delta, that is sine delta. So that is what happens. Okay, that is how you can remember it. And this one, again, you have to make some ways. So divide by B will be there. Into A, you have to remember, and into VR square. Already Vs is here, right? You will not use Vs, you will utilize VR square. Okay, that's how you remember it. Into cos of beta again will come here minus alpha. Why cos is there? Because remember, this expression comes from the derivation of the complex power. Complex power is Vi conjugate. So in Vi conjugate, you will get a complex number, like complex equation, and then if you take the cos on both sides, that will give you the active power, and if you take the sine on both sides, that will give you the reactive power. That's all. Okay, so that's all basically, if you understand this thing. So yeah, that's how you remember it. And reactive power, you don't need to remember. Just instead of cos, replace this with sine. That's all. Reactive power, you don't need to remember. Just replace cos with sine. Okay. So I hope this part is clear to you. Replace cos with sine and you are good to go. Correct? Yep. Now, yeah. Now we can calculate. So I know the power, right? What is active power? Active power is 3 megawatt. Remember, this is the 3-phase active power. What is the single phase active power? It is 1 megawatt. Correct? Because this expression is written in terms of single phase components. So it is the single phase power. So it is 1 mega. I will not write mega because ultimately these are in kilo. So automatically things will be cancelled. So Vs into magnitude of Vs into magnitude of Vr. Magnitude of Vs was 10 root 3. Sorry, not 10 root 3, sorry. It was 10 root 3. This was the line voltage, right? And divided by root 3 would be my phase voltage. So this will be 10 only in phase, right? I am talking about the VR. What about Vs? Vs is 17.87. So 17.87 divided by root 3, that is equals to 10.31. Okay, divided by B. So magnitude of B, what is magnitude of B? Magnitude of B is nothing but magnitude of Z. In this case, it is Z, right? So this is 3.9 33 plus magnitude of A is this number, right? That is 1 into VR square. VR square is nothing but 10 square divided by magnitude of B, that is again 3.933 into sine of beta minus alpha. So beta minus alpha, right? Beta minus alpha. What is beta minus alpha? Beta minus alpha would be beta is how much? 86 degrees minus alpha. Okay, here I forgot to write. This would be sorry, not sine, sorry, this would be cos, right? I forgot to write beta minus alpha is also there, right? So cos beta is 86.35 minus delta. Actually we need to calculate delta. If I know delta, right, I will easily be able to write this expression, then I will be able to calculate q. Okay, that is the purpose basically. Or actually without that also you can solve. We will see how without that we can solve. Is there any easy way out to the solution? That is what I'm thinking about. Actually no, you will have to use this equation anyhow. Okay, so we spend a long time in this question, that's fine. This would be cos of 86 beta alpha. What is the angle of alpha? It is 0, so it is 0. 86.35 minus 0. Okay, so this would be equals to into 10 divided by 3.933 okay, 26 point cos of 86 minus 35 minus delta plus this would be 10 square divided by 3.933 into cos of 86.35, that is 1.686, and your active power is 1 megawatt. How is it possible? This has to become negative. Okay, 100 divided by 3 into cos of 86. Interesting. A is 1 only, so it does not matter. 100 divided by, okay, so, this is 4 only, so that is 25, that is fine. Cos of 86 when 3, this is also fine. How is this coming out to be greater than 1? That is what I'm trying to figure out, where I'm making the mistake. So this would be 100 upon 3.933, sorry, 100 upon 3.933, this is 6.35 cos of this, just 1.616, and this is 1 megawatt of power, so it will come out to be negative. How is it possible? Oh sorry, there was a, if I remember, there was, sorry, this was a negative sign. This also you need to remember, there will be a negative sign. So how do you remember? So I remember the negative sign with the reactive power actually, because if you remember in reactive power there was a term Vs minus Vr square, something like that, right? Del V basically. So yeah, you need to remember this will be negative. So there is a problem. Yeah, I do agree, but everyone has to remember, not only you. So you will have to remember this, unfortunately. So plus 1 divided by 26.23 cos, okay, not cos inverse, then again cos inverse, and then this plus 86.35. So your delta comes out to be 2.79 degrees. From this solution, delta comes out to be 2.079 degrees, and you can use this equation. So if I have a impedance over here, right, and I have a load over here, and I know the voltage here, that is VR angle 0, I know the voltage here, that is Vs angle delta. So I know this Z, So your current, right, IA, it is just a simple series circuit. So your current, receiving end current would be Vs angle delta minus Vr angle 0 divided by Z. Z is magnitude of Z, that is 3.933 angle 86.355 degrees. Okay, 86.355 degrees, right? So that is the case over here. Now this again you will have to solve. So Vs, remember, it has to be in the proper phase format. It is the phase voltage, right? Phase voltage. So it is 10.13. All I am concerned about is the angle actually. I'm not concerned about the phase, but overall it will come 10.13. Okay, this will be into cos of delta. So 2.079 cos, and then subtract this with Vr. Vr is 10. So the real part is very low, seems to be very low. That is 0.3 in kilo amperes, right? Remember, this is in kilo amperes. Okay, and the imaginary part would be plus j. This will be 10.31 sine of, so sine of 2.079 sine of this. So it is actually, okay, this is also pretty less, only 0.374, right? So now this, I will convert this into your format, polar format. So this will be this square plus 0.3 square under root. So this will be 0.489 divided by, oh no, what is the angle? 0.374 divided by 0.3, tan inverse. So it is 51.26 degrees. This is 86.355. Okay, so your phase of the current comes out to be minus 35.09 degrees, and your magnitude of the current 0.479 divided by 3.933, which is 0.121 kilo amperes, or I can write 121.79 amperes. Okay, so yeah, so your power factor angle would be what? Power factor angle would be 35. It is lagging, as you can see. Cause of this, it will be 0.812. Okay, so your power factor will be 0.818. In how many decimal places? In, okay, they have not even mentioned the decimal. So if you see, right, you're a bit far off your answer. Okay, so yeah, there is trade-off. So you see, this solution was so much simpler than this. I completely agree. Completely agree. So if it's NAD, right? So pause, solve it later, and then if you have time left, use the longer method. If you have no time left, use the shorter one, and just pray to God that they have given enough range. Pray to God that they have given enough range. That's all. Okay, you will have to pray to God. So we are done with this question. This question was lengthy to uh, to be least. Now there is the next question. A nominal pi model of a transmission line is shown. The impedance Z is given, the reactance X is also given. The magnitude of the characteristics impedance of the transmission line is. So this is a, like, again you have to memorize it. So the nominal pi model, the standard nominal pi model is defined by this, and the characteristics impedance is nothing but the ratio. So ZC, right? It is the ratio of Z upon Y. Okay, where Z is the series impedance and Y is the admittance. Y represents the admittance, and this is your standard pi model. So if this is x, right, so your characteristics impedance would be what? So this is my y by 2, this is my y by 2, correct, and this is my z. So what is my y basically? Characteristics impedance is z by y, right? So what is your y? Y is equals to this. Y would be equals to, remember, I have to write admittance here. What is the admittance here? It is 1 by x. Remember, what is the admittance? 1 by x. So I will have to equate admittance with admittance. Okay, don't equate impedance with admittance. Don't do that. Equate admittance with admittance. So your equivalent admittance, right, will be 2 by x, because y by 2 is equals to 1 by x. I am equating the standard nominal pi model admittance with the actual admittance that is present in the circuit, that is 1 by x. So your y will be equals to 2 by x, right, and that is what you will replace over here. How to remember this formula? So you certainly know that this is a impedance, right? Certainly it will have a unit of impedance, so certainly z will come at the top. Okay, and you remember that this under root L by C, this you have seen somewhere, right? So if z is there, there will be some under root. Okay, now where shall I place my y so that the unit, overall unit, becomes ohm? If I place my y in multiplication, so this is z, this is ohm, and this is ohm inverse, so this will become unitless. So certainly y has to come in the denominator, then only unit will make sense. That's how you can remember this formula. Okay, so this will be under root z. Under root z would be magnitude of under root z, that is 100. Okay, or you can simply put z also, no problem, because it is fine, you can put z. So actually what happens, this formula characteristic impedance, if you remember, it was r plus j omega l divided by g plus j omega b, something like this, right? Not g plus j omega c actually. Okay, and this is nothing but your z, and this is nothing but your y, that's all. Okay, and this is the standard nominal pi model. So yeah, I think you can put here with angle, so it is z is 100 angle 80, you can put that. Okay, because we can take under root for complex numbers, divided by y is 2 by x, so 2 by 3300. So this would be equals to 100 into 3300 divided by 2 under root, right? This will be equals to 406.2 angle 40 degree. Z is equals to 406.2 angle 40 degree. Now don't forget, you will have to write angle here as well. I missed a point. This is reactance, right? So this, what will be the angle here? This will be with J. Okay, so there must be an angle here. Don't forget to write the angle. I messed up. Don't forget to write the angle. So actually what will happen, this will be 40 plus 45. Okay, because this angle will go at the top, so 40 plus 45, so this will be 406.2. although they are not asking the angle, but someday they might. Okay, don't do this mistake. So this will be 406.2. so they have asked the magnitude of the characteristics impedance, so it will be 406.2. they could have asked you the angle of the characteristics impedance as well. Okay, they could have asked you that, so just be careful, don't make this mistake, right? Yeah, let's solve this question. Correct. So a 3-phase 50 hertz 400 volt transmission line is 300-meter long. Okay, so if it's a 300-meter long transmission line, that means they are talking about the long transmission line. Long transmission line. Okay, the line inductance is 1 millihenry per kilometer. Okay, so 1 millihenry per kilometer. The capacitance is 0.01 microfarad per kilometer per phase. Okay, the line under open circuit condition at the receiving end and energized, the line is under open circuit condition at the receiving end. So basically your current IR is equals to 0 at the receiving end. Okay, with and energized with a 400 kilovolt at the sending end. So my Vs is equals to 400 kV. The receiving end line voltage is equals to what? What is my VR? So how do I calculate my VR? So do you remember certain things that we had a ABCD parameter, right? So in ABCD parameter, your Vs was equals to AVR minus BIR, correct? So if it is operating in no load condition, so your VR would be equals to Vs by A, correct? And I will have to compute the parameter A. Now in a long transmission line, the parameter A is this, cos of H gamma L. Okay, that is how we define basically. So the receiving end voltage we can write. So these formulas you will have to remember. Unfortunately, we don't have any options. Okay, we don't have any options. We will have to remember it. So this is my A basically. Correct. So cos hyperbolic gamma L. I hope there is a hyperbolic function here, right? I hope there is a hyperbolic function. There is a hyperbolic function. So be very careful. So what is this gamma? This gamma is equals to basically under root Z1 into under root Y1, which is nothing but basically the series impedance into the parallel admittance. So yeah, we don't like it is, they are saying it is lossless line, right? So there is, I don't see any resistance. So what is your Z1? Z1 is the small z1, basically the impedance per unit length, right? That would be equals to 2 pi into f, that is 50 into 1 milli, right? And this is in per kilometer, so I will keep it in kilometer for now, it won't matter. Okay, I will keep it in kilometer. So this will be ohm per kilometer. So let me rewrite this will be 0.1 into pi, that is 0.3, correct? So 10 raised to the power of minus 3 into 100 into pi. Okay, so this will be equals to 0.314 ohm per kilometer. And what is your y1, right? What is your y1? So your y1 would be equals to basically it is the admittance, right? It will be omega into c, that's all. Y1 would be your omega into c. Okay, it is the admittance, correct? So omega into c would be equals to, so it is again the same 2 pi into 100 into c. What is c? C is 0.01 microfarad. Okay, so okay, this is already in micro, so let me keep it in micro only. So this will be 6.28 into 10 raised to the power minus 6 ohm per kilometer. Okay, so basically, right, your gamma. So gamma is the propagation constant. It is Z1 into Y1, and ZC is the if you see, ZC is the characteristic impedance that comes here and here. Okay, so we are concerned about A. So for A, you have to remember this, and because, so how will you remember this particular thing? This here you will have to remember. First of all, if you remember the first element, you know first element A will always be equals to or less than 1. okay, magnitude basically. So this will be only cos gamma, cos hyperbolic of gamma L, okay. Why cos and why not sine? This element will most probably be never negative, okay. This will be never negative. This will be almost always positive. If it is almost always positive, sine cannot come, cos will come, okay. Cos in the given range will be always positive. Second point is here, because cos has came here, here sine will come, and this will be coming with zc. Why? Because the unit of this is zc. Remember, a is unitless, so in a there will be no zc or no 1 by zc term, okay, because a is unitless. Similarly, d also is unitless. You can see a is unitless, right? B has unit of ohms. That's how you remember. And C has unit of ohm inverse. That's why there will be 1 by zc. That's how you remember this equation. And with this equation, I think most problems will be solved. Okay. So yeah. So gamma would be equals to this 6.28 into 0.314. Remember, per kilometer, it becomes per kilometer whole square. I'm taking the under root. So ultimately, it becomes per kilometer only. So this is Z1 into Y1. So this will be 0.31 whole under root. So this actually becomes 1.4 into 10 raised to power minus 3. I'm just simplifying my calculations. Ohm, sorry, not ohm, sorry. This will not be ohm, right? Sorry. What am I doing? This is ohm and this is ohm inverse, correct? So gamma will not have any units. Basically, it will be, the unit of gamma would be per kilometer square or kilometer raised to the power of minus 2, because ohm and ohm inverse will be cancelled, correct? Now what I will do, my a, right, will be equals to a will be equals to cos hyperbolic of gamma into L. Gamma is 1.4 into 10 raised to the power minus 3, and what is L? L is the length, because I am calculating the a parameter at the receiving end, because I have to calculate the receiving end voltage, right? So this a also should be at the receiving end, okay. So L is the distance from the sending end. So it is 300 kilometers long, so my L would be 300 here, okay. It is in kilometer already, this is also in kilometer only, okay. Gamma L, hold on a second, gamma, sorry, this will not be kilometer minus square, this will be kilometer inverse, right, because I am taking the inverse, okay. So kilometer inverse and kilometer, the units will be cancelled. So your answer would be, this will be 300 into 10 raised to the power of minus 3 cos hyperbolic of h. So this is a cos hyperbolic of this is actually 1.0. 1.09. That is what your a is equals to, right? 1.09. Okay. So a is 1.09. You got your a value. I'm just thinking whether I'm doing everything correctly or not. Z1, Y1, omega. Okay, omega can actually go outside. And root L1, C1. Omega is outside. So C1, right? So C1 into 100 L1, that is 0.01, that is 0.01 into 10 raised to the power of, so this is actually 10 raised to the power minus 8, 10 raised to the power of, I'm just thinking something whether I'm doing everything correctly or not. 10 raised to the power minus 8, 10 raised to the power minus 3, right, 10 raised to the power minus 11. So 10 raised to the power minus 4 can go outside, okay, and 10 raised to the power minus 1 inverse into 2 into pi into 50, and 10 raised to the power minus 4 is there, right? 10 raised to the power minus 4 is there. Okay, something weird is happening. We are doing something wrong. It seems so. Doing something wrong. Seems like that. It should come out to be 99 point something. Here I have done some calculation mistake. This is not correct. It is supposed to be basically 99. So basically it will be 9.934 into 10 raised to the power of minus 3. Okay, I'm doing some calculation mistake. That is what I'm thinking. So you can simplify this thing, right? Instead of calculating all this, what do you know? Your Z1 is omega into L, your y1 is omega into c, so your gamma is simply omega into L1 basically, right? Let me write this small l only, okay, L1 and C1. So omega into L1 into omega into C1, so this will be actually omega into under root L1 C1. So it becomes simplified. Then if you do it right without doing all this, right, this is just some manual task that we must not do, we must avoid in the exam hall. We must avoid these things, okay? Don't do this. Directly multiply, okay? So if I directly multiply, remember L1 and C1 are per kilometer, they are per kilometer, right? So if you solve this, you'll get this, okay? You can put C1 as 10 raised to power minus 8 and your L1 as 10 raised to power minus 3. Okay, it is 10 raised to power minus 3. Okay, sorry. It is 10 raised to power minus 3, right? So it is 10 raised to power minus 3. 10 raised to power minus 3 into 10 raised to power minus 8. No, that is correct. Okay, that is correct only. Yeah. So 9.934 into 10 raised to power, hold on a second, this will be 10 raised to power minus 4. Okay. So cos hyperbolic of this value, right, would be what? 9.934 into 10 raised to power minus 4 into 300. So 9.934 into 10 raised to power minus 4 into 300 cos hyperbolic 1.044. Okay, that is what your A is equal to, and you can use your A. Hold on a second. Again, I'm doing something wrong. Sorry, this is not degree, right? This is radians. Okay, don't make this mistake. It is radians. So 9.934, and don't forget there is 10 raised to power minus 4 as well, right? So 9.934. So I was doing degrees. Don't do degrees here, right? It is all in radians, okay, not in degrees. So into 300 into 10 raised to the power of minus 4 and cos hyperbolic of x. So okay, in radians this comes out to be 1.044. Okay, that is interesting. Am I doing this correctly? This is correct only. So 9.934 into 9.934 into 300 into 10 raised to the power of minus 4 cos hyperbolic. Yeah, it comes out to be 1. I think it was previously also coming out to be 1.044 only. I don't know why it is always coming out to be 1.044. I don't know. This is not supposed to be this, right? This cos hyperbolic function is wrong or something. I don't know. Okay, if it is operating in no load, actually this should A should come out to be less than 1. It should not be greater than 1. Actually, I'm just not able to figure out what mistake I'm doing. Either this hyperbolic function has something wrong or I don't know. Okay, let me try this, right? So this is 9.934 into 300 into 10 raised to the power of minus 4, which is 0.298. And I know basically cos hyperbolic, right? This e to the power of x minus e to the power of minus x. So this will be 0.298 divided by 2. That is what. So it is not minus, so it is plus, right? Sine hyperbolic x is minus, right? Okay, sorry. So this will be e to the power of x. E to the power of x is equals to, this is equals to 0.298 e to the power of x plus 0.298 e to the power of minus x divided by 2. This is 1.0447 only. Okay, that is interesting. Okay, then it's fine. 1.0447. So your magnitude of voltage would be, A is this value. So if A is this value, we know our VR is equals to, so this is actually magnitude. Okay, if I want to compute the magnitude of VR, I can only compare the magnitudes. So I know sending end voltage, the line is energized with 400 kilovolt at the sending end. So it is 400 kilovolt at the sending end. uh, uh, Remember this is line voltage, right? Okay, so if I write the phase voltage, it will be 400 kilovolt by root 3 divided by A is 1.044, and ultimately they want me to calculate the receiving end line voltage only. So anyways, you will multiply this by root 3. Okay, so automatically root 3 and root 3 will be cancelled. So your final answer would be this into 400, that is 382. 382.87 kilovolts. I think this will be your, this should be your answer for the question. Okay. So yeah, let's solve the next question. This is the next question. This is the fifth question, which we will have to solve. So in a single phase infinite bus system shown below, the generator is developing the real power of 0.8 pu at 0.8 power factor. Okay. So it is delivering real power at 0.8 pu. So the power that the generator is delivering, that is 0.8 pu. The line is purely reactive at 0.8 power factor. So cos phi is equals to 0.8 lagging from to the infinite bus. The power angle of the generator in degrees would be, what is the power angle? What is the power angle of the generator in degrees? Okay, what is the power angle of the generator in degrees? So they're asking me this power angle, right? So okay, I know the power factor, I know the power. I can also comment about the reactive power. Yeah. So what is, remember this line is purely reactive, right? If this line is purely reactive, I can use this, we can use multiple things here. So we know this, right? So we know active power is equals to EF Vt by XS sin delta, just the smaller version of this formula. This formula, that's it. And what is the smaller version of this formula? So this formula, the smaller version is Q reactive power, QE, equals to EF Vt by XS it is minus Vt square by XS cos delta. That is a smaller version. Okay, of course you can see the actual formula and then do the proper simplifications. Okay, so this is enough because I know my active power, I know my power factor. So what is my reactive power? Reactive power, right, at the receiving end, right? This is the receiving end active power, this is the receiving end power factor. The reactive power receiving end would be simply 0.6. Okay, you know the power factor, I think you can calculate. I will not comment here much. So I can, first of all, I can write in this formula. Okay, will that help me? That is what I'm thinking about. So EF EF sin delta, right? EF sin delta. I don't know what is EF sin delta. Actually, this formula will not be much useful to us, huh? This formula actually will not be useful to us because we will not. This will be very tedious for me to calculate the EF from here. We can use this formula. Okay. Now we can use this approximation, or you can use this one as well, whichever one is suitable to you. So this is the exact formula. This will always be applicable, right? This is always applicable. This is the approximated formula. Okay. So here we can use it. I know my receiving end voltage. So what are they asking? They are asking me the power angle, right? So from this I can actually I can compute my magnitude of the EF. If I calculate the magnitude of EF, then I will just put in this equation and I will get sin delta. So what is magnitude of EF? Magnitude of EF. Magnitude of EF, right? Magnitude of EF would be from this equation, right? We can use from this equation. This would be equals to VR cos phi. Okay. So yeah, we will calculate. So I know the receiving end voltage, that is 1 pu, right? 1 pu. So this is 1 pu, 1 into cos phi that is 0.8 plus 0 whole square plus VR sin phi r. So this will be 1 into sin phi, that is 0.6 plus IR into x. Now x is there, right? X is there. So what is the equivalent reactance? So it is J 0.25 plus J 0.2. So 0.45 plus 0.2, that is 0.65. So this equivalent reactance is 0.65. So I is 1. They have told me. What is the current? So we know P will be equals to VI cos phi, right, in per unit. So your I actually will be equals to V is 1, cos phi is 0.8, power is 0.8, so I also is 0.8. Angle is minus 36.86 degrees. So this would be this is minus 36.86. So this is actually 1 P only, 1 into now x. What is x? X is point okay, we just completed the x, that is 0.65, right? Yeah, 0.65 whole square. This will be equals to 0.8 whole square plus 0.6, sorry, 0.6 1.25 whole square under root. So your magnitude of V comes out to be 1.48 pu. All these formulas have been derived and this marathon has been taught already. Okay, you can watch that there. So this will be actually my EF, magnitude of EF. So I can use that here. So I know my active power, that is 0.8. I know my magnitude of EF, that is 1.4. Okay, let me use it here. So 0.8 equals to 0.1.484 into Vt is 1 divided by xs, that is 0.65 into sine of delta. That is what I need to find out. So from here, this divided by 0.65 into 0.8, that is, so sine inverse. Okay, this is in radians. What have they asked? Have they asked in degrees or radians? They have asked in degrees. Okay. So sine of this, and make sure you find in degrees only. So in degrees, your delta will be 20.51 degrees. So 20.51 would be your answer of the question. I could not think of a better way. So because here also you could have solved it, but it seems like I will not be able to separate out cos and cos delta, sin delta. That will be very difficult for me, right? I'm just thinking. It's difficult. It's difficult from here. Actually, yeah, because delta is unknown, right? It's not that difficult. I'm just thinking something. So this is one way to solve. Okay, certainly this is one way to solve. I'm just thinking whether I can find any other way. So, so if you remember one thing, yeah. So I think there is there was this machines chapter, right, in synchronous machines. So we had defined. So let's say this is my Vt, okay, and IR is lagging, okay, and we used to define our EF, right, that is the synchronous machine voltage, and then we used to say this particular angle is delta, this particular angle is theta. So and this whole angle, right, the angle between the current and the internal EMF is called as Xi. And do you remember what was the derivation for Xi? What was the Xi value? The Xi value was this: tan Xi was equals to, so whatever was here, right, this will come in the numerator and this will come in the denominator. Why? Because this is sine and this is cos. Tan Xi is sin Xi by cos Xi. That's why the sine term will come first and then the cos. So this will be V VR sin phi, which is sin theta essentially, plus IR into X divided by VR cos phi R plus IR into R. So in this case R is 0. So this formula will be much simplified. So now I think we can solve. So what is xi actually? Xi is this angle theta or phi plus delta. That is what my xi is equals to. Okay. So this is a derivation in the uh, machine chapter. So you can have a look for that. So from this also we can actually solve. So VR sin phi. So VR is 1, sin phi is 0.6. Correct. IR is 1, X is 0.65, that we just derive. Divided by VR is 1, cos phi is 0.8. Okay. So 0.6 into 0.6 plus 0.65 divided by 0.8, 1.5625. That is my tan xi. So if I take the inverse of this, right? So your xi would come out to be 57.38 degrees. So your delta actually would be this minus theta. Theta is, or phi is 36.86. Okay, that is my perfect angle. Right? That is my perfect angle. So this will be 36.86. I have to subtract 36.86. So this is 20.52 degrees. Okay, and that is your answer basically. Okay, so yeah, this is also another way. Instead of going by this long route, this is a easier route, because first you will have to find out the magnitude, then you will put it in this formula. That's a bit of lengthy way to go about it, right? This is a bit of easier way to go about it, right? So let's solve the next question. This is the next question. Okay, now this one is based of a very simple concept. Two single core power cables, so there are power cables, have a total conductor resistance of this and this respectively. So conductor resistance is there, and insulation resistance of this and this. When the two cables are joined in series, the ratio of the insulation resistance to the conductor resistance shall be. So this again I have taught in my full course. If two conductors, like a underground cables, right? Cables are connected in series. What happens? Their conductor resistance are in series, and their insulation resistance are in parallel. Why? Because insulation is always in parallel, right? And it is so high value, so I can approximate that there is very less amount of current flowing. So approximately these two values will be in series, and these values are so high that approximately this two potential, there will be no potential drop here. So approximately these two potentials will be same. That's why the insulation resistance will be in parallel. So what is the core conductor resistance? Overall, the conductor resistance, okay, is basically 0.7 plus 0.5, 1.2 ohms. Okay, and your insulation resistance will be when the two resistances are in parallel, that is 600 mega ohm into 900 mega ohm upon 600 mega. So I don't need to write mega, this will be mega only. Final answer. This will be 600 into 900 divided by 1500, so which is 360. That is what your insulation resistance is equals to. So this is my insulation resistance. Now they are asking me the ratio of insulation resistance over conductor resistance. So it is R insulation over R conductor, that is equals to 360 over 1.2 into 10 raised to power 6, right? Because it is in mega ohms insulation resistance. So this will be 30 actually, right? 360 upon 1.2, sorry, not 30, 300, okay? 300 into 10 raised to power 6. So your answer would be 300, right? Because 10 raised to power 6 is already there. Okay, so 300 is your answer for this question. Let's move on to the next question. So this is the next question where you will have to find out the geometric mean radius of this whole conductor, right? So how do I of a conductor having 4 strands with each strand having this, how do I compute the geometric mean radius? So I can consider this single conductor, okay? So what is the geometric mean radius of this particular conductor? So how do I compute the geometric mean radius? So it will be gm, so let me consider this as a, b, c, d, right? So basically the geometric mean radius would be daa into dab into dac into da, yeah, ad, okay? That is for the first conductor, right? First conductor. Now similarly I will have to do this same thing for the second conductor. It will be dbb, right? Then dba, then dbc, then dbd, okay? Similarly I will have to do the same for this conductor and this conductor, okay? So I will have to do it for these conductors. So the thing is that because it is a symmetrical structure, these values will be same. So essentially what I can do is this whole thing I can multiply this by 4 and then I can take the 1 by raised to the power of 1 by 12, right? Because there are 4 of these, right? 1 2 3 4, as it is symmetrical, all of these will be same. So actually there should be total 12 terms, right? 12 terms. Why? Because each of them will have these 3 distances and their own self GMR, right? That's why 4 terms. 4 into okay, hold on. See, this will be 16, right? The total combination will be 16 actually. Sorry, total combinations would be 16, not 4, 12, not 12. Sorry, 16. Because each has 4 terms and total I have 4 conductors, so total will be 16 terms. So that's why raised to the power of 1 by 16. Now as it is symmetrical, so they will be squared and then squared again. So they will be raised to the power of 4. So it won't matter. They will be same. So I will just have to compute this. So what is DAA? DAA will be the GMR of its own conductor, right? What is the GMR? DAA, that would be equals to 0.7788 raised to the power of R. If you remember it properly, right? It was e raised to power minus 1 raised into R. Right? That is what your self GMR is equals to, multiplied by DAB. So the distance between the centers, right? With distance between their own geometric mean radiuses. So this is, what is the distance? So this is R, this is also R. So it is 2R. So this will be 2R basically, right? Multiplied by DAC. So DAC, right? This is again 2R. And DAD, this is interesting. What is this? So if I see, this is a right angle triangle, right? So 2R is the base, 2R is the height. So what would be the hypotenuse? It will be 2R whole square, 2R whole square. So that would be equals to 8R square. That would be equals to 2 root 2R, right? Because it is hypotenuse, Pythagoras theorem. So into 2 root 2R, okay? And this raised to the power of 1 by 4. I hope you get the point, right? 4 and 1 by 16, this will be 1 by 4. So this will be actually equals to, R will come at the outside and this will be 0.7788 into 2 into 2 into 2 into 2 into 2 into 2 into root 2 raised to the power of 0.25. So that is 1.72289. And what is your R? Okay, R is not even given. So yeah, 1.7289, that is actually present in option D. So option D is your correct answer for the question. Let's move on to the next question, right? So this is the next question. Again, a pretty simple question where they have asked only 5% of the supplied power to a cable reaches the output terminal. The power loss of the cable in decibels is. So it's a very simple thing. Basically, power loss in decibels is computed as the ratio 10 log. So generally, any voltage, current, analog quantity will be written in voltage, current, everything will be written in 20 log some ratio. Okay, some ratio. But power, right? Because power is what? Power is V square. If it is V square, what happens? If I want to compute power, this ratio will be reduced to 10. Okay, so not ratio. This value will be reduced to 10. Why? Because if I want to compute power, power is equals to V square. Correct. Now, if power is equals to V square, so how do I compare it? So if I take the ratios here, essentially what happens is, if I take the ratio of V square and V square, right? Let's say V square into some value, V square by R1, and then V square by R2. So what happens if I do 20 log this, right? What will happen? This will become 40 log something, right? Because there is a power property of log, so it will become 40. I don't want that. I want this to be 20 only. So what will I do? I will reduce the multiplication factor. So that is the reason, intuitive reason why we multiply by 10, not 20. But that's for a separate discussion. Let's not go into that. So your power formula, power gain formula or power loss in decimals is 10 log of P out over whatever is the power reference power, right, that I am comparing to. In this case, we are calculating the power loss in decimal. So it will be 10 log power loss. P loss is what? 5% of the supplied power. So supplied power is my reference. So it will be 5% of the supplied power. So 5% basically means it will be 0.05 into the supplied power PS upon the reference, that is PS itself. So it is 10 log 10 log 0.05. This will be minus 13, right? Now the thing is, because they have already mentioned it to be power loss, right? They have already mentioned this to be a power loss. So we already know a power loss. So specifically in the power loss formula, an additional negative sign is there just to mitigate this. Okay, I do understand this is too much to remember, but what can you do? If they have asked this, what can we do? We'll have to remember this. So this will be negative, right? So this will become plus 13. That's all. Because we already know it is power loss. We already know it is power loss only. Okay. So you will add an extra negative sign just to make this. This negative sign comes because it is mentioning that it is a power loss. But if you know already it is power loss, I don't need to mention this with the negative sign. That's why this will be plus. That's why your answer will be plus 13, not minus 13. So just be careful here. You can go wrong here. Okay, in many ways. So let's solve the next question. So this is the next question where you have been given the line parameters. It is a long transmission line because it is 400 kilometers and it is represented by nominal pi model. So if it is represented by nominal pi model, so we'll have here Z, I will have here Y by 2 and Y by 2. Okay. So I have Y by 2 and Y by 2, and yeah, so with the magnitudes of the sending end and the receiving end voltages of the line denoted by Vs and Vr, okay, maintained at 275. So magnitude of the sending and receiving end voltage both are same. Magnitude of Vs is equal to magnitude of Vr, that is equals to 275 kilovolt. It is a line voltage, right? So the phase voltage will be 275 divided by root 3. Okay. The phase angle difference between Vs and Vr required for maximum possible active power to be delivered to the receiving end would be. What is the phase angle difference between Vs and Vr? Do you remember? So this was the active power formula, right? And the phase angle difference, that is this, they are talking the phase angle difference between Vs and Vr, that is actually equals to delta, right? And in this case they are defining it with theta. So for maximum power transfer, your delta must be equals to beta, that is your theta must be equals to beta. And what is your beta? Beta is nothing but basically what is beta is the angle of Z basically. beta is the angle of z. Okay, so we have to calculate the z. Okay, so beta is the angle of z, we will have to calculate the z. That's all. Beta is angle of z and we'll have to calculate the z. Okay, because in nominal pi model we have to calculate the angle of this particular b element, and b element is nothing but z, right? So I don't need to compute z. Z also you can compute. Okay, for a long transmission line you can compute z. You don't need to compute, all you need to compute is angle of z. Okay, you need to compute angle of z, it is beta. Beta would be what? Beta would be x by r. Okay, so and don't worry, they will not let you remember this big form. They will use something easy, so they are not using this much, right? They are only concerned about the angle. Okay, they are only concerned about the angle, and this beta is a different thing. Okay, don't get confused by this beta. Okay, so I need to compute the angle of z. It is simply r plus jxl, right? So this will be tan inverse omega into L. Everything is in per kilometer, so it won't matter for us, right? Omega into L. Omega is 2 pi into 50 into L, that is 1 milli Henry. Ten raised to minus 3 upon 2 pi f into 10 raised to minus 3, that is milli Henry. 2 pi f L, 2 pi omega, 2 pi f L divided by R. R is 0.035, correct? So if I compute this, what will be this value? This will be equals to 100 into 10 raised to power of minus 3. Hold on a second. 100 into pi into 10 raised to the power of 3 divided by 0.035, 10 inverse. So your beta comes out to be 83.643 degrees. That is what your beta is equals to, right? Okay, so yeah, that is what your beta is equals to. Now let us solve, right? What do we need to solve? This is our answer. We don't need to solve anything, this is our answer. Okay, so beta must be equals to your theta for maximum power transfer. This is a derivation. So yeah, this is your answer, that's all. This is your answer. So your answer is this. Okay, so it is 83.64, 83.64, right? Let's solve this question, right? Again, pretty interesting question. The figure shows a single line diagram of a 4-bus network. The branches B1, B2, B3 have impedances. So B1 has an impedance of 4Z, B2 has an impedance of Z, B3 has an impedance of 2Z. Everything is in per unit, and B4 has an impedance of 4Z. The current, remember, with Z is equals to R plus Jx, the current drawn from each load bus is marked. Okay, you can see the current drawn. That is IPU. If the network is to operate with minimum loss, the branch that should be opened. Okay, which branch shall be opened if I want to operate in minimum loss? It's very simple. Just open one branch and check what is the loss in the line. So let's say if I remove B1, right? If I'm removing B1, this is taking how much current? I, right? So the I current must come from here. Already this is taking I, this is going I. So incoming current here should be 2I. And here another I current is going. So here the current should be 3I. Okay. So B2 is Z. So Z into three I square. Okay, that is what your power loss here. Okay, not Z actually, it will be Z is R plus Jx, right? So let's assume that I is I does not have any angle, it is unity power factor. So it will be 3I square into R plus B2 is R, right? Yes. Then 2I square into this is 4R plus this would be uh, 2R into I square. Okay, that's all. So here the total losses is, if I take the R common, this will be R into I common, R into I square common, this will be 9 plus 4 into 4, that is 16 plus 2. So it is 25 plus 2, that is 27 R square. Okay. So it is 27 R square. So similarly you can solve for let's say now if I want to remove line B4, now what will happen? Or let's say if I want to remove line B2. So what essentially happens, right? If you remove one of the, so you have to choose the minimum impedance path. So if I remove this line, so 4Z is reduced. So actually this is actually good. This is good. Either you want to remove this line or this line, right? Because these have the highest impedances. Okay. So actually removing this this won't help much, because there will be 3I amount of current that will flow through this, that will have huge losses, right? So there is no point in solving for this. Let's try to reduce, let's try to remove this. Okay, let's try to remove this B4. Okay, if I remove B4, then what will happen? Then this will be B2 will be Z, that is R again. So how much current will flow? So from here I current will flow, from here 2I current will flow, right? And from here I current will flow again. So this will be I square, and this is Z, right? This part is Z, 4Z. So this is Z, this is 4Z, this is 2Z. So I square into R plus 2I square into 4R plus I square into 2R. Five I square plus 7I square R. Okay. So it seems this has the least amount of losses, right? If I'm not mistaken. So this is 2I will come from here, I and I 2I. This is going I, so this is 2 square 4. Sorry, this is 4 into 4, right? So this is 16. 16 plus 3, that is 19 R square. 19 I square into R. Okay. Now this can be correct, but let's try to see the last one. Let's try to remove this one. Whether removing this one helps us or not. Okay. So this will be last one which will remove. Certainly we know that removing this won't help us. Certainly we know that, right? You can check it, obviously. You can in the exam hall, actually I will check it. Okay, I will not take any risks in the exam hall. I will check everything. So this will be I, this will be 2I, this will be I. This is best actually, because through the 4R resistance, if you see, 2I current was flowing, but now I current is flowing through the 4R here, I current is flowing through the 4R here. This is best configuration, and 2I is flowing with R. So here I will see the least possible loss, which can be verified as well. That will be I square into R, this has a impedance of Z, this has impedance of 2Z, sorry, yeah, this has impedance of Z only, sorry, this has impedance of 4Z, this has impedance of 4Z again. So this will be I square into 4R, right, plus 2I square into R plus I square into 4R again. Okay. So this would be equals to 8R plus 4R, that is simply 12 I square R. That is your answer for the question. This is least. Okay. So this should be your answer for the question. Okay. So 12 I square R is the least. So you will have to remove B3. So B3 is present in option C. So option C would be your answer for the question. Let's solve the next question. So for the three-phase bus lossless power system network, so all of them are lossless, they are purely inductive. The bus voltages at all the buses are 1 pu. The phase difference, uh, the phase differences of the voltage phase angles are very small. So there is literally very small phase difference between the bus voltages. Alpha, beta, gamma, and x. Okay, x all are strictly positive. The bus injections P1 and P2 are in PU. Okay, the power are in PU. If P1 is equals to M P2, P1 is equals to M P2, where M is greater than 0 and real power flow from bus 1 to bus 2 is 0 pu, then which of the following options is correct? So there is no power flow between bus 1 to bus 2. Okay, uh, and so gamma is equals to M into beta. Gamma is equals to M into beta. Beta is equals to this. So which are the following options? So it can be a MSQ as well. Okay, pretty interesting. So they're telling me that no power is flowing from bus 1 to bus 2. Certainly no power is flowing from bus 1 to bus 2. Okay, and the phase difference is very small between all the magnitudes of the buses, right? So only power is flowing from here to here, right? So if no power is flowing from bus 1 to bus 2, so what will be the power flow from here to here? That would be, so let's assume, even though they are very small, let's assume some angle. Let's assume one angle delta 1, one angle delta 2, and one angle delta 3, and we know there is no power flow from bus 1 to bus 2. Certainly if the voltage magnitude are same and it's inductive lead, certainly delta 1 would be equals to delta 2. Otherwise there has to be some power flow. If delta 1 and delta 2 are not equal, then certainly there will be no power flow from bus 1 to bus 2. Now let's come to this. They are telling me that power is flowing from here to here, right? So what is the power flow equation? So what is the amount of power flowing from bus 1 to bus 3? So no power is flowing here, so this will be P1. So P1 amount of, all of the P1 amount of power is flowing from bus 1 to bus 3 only. So P1 would be equals to Vs Vr by x. So 1 into 1 by x. What is the x? X is beta into small x. Beta into small x into sine of delta 1 minus delta 2. Basically the phase difference. Delta 1 minus delta, not 2, sorry, delta 3. Similarly, whatever is the power, right, none of it is flowing from bus 2 to bus 1, all of it is flowing from bus 2 to bus 3. So it shall be, P2 shall be 1 into 1 divided by, what is this, gamma into x, sine of delta 2 minus delta 3. Now they have given me this relation that P1 is equals to M into P2. So certainly what I can say is P1 equals to M into P2. So I can replace my P1 with this value, correct? And I can replace my P2 with this value, that is 1 only. This is 1 only, right? 1 into 1 is 1 only. Okay, I should not put x here, otherwise you will be confused. I should put dot. So this should be 1 into m. Now one thing is certain, that delta 1 and delta 2 are equal. So this will be delta 1 only. So this thing will be cancelled. So from here x and x also will be cancelled. It is non-zero. They have told me x is a m is greater than 0. Your x also will be some positive. They have told me these are strictly positive. Okay, strictly positive. So it cannot be 0, right? So from here I can directly say that your gamma would be equals to m into beta. Okay, m into beta. Gamma is equals to m into beta. That is present over here. Now, can I get a relation between alpha? No, I will not be able to comment regarding the relation between alpha. So only I can comment about one relation. Okay, so gamma is equals to m beta. So option A is absolutely correct in this question. Okay, cool. Let's solve the next question. This is the next question. Consider a distribution feeder R by X ratio of 5. Okay. At the receiving end, a 350 kVA load is connected. The maximum voltage drop will occur from the sending end to the receiving end when the power factor of the load is what? So do you remember when my voltage regulation is maximum? Do you remember it? It is basically what? When it is minimum. It is minimum in case of leading load, when my load is leading, and when the angle, power factor angle phi is equals to tan inverse R by X. Correct? So when it is tan inverse R by X, then we get a what do you call? The minimum voltage regulation. At this particular power factor angle, we get minimum voltage regulation, right? Okay. Now, when do we get maximum voltage regulation? When my power factor angle voltage regulation is maximum when my phi is equal to tan inverse x by r. Okay, this is the condition basically. How can you derive it? So yeah, of course you can derive it, right? You can of course derive this x, yeah, x by r, yes. So there is a derivation. So if you remember, your voltage regulation is equals to RPU cos phi r plus minus XPU sin phi r, right? So voltage regulation will be maximum when I will choose the positive sign, of course. I will not choose the negative sign. So if I choose the positive sign, right? So that means I have chosen a lagging load. So you can differentiate your voltage regulation with respect to phi r, because we have to find out the condition for the power factor angle. So this would be equals to minus RPU sin phi r plus XPU cos phi r, and this will be equals to 0. If I equate this equal to 0, so I get tan phi r equals to XPU by RPU, right? If you just multiply by Z base, you will get back to this equation and then take the tan inverse. So this is the condition for maximum voltage regulation, and the minimum voltage regulation will happen when I will choose a negative, right? If I choose a negative, then voltage regulation will be minimum. That is, what is the minimum value of voltage regulation? That is 0, right? So if I choose the negative number, then my voltage regulation will be 0. That voltage regulation will be 0. That is the minimum value. So from that equation, you will find out your tan phi r. So this is not pu, sorry, this is r, will be equals to, it will be just opposite, RPU upon XPU. Okay. So for minimum voltage regulation, the condition is just the inverse. Minimum meaning this has to be 0, and this can be 0 if I choose a negative number here. That means my load must be leading. Okay, these are the things, but people remember it. If you don't want to remember, you can directly derive in the exam hall as well. Okay, so this is the load power factor angle. So yeah, we have to solve for this. Already what is given to us, R by X is given. So what is X by R? It will be x by r, it will be 1 by 5. So 0.2 tan inverse, so 11.3 degrees. Okay, so 11.3 degrees is your answer for the, not your answer, they have asked you what is the power factor, right? Not your perfect angle. So cos of this would be, so cos phi r would be 0.98. Okay, so yeah, 0.98 is your answer for the question. This is the last question that they ask from transmission and distributions of power system, right? Using shunt capacitors, the power factor of a three-phase 4 kilovolt. So it's a three-phase 4 kV. So your V line voltage is three-phase 4 kilovolt. Drawing a apparent power of 390 kVA and power factor cos phi is 0.77 lag. Okay, is to be corrected to, so we this is the power factor 1. I want to correct this to 0.85 lakh. The line current of the capacitor bank must be. So what is happening? Basically, if I consider just a single phase load, I will have a single phase load that has a power factor now, and that is consuming, that is a power factor of this, right? 0.77. So if I connect a capacitor bank parallel to it, what will happen? So this capacitor bank will actually deliver some amount of reactive power to the load, so that the supply does not have to deliver that amount of reactive power now. So the reactive power delivered by the supply will be reduced, right? So this will be the reactive power delivered by the capacitor, and overall reactive power, this is the QS. Overall reactive power of the load is constant. It is demanding still the same reactive power, but actually what is happening? The capacitor is delivering bit of additional reactive power, so that the supply reactive power delivered has been reduced. Hence the power factor will be improved. So there is derivation and all these things are already there in the YouTube channel. Okay, all these things have been taught, so I will not explain much. Essentially what happens is the additional reactive power that the capacitor needs to send would be P, because power, active power is constant. So basically, right, you know, your tan phi is equals to Q upon P. So what happens is the reactive power, additional reactive power delivered by the capacitor, right, QC, this will be equals to P into tan phi 1 minus tan phi 2, because initially all of this, what is P into tan phi 1? It is basically the QL, right? This QL, this thing is QL, and what is this P into tan phi 2? This thing is QS. So basically your QC is QL minus QS, that's it. Okay, because the supply is now delivering lower amount of reactive power. Okay, from this I will be able to calculate my what do you call, line current. Certainly I will be able to calculate that. So what is the active power? They have not told me what is the active power. We can obviously calculate the active power, right? So active power would be, so root 3 into VL into IL cos phi, right? I know what is my kVA. If I divide this by, if I multiply this by power factor, right? So S cos phi 1 would give me the active power, right? So what is S cos phi 1? So it will be 390 into cos phi 1, that is 0.77, right? So this would be 390 into 0.77. Let me calculate that. 390 into 0.77, that is equals to 300.3 kilowatt. Tan phi 1, so 0.77 0.77 cos inverse tan minus, now power factor needs to be improved to this, cos inverse of tan, this is equals to 0.20088. So this is the amount of reactive power that the capacitor bank will deliver. Remember, this is 3-phase reactive power. Okay, 62.72 kVAR. Okay, this is the amount of reactive power the capacitor will obviously deliver. So from this we can easily calculate what will be the uh, current in the line current of the capacitor bank. What shall be the line current of the capacitor bank, right? So we know this, right? How do I calculate this? So we know reactive power. Okay, we have to calculate the line current. So using shunt capacitor bank, it's a 4 kilovolt induction motor. So the voltage across the each capacitor bank I know. So remember, we will assume this to be star connected. We'll assume our load to be star connected. So if I consider per phase model will be 4 kilovolt by root 3. That is the voltage across the capacitor, and they are asking me what is the line current. So whatever kVA the capacitor will generate, it will be solely due to it will be reactive, right? It will be totally reactive because capacitor does not have a real component. So simply what I can say, your kVA or S base will be equals to, this will be equals to root 3 into VL into IL, because this is a 3-phase reactive power. So what is my kVA? S equals to root 3 into VL into IL. Certainly you know this. Now it is equals to P plus like P square Q square. Okay, P square plus Q square, that is a S, right? Now in our case, the power by the capacitor bank is 0, correct? So if it is 0, then we only have QC. So this will be equals to root 3 into VL into ILC, right? So I know the line voltage already, that is 4 kilovolt, that is given to us, correct? So I just need to compute the line capacitor current, that would be 62.728 upon 4 kilovolt, root 3 into 4 kilo. Remember, kilo will be cancelled. So this will be this divided by 4 divided by root 3. So that is 9.054 amperes. Okay, that will be your answer for the question. Round off to 1 decimal places. So this will be actually 9.1 ampere. Okay, so 9.1 amperes will be your answer for the question. That's how simple and straightforward this question was. Okay, if you know all the concepts, you will be able to solve it in a very easy manner. Okay, so let's solve the next questions, right? So here let's come to the next topic, that is economic load dispatch. So again, this is a very important topic, very important topic. You must not skip this. Okay, you must not skip this, right? Two generators, like every year one question has came, so and very easy, you will be able to solve it. Like there is mainly 2-3 concepts. Two generators have cost functions given F1 F2. They need to deliver a combined load of 260. So P1 plus P2 must be equals to 260. Ignoring the network losses, for economic operation, P1 and P2 must be. For economic operation, basically your del F1, the cost function by del P1 should be equals to del F2 by del P2, that is equals to lambda. So this is the condition for economic load dispatch. This is the Lagrange's derivation. You can go and watch the full course there. All this has been discussed. So this would be equals to 40 plus 0.2 P1, this is equals to 32 plus 0.4 P2. So from here we get the condition that P1 minus 2p2 equals to 8 40 minus 40. So or I can write here 2p1 minus 2p2 minus p1 equals to minus 40. No, plus 40, right? Plus 40. This will go there, this will go there, yes. So yeah, now what I can do, I can add these two equations. If I add these two equations, I will get 3p2 equals to 300. So p2 equals to 100. So p1 would be equals to 160, right? So option B is absolutely correct for this question. Like there is nothing to explain over here, right? Okay, so let's solve the next question. This is the next question. The fuel cost function is given, right? P1 P2 are power plants generated in megawatt. A is a constant. The incremental cost of power lambda is 8 rupees per megawatt hour. Okay, it is 8 rupees per megawatt hour. The two thermal power plants meet the total demand. So P1 plus P2 is equals to 550. The optimal generation of the plants P1 and P2 would be. So again, they have given me the incremental cost of power is 8 rupees per kilowatt hour. Okay, incremental cost is 8 rupees per kilowatt hour. Now if they have already given me the incremental cost of power is 8 rupees per kilowatt hour, I can easily compute my answer. So what is the incremental cost? It is delta C1 upon delta P1, that is equals to, in the first case it will be 6 plus 0.008 P1. Okay, and this is given to me, that is 8 rupees per megawatt hour, correct? So I can easily calculate what will be my P1. So P1 would be, this 2 will get on gas side, so 2 upon 0.008, so this will be 1.0.004. I think this would be 250. So your P1 comes out to be 250 megawatt, hence your P2 will come out to be 300 megawatt. Okay, you can calculate, but I don't think you need to calculate. That is my assumption, right? You can calculate, but I don't think you need to calculate. Already the question is solved. They have already given you the incremental cost, right? You don't need to solve further. So your answer would be 250 and 300, that is present in option B. Okay, let's move on to the next question. Like these questions are very, very simple, not that difficult, but you might have run into problem if they would have given you the limits of plants P1 and P2. If limits are given, right, then you have to be very, very careful. That is there in this question. If limits are given, then you cannot just do this. Okay, limits are given, you have to check. After getting the values of lambda incremental cost, you will have to check whether the maximum value delivered, maximum power delivered by a particular plant is reaching its limits or not. If it is reaching its limit, then you have to stop it. Okay, the expression for fuel cost is given. The limits of working limits of plant 1 and plant 2 is given, where A is a constant. For the given value, for a given value of A, optimal dispatch requires the total load of 290 to be shared between this and this. Okay, so this is the optimal solution for 290 megawatt to be delivered. With the load remaining unchanged, the value of A is increased by 10% and optimal dispatch is carried out. The changes in Pg1 and the total cost of generation, F1 plus F2 would be what? Okay, interesting question. So first of all, they are telling me that in this particular condition, the optimal like we get the optimal sharing if Pg1 and Pg2 are these values. Okay, so let's take it case by case. So let's do it for case 1. Let's do it for case 1. So if we do it for case 1, what will you get? That we have to deliver, we have to share 290 megawatt of load Pg2. Okay, Pg1 plus Pg2, right? So so uh, also the optimal values are given. So if optimal values are given, that means that if I differentiate my cost function, that is equals to 0.2a Pg1 plus 40, this should be equals to the optimal cost of the second function. This will be 0.4 Pg2 plus 30. Okay, so now we know both of these will be equal, correct? If it is optimally if there is optimal solution, both of them will be equal, and already I know what is my Pg1 equals to, right? So okay, let me do this. Both of them are equal. If both of them are equal, that means 0.2a Pg1 plus 40 is equals to 0.4. Okay, I forgot to write the a here. A Pg2 plus 30. So let's calculate a basically. So what is a? So Pg1 and Pg2 we know the values, right? Pg1 is 175, Pg2 is 115. So 0.2 a into 175 minus 0.4 into Pg2. Pg2 is 115. That is equals to basically minus of 10. So from this actually we can compute what will be your a. So this shall be, let me compute this value. This will be 175 into 0.2 minus 0.4 into 1.5. So your a comes out to be 10 by 11. Okay, now they're telling us that they are incrementing a to a dash by 10%, that is 1.1. So this shall be 1.1 into 10 by 11, so that will be this divided by 10. So this will be a dash will be exactly equals to 10. Okay, so a dash is 10, right? A dash is 10. So now if we solve, if we now if I again put this a dash in this equation, right, because ultimately a will be replaced with a dash, so both of them will be equal. So this will be 0.2 into 10, that is 2 Pg1 is equals to 2 Pg1 plus 40 equals to 4 Pg2 plus 30. So I can say that 2 Pg2 minus Pg1 is equals to 5. And also obviously we know both of them are delivering the same amount of like same load, so that this is still equals to 290. So now if I add these two equations up, I'll get 3 Pg1 3 Pg2 will be equals to 295. So 295 divided by 3, that is 98.33 megawatt. Okay, and your Pg1 would be 290 minus this, that is 191.67 megawatt. So previously what was the case? Previously if we saw that your Pg1 was 175, your Pg1 has increased and your Pg2 has reduced. Okay, so yeah, Pg2, hold on a second, let me check if I'm doing everything correctly or not. Okay, sorry. Pg1 is this, Pg2 is this. So Pg to Pg1 has increased. Yeah, Pg1 has increased. Pg1 has increased. Uh, yeah, Pg1 has increased and your Pg2 has reduced. So Pg1 has both Pg1. Now what will happen to F? So of course, if A has increased, right? What will happen to F? F also will increase. I mean, so this value is constant. Okay, here Pg1 has increased, but Pg2 has reduced. So actually, we might need to calculate it. So let us compute actually. So previously, what was your F, right? So previously, F was F1 plus F2. So ultimately, all we are concerned about is this part because this is constant, right? All we are concerned about is this part. So if I add these two, let me compute. So F will increase certainly, right? F cannot decrease. If the incremental cost has increased, F will increase. Certainly F will increase. You can verify that, but I know F will increase. So I will obviously tick mark this, but if you want, you can put the value, right? You know the value of A, you know the value of F, Pg1, Pg2, whatever we have computed here, you can easily put that there. Correct? You can easily put that there. Now let's solve the next question. I certainly know, so option A will be the correct answer. The incremental cost curve, just give me 1 second. This, sorry, Pg1, sorry, option B will be the correct answer, right? Both Pg1 and F will increase. Okay, both Pg1 and F will increase. Intuitively, can we make sense of this? So previously this was 175. So what was happening was 14 to Pg1, right? So what was 14 to Pg1 and what was this? Okay. Yeah, I think you can make sense of this, but let's solve the next question. Option B is the correct or answer. The incremental cost curves of two generators are shown. This is the incremental cost curves, right? As the plant supplies a common load, if the incremental cost supplying a common load at 7,400 rupees 7,400 megawatt per megawatt, okay, then the common load in megawatt is, okay, so this is a generator B, this is a generator A. If the incremental cost of supplying the common load is 7,400 per megawatt, okay, then the common load is equals to what? How do I compute this? uh okay, the incremental cost overall, they're talking about the overall incremental cost, right? Overall incremental cost of the system is 7,400 megawatt, okay. So if the overall incremental cost of the system is 7,400 megawatt, then uh, what is the common load, right? So we can obviously plot the incremental cost function, right? We can plot the incremental cost function. So what is my incremental cost function for generator A? So I can plot y equals to mx plus c. So what is the slope of generator A? Slope would be dy upon dx, right? So what is the change in x? That is 150, sorry, 160. So it is 160, and what is the change in y? So this is actually 3000, right? Approximately this is 3000. Okay, so this we got, and plus is this 3000. So this seems this is approximately 3200, right? There are 5 divisions. This will be approximately 3200, right? Not exactly 3000, just to make it proper. Although they should have properly mentioned it is 3200, but that's fine. Into obviously slope into the x axis, that is Pg1. Plus the y intercept. So at 0 it is 8000. So plus 8000. 20 PGA. Okay. What about incremental cost of plant B? So incremental cost of plant B, that is this. So again there is, this seems this is like not half, but this will be some multiple. So I'm changing my load to again 160. So this will be 12. So again what is the delta? Delta is 6000 to 12,000. Okay. So 160, 6000 to 12,000. It will be 12,000, somewhat 12,000. It seems it is 12,400, something like that. Correct. So the change in X is 160. Sorry, not 12,000. Sorry, 6,400. Okay, because if you see, this is exactly half, right? So it is just below the half. So just trying to make a multiple round figure number, although all this will not match. If you all this won't matter. If you say this is 6,500, then also you will get the correct answer. Okay. 160 PGB plus the Y intercept, that is 6,000. Correct. So this will be actually 40. That is what your ICB is equals to, right? So nothing is mentioned, so we'll assume it is operating at economic load dispatch. We'll assume that. So they have mentioned that the incremental cost is this, so we will equate that, right? So if they are operating at incremental cost, so that means your ICA will be equals to, they are operating at economic load dispatch, that means your ICA will be equals to ICB, that will be equals to 7,400, right? And if you make that 7,400, what will be your ICA? So your ICA will be coming out, sorry, your PA, right? Your PA will be equals to, this will be minus 600 divided by 20, that is minus 30, which is a problem to us, right? PA cannot be negative, right? PA cannot be negative, PA has to be positive, because they have given us the minimum limit of PA, right? That is 0. It goes from 0 to 160, right? So it cannot be negative, so we will have to choose the minimum value of PA. So PA will be 0. For most economic load dispatch operation, if it is telling me that P has to be negative, right? So P has to be minimum. PA cannot go below 0. So for economic load dispatch, I will have to choose PA equal to 0. This concept has been explained in PSA. You can watch that. Like, I think it's there in the YouTube video, so you can watch these things. Okay. So this is PA. What about PB? So again, if I equate the incremental cost, ICB, this will be equals to 40 PGB, right? 40 PGB equals to 6,000. So and your incremental cost is 7,400. So it will be, your PGB would be equals to 1,400 divided by 40. Okay. So this comes out to be 35 megawatt. So basically what load they are delivering, common load, both of them will be PA plus PG. PA is equals to 0, PB is equals to 35. So overall they are delivering 35 megawatt of power. That's it. That's how you solve this. Okay, so the answer would be 35 megawatt in this question. Let's solve this question. Okay, this is the next question. I think this is the last question. Two units rated at this and this are enabled for economic load dispatch with overall incremental cost to this. So they are enabled for economic load dispatch. So incremental cost is already given to me, that is 10,000. The units are dispatched to P1 equals to 50 megawatt and P2 will be equals to 80 megawatt at overall incremental cost. So let's say this is lambda dash of 10,000 600 rupees per megawatt hour. The power output of the units is 80 megawatt. P1 dash is 80 megawatt and P2 dash is 92 megawatt. The total plant megawatt output without overloading any unit at an overall incremental cost lambda double dash of 11,800 rupees would be. Okay, so if they are operating at economic load dispatch, I know basically lambda 1 would be some A1 P1 plus B1. It depends like this, right? And lambda 2 incremental cost for the plant 2 would be some A2 P2 plus B2, where A1 and A and B are constants basically. Okay, so in lambda dash, right? So in the case 1, your A1 P1 plus B1 would be equals to your A2 P2 plus B2, right? Because they are operating in economic load dispatch, the incremental costs will be same. That will be equals to 10,000. And I know what is my P1 and P2 values. Okay, I will put those values later on. Let me just comprehend what the question actually is asking. The units are dispatched at 50. Now, if the overall incremental cost of the system is increased to 10,600, right? Then obviously P1 will change, P2 will change, correct? This will become, this will be equal, and what will happen is P1 will become P1 dash. So let me put the P1 values and P2 values, that will be easier for us. So this will be actually equals to initial case P1 is 50, P2 is 80. 50, 80. And in the second case P1 is 80, P2 is 92. Okay, and in the third case, right, in the third case they are asking me what is the value of the overall total planned output, right? So I need to calculate P1 and P2 in this case, plus B1 equals to A2 P2 plus B2. I will need to calculate P1 and B2 if it is given that uh, the incremental cost is 11,1800. So of course, if you see, I have two equations, right, and two unknowns. So I will be able to comment on what is my A1 and B1, correct? So that, let's do that. So basically, right, what will be the solutions? So if I look at this equation in isolation, this is the equation in isolation. There are many ways to solve this. Whichever way you find it suitable, you can do it. So how do I solve this, right? So we can subtract 1 from 2. So I will get A1 into 30 will be equals to 600. So A1 would be equals to 20. A1 would be equals to 20, right? Yes. Now A1 is 20, so simply I can put here in this equation. So if A1 is 20, what will be your B1? B1 would be, this is 20, so this is 100 into 2, 1600, 1600 minus that, so B1 comes out to be 9000. Okay, that is what my B1 value is. So we got our B1 value, we got our A1 value. Similarly, if I solve for this equation, correct, again I will directly solve now. So if I subtract 1 from 2, I will get 12 into A2 is equals to 600, correct. So your A2 is equals to actually 50. So if A2 is 50, right, this would be 50 into 80, right, that is 40 into 100, that is 4000. So B2 comes out to be 6000. So now we can simply put in this equation, so E3 is 20, P1 plus B1, B1 is 9000, that is equals to 11800 given to us, right. So this will be 2800, 2800 divided by 20. So this would be P1 would be equals to 140. Is 140 within my limits? Let me check. 140 is within my, okay, it is not within my limits, right, because P1 is supposed to be the first plant. So we are getting 140 is not within my limits, which is greater than my limit. So of course I will have to choose the maximum value, because incremental cost for economic load dispatch, it is telling me choose P1 to be 140. That is not possible. So choose the maximum value. It is telling me P1 must be high. So choose the rated value. So P1 would be equals to 100 megawatt. Okay. Now if P1 is 100 megawatt, okay, what about the plant 2? What about the plant 2? So for the plant 2, if I equate my equation, so A1 is 50, 50 into P2 plus 6000 equals to 11800. So this would be equals to 4000, sorry, 5800, 5800 by 50. So 580 by 5, that is 100 and 114, 116. So P2 is equals to 116 megawatt. That is what our P2 is equals to, which is lying within our limits. We don't have any problems in this case, right. So 116 is within our limits. So overall load shared would be P1, that is 100 plus 116, that is 216 megawatt. This will be your answer for the question. This was a good question, okay, good conceptual question. So with this we are done with economic load dispatch. Now we will begin with the third part of PSA, that is circuit breakers, relays and power system generation. Let's start with the third part of PSA, that is power system protection and generation. So this is the first question, okay, where the overcurrent relays are shown, RA, RB, and we have loads connected. You can see 300 amperes, 200 amperes, 100 amperes, correct. Uh, the relays are IDMT in nature, having these characteristics. According to plug setting multiplier and time setting multiplier, the maximum and minimum fault currents at bus B is 2500 ampere. So minimum fault current in bus B, minimum fault current in bus B is is what, uh, minimum fault current in bus B is 500 amperes, okay. And what are they telling you? They're telling you that uh, the maximum fault currents are 2000, okay. assuming the time setting multiplier and plug setting, okay, they have not given you the plug setting multiplier, they have given you the plug setting to be 5 ampere. The plug setting is 5 ampere and time setting multiplier is 0.1, that will be put here. The operating time of relay RB would be, what is the operating time of relay RB for, obviously we will compute for the maximum fault, right? Whenever the highest fault current occurs, what is the operating time? Okay, so basically when a fault current of 2000 is flowing through the relay primary coil, what is the fault current? So relay setting is given, right? That is 5 ampere. What does relay setting means? So let us first say what is the overall current delivered by the generator. It should be 500 amperes. Why should be 500 amperes? Because 300 is flowing here, other 200 will be flowing here, right? So not 500, sorry, 600 actually. So then 300 will be coming from here, right? Then out of this 300, 200 will be flowing to this load, 100 will be going to this load. So what can I say? So the relay RB is there to protect the line. So relay RB protects line BC, right? So RB will protect the line BC, correct? So if RB protects the line BC, and if I know that the, so plug setting is given as 5 ampere, right? Plug setting is given as 5 ampere. This is nothing but the pickup current, I pickup of the relay B, that is 5 ampere, right? In the secondary, I pick up in the secondary, right? Secondary. Okay. Now, if it is used to protect the line BC, so you want your relay to operate when the current exceeds a certain value. So when your current will exceed 100 amperes, of course you will want your relay to operate. So my pickup current on the secondary should be equal to 5 ampere when the relay current is greater than 100. That is, then the CT ratio would be 100 by 5, correct? So from this you get the ratio of the CT, that is 20. Okay, so you want your relay to operate when obviously this load current increases higher than the 100 amperes threshold. Okay. Now they have told you that minimum fault current is 500 ampere, that is fine, but this calculation was used to calculate the CT ratio. Now if you know the CT ratio, now you can easily calculate for what is the plug setting multiplier for the highest fault current, right? When the fault current is highest, right? What is the definition of plug setting multiplier? It is the relay fault current in the secondary coils of the relay, right, upon the pickup current. So what is the fault current in the secondary coil of the relay? If it is 200, right? So if I convert it into the primary, it will be 2000, so not 200, 2000 by 20. So 2000 by 20, this is the secondary relay fault current divided by the pickup current, that is given as 5 ampere. So this will be equals to 2000 by 20, that is 100 by 5, that is 20. Plug setting multiplier is coming out to be 20. Okay. Now you can put your value. T operating. T operating would be 0.14 into 0.1 upon 20 raised to the power of 0.02 minus 1. So this, right, if I solve this, 0.14 into 0.1 divided by 20 raised to the power of 0.02 minus, okay, hold on, 20 raised to the power of 0.02 minus 1 into 0.1 into 0.14. So this comes out to be 0.2267 seconds. Okay, so this will be your answer. I do agree there are a lot of things that are not mentioned here that you have to assume. So this was an old question, so I'm assuming in recent years they will not like keep you in the blue, basically not mentioning what does each terms mean. So plug setting is not a standard term. Okay, pickup current is a standard term, current setting is a standard term, PSM is a standard term, time setting multiplier is a standard term, right? So these things are not standard, so don't worry if you are not able to solve this question. I don't think nowadays this kind of question will be asked. They will define everything properly. Let's solve this question. The total impedance of the secondary winding, leads and burden, uh, uh, winding and leads and burden of a 5 ampere CT is 0.01 ohms. Okay, these are total impedance. If the fault current is 20 times the rated primary current, that is given here, right? Of the CT, the VA output of the CT would be. So they want me to calculate the volt ampere output of the CT. If I know the rated, if I know the fault current is 20 times the primary rated current. Okay, if fault current is 20 times the primary rated current, then the V output of the CT during the fault, that is what they mean. During the fault, what will be the V output of the CT, right? It is very simple, right? What is burden? Burden is the volt amperes. So we can assume this to be the power, that is I square into R. So if the primary is 20 times the rated, like if the fault current is 20 times the rated primary current, so will be the, so the secondary current also will be 20 times the rated secondary current, and rated secondary current is given to me, and the secondary impedance is also given to me. So this will be rated secondary current, that is 20 into 5 whole square, 20 times the rated secondary current whole square into 0.01. So this would be 100 into 0.01, that is 100 volt ampere. So 100 volt ampere would be your burden of the transformer when it is when rated primary, when fault current is flowing through the primary, that is 20 times of the rated primary current. Okay, this is the answer for your question. Let's move on to the next question. So this is the next question where a lossless transmission line with 0.2 pu reactance per phase is uniformly distributed along the length. Okay, so the reactance of a lossless transmission line, only reactance is distributed, and that is actually equals to 0.2 per phase throughout the whole length. 0.2 per phase, uh, that is distributed throughout the whole length. Okay, 0.2 divided by L, right? The connecting a generator bus, so I have a generator bus here to a load bus, and here I have a load bus. Correct. Now is protected up to length 80% of its distance by distance relay placed at the generator bus. So if I have a relay placed here, so it will protect 80% of the distance. So how much distance will it protect? So distance will be defined by the impedance, right? Because it's an distance relay, and in a distance relay we define the protection zone by impedance. So if the overall impedance is 0.2 and I want to protect 80% of the distance, that means it will protect till the point, till the impedance 0.2 into 0.8, right? That is the range of my distance relay. So Z, the impedance, the maximum impedance that it will see is 0.2 into 0.8, that is 0.16. Okay, the generator terminal voltage is 1 pu. Generator terminal voltage is 1 pu, and there is no generation at the load bus. The threshold pu current for operation of the distance relay for a solid 3-phase ground fault closest to the transmission line is. So my distance relay is supposed to protect till the point my impedance is 0.16. So till this point, right, somewhere here, they are asking me if a fault occurs, three-phase fault occurs closest to the transmission line, like what will be the threshold current, right? This is the minimum amount of current that the distance relay can detect. I will explain this question again, don't worry, after solving this. So it can protect till 80% of the line. So if it protects till 80% of the line, right? So till this point there is a three-phase fault. If there is a three-phase fault, what will be the current? Current would be this 1 pu, that is a voltage. I can convert this whole distributed impedance into a single impedance, concentrated one, that is Z equals to 0.16. I will explain again this, don't worry. Remember, it is a lossless line, so it is actually J. Don't forget, it is not real, it is J. J 0.16, and then there is a three-phase fault, and they are asking me what is the current in this case. What is the like minimum? So this whatever current will flow, the same current will flow through the CT, and everything is in per unit. So it does not matter whether I am in secondary or primary. Okay. So they are basically asking me what is the fault current in this case, and this is the minimum fault current for which the relay will operate. It will not operate if the fault current is lower than this. I will explain, don't worry. So here the fault current is, this is 1 angle 0 degree. I1 is equals to 1 angle 0 J0.1. This is so 1 divided by 0.16, so 6.25. okay, and so your magnitude of current would be 6.25 pu. This is the minimum amount of threshold current. Let me explain it again. So first of all, there is a uniformly distributed line which has the impedance uniformly distributed over it. Now they are telling me that relay protects only 80% of the distance. What does it mean? What do I mean by 80% of the distance? If relay protects only 80% of the distance, that means relay will protect only 80% of the line, correct? If it protects only 80% of the line, what is the minimum fault current? That is they are asking me, right? Because they are asking me if a fault occurs nearest to the transmission, nearest to the load, when can my relay detect? Relay can detect if the fault happens somewhere here. If it happens here, relay will not be able to detect. Why? Because let's say the fault has happened here, right? What is the fault current? It will be let's say the fault has happened here. What is the fault current? It will be 1 divided by this whole impedance, that is 0.2. So your IPU comes out to be 5 pu, correct? Magnitude. Now this is a problem because my relay is supposed to protect till 80%, right? And if there is protection till 80%, we have just calculated that relay will operate for a current of 6.25 pu. If the fault occurs here, the current reduces, right? And relay will not be able to operate. That's why this is called as the threshold current of the relay. Below this, the relay will not operate. It is just like the pickup current of the relay. If the fault occurs here, let's say 50% of the line, what is the impedance seen? It is 0.1. And what is 1 by 0.1? It is 10 pu. So of course, if the relay is operating at 6.25, of course it will operate at 10 pu. So that is what they mean by distance protection. Okay, very simple, very easy to understand. I have just tried to explain it again. So let's solve the next question. This is the next question. The most commonly used relay for protection of alternator against loss of excitation, again theoretical point, we use offset Moore relay. Okay, like there are many characteristics, there are many mathematical things. How many things will you remember? So you just know that we use offset Moore relay for protection against alternators. There are a few more protections. You can see for what reason we use overcurrent differential relay, Buckles relay. Buckles relay is also used in transformers, right, for when the oil level is low. So all these things you can see, and most probably they will not ask this, but if they ask, you have to answer. It's a theoretical point. Okay, now the next question, this is the next question. For the three-phase power system bus shown, the trip signal circuit breakers B1, B, all this have overcurrent relays R1 till R9 respectively. some of which have directional properties also. The necessary condition for the system to be protected for short circuit fault at any part of the system between bus 1 and any of the RL loads with isolation of minimum portion of the network using minimum number of direction relays is, and there are 4 options. Obviously one of them will be correct. R3 and R4 are directional overcurrent relays blocking fault towards bus 2. So they are telling me that R3 and R4 are directional overcurrent relays. Everywhere I see R3 and R4, R3 and R4, R3 and R4, R3 and R4. So certainly R3 and R4 are directional overcurrent relays. Okay. Now they are certainly directional overcurrent relays. Now what is the direction? How to solve this? We'll see. So this option is bit simpler. Let me read another option, right? R3, R4 are directional overcurrent relays blocking fault towards bus 2. R7 is directional overcurrent relay blocking fault towards bus 3. So R7 is here, right? So does it need to be a directional overcurrent relay? Does R3 need to be a directional overcurrent relay? It protects the fault towards bus 3. So certainly we know current in bus 7, right? Current will flow only in one direction. Current will only flow in one direction. So do we need to provide a directional relay here? Whenever there is a possibility that current can flow in both directions, there only we need to provide directional relay, because directional relay are costly. Directional relay are costly and we will lose out on some other feature, right? If you are implementing the directional feature, we will lose out on something else. So directional relays are costly. And they want to use minimum directional relays as much possible. So we will use directional relays in those cases only where currents can flow in both directions. Because if current is flowing in both directions, maybe I would only want to eliminate the fault if current is flowing in a particular direction. I will explain. Okay. Otherwise, use bidirectional, because we don't need to add this feature if we know that current will only flow in one direction. Now for this RL load, is there any possibility that current can flow from load to the source? No, no possibility. So this will have a bidirectional relay. This will have a bidirectional relay. Okay. This will have a bidirectional relay. Correct. Now they are telling me that the R7 must be directional. No, R7 need not be directional, because I know current direction will flow from here to here only. It will flow from source to load only. Similarly for generator, if I see, current direction will be from here to here. Correct. It is constant. Generator will supply the power. It will not absorb. So current direction will be leaving. So certainly this also does not need a directional relay. This needs a bidirectional relay. Okay. Now for B6 as well, certainly I know this also will need a bidirectional relay. Now for B5 as well, you see that current can only flow from here. Okay. Current will flow from here to here. Correct. For B5 as well, I will need bidirectional. So the confusion is only in B1, B2, B3, B4. In B1, if you observe, if a fault is occurring in line 1, so current will flow like this, correct? And yeah, that's all. Current will flow like this from here. If a fault is occurring in line 2, if a fault is occurring in line 1, right? So one of the direction of current is this. Now, of course, the current can follow this path as well. Correct? Current can follow this path as well. So if a fault is occurring in line 1, I observe current is flowing from left to right from the line 1, and from the line 2 it is flowing from right to left. So in B3, in normal operation, I already know current flows like this. During faulted operation, current is flowing like this. left to right. Let's see what happens when a fault occurs at line 2. If a fault occurs at line 2, current will flow like this in line 2, and in line 1 current will flow like this. So if you observe in B3 and B4, if you observe properly, current is flowing in both directions during faulted operation, right? So we, in case of B3 and B4, we will have to use a directional relay. Why? So B1 already eliminates the point when a fault occurs in line 1, this will trip. So B1 is there for protection of line 1, right? B3 is there for protection of line, isolate the system, isolate the line 1 from line 2. That is the purpose of B3, because current is flowing in this direction. That's why B3 have to be provided with a bidirectional feature, correct? If a B3 has to be provided with a directional feature. If B3 has a bidirectional feature, it does not make sense, because B5 is, let's say a fault is occurring here. So for that fault, B5 is already protecting, huge current will flow, and B5 is there to protect that. I don't need B3 to protect it again. So it's a overlap, right? That's why B3 must be bidirectional. Okay. So B3 and B4 must be bidirectional. Other relays, they need to be bidirectional. So that is not B3, sorry, R3 and R4. So R3 and R4, whatever I said B3, B4, replace that with R3, R4. That's all. So this is incorrect. This is incorrect. Let's read the third one. R3 and R4 are directional overcurrent relays blocking fault towards line 1, okay, and line 2 respectively. Yes, it is correct. R3 and R4 are blocking fault towards uh, line 1 and line 2 respectively, okay. R7 is directional overcurrent relay. No, R7 is not directional. R3 and R4 are directional overcurrent relays blocking fault towards line 1 and line 2 respectively. Is it correct? So yes, it is correct, right? So here R3 and R4 are directional overcurrent relays blocking fault towards bus 2, line 1 and line 2 respectively. R3, okay. R3 and R4 are directional overcurrent relays blocking fault towards line 1 and line 2 respectively. Is it correct? No. R3 is used to block fault in line 2, and R4 is used to block fault in line 1, right? That is the purpose of R4. So if a fault is occurring in line 1, what will happen? First of all, B1 will trip, that is R1 will trip. Certainly R1 will trip, and your R4 will also trip because it wants to isolate the system from line 1. Okay, so it is written other way around, right? It should be swapped. So this statement is absolutely correct, that R3 and R4 are directional overcurrent relays and they block fault towards the bus 2. Yes, certainly both of them are blocking the fault towards, if a fault is occurring here, so fault current will flow from the bus 2. To block that, to isolate that, R3 and R4 must be directional overcurrent relays. Okay, that is the solution of this question. Okay, pretty interesting, pretty conceptual. Let's move on to the next question. This is the next question. In a 132 kilovolt system, the series inductance up to the point of the circuit breaker L is equal to 50 millihenry, and the shunt capacitance C is 0.05 microfarad. The critical value of the resistance RC for the circuit breaker to be connected for no transient oscillations. So basically, when my system is critically damped, and when my system is critically damped, basically your circuit is converted like this, right? R, L and C. So when is the system critically damped? When my R is equals to 1 by 2 of under root LC, right? You can derive this, but I think remembering the result is the best way to go about it, right? So 1 by 2 into under root of LC. L is 50 into 10 raised to power minus 3. This is 10 raised to power minus 8. So 10 into 10 raised to power 5, that is 10 raised to power 6. So 10 cube by 2, this is 500 ohms. So your critical resistance between the contacts should be critical resistance that should be connected is 500 ohms for no transient oscillations to occur. Okay, that's how simple this question was. Let's solve the next question. Base load plants are what? So we know certainly nuclear power plants are base load. Certainly nuclear power plants are base load. So wherever R is present, we will choose that R is present here. So either option answer will be option C or D. Then we have Q is present in both of them. So Q also, run of river plants also will be base load. Why? Because your river flows continuously throughout the year, so it can operate as a base load. Now, is P correct or not? So P is also can be used as a base load plant because wind farms are wind power plants are there whenever wind is flowing constantly, right? In certain areas, wind does flow constantly, so it can also operate as a base load plant. So PQR will be correct. C will not be correct, right? Your S can never work as a base load. Diesel power plants always we use it as a peak load plants. Okay, so we use diesel as a peak load plants. So your answer would be option C in this case. Theoretical question, and this is a very old question. I don't guess they will ask anything recently from here. Now this question: which of the following options is /R correct for automatic generation control AGC and automatic voltage regulation AVR installed in synchronous generators? Okay. So what does AGC do? Automatic generation control, basically it controls the power generation, right? How do I control the power generation? It controls the steam input of the synchronous generator. Okay, if you remember, we have studied droop characteristics. So in droop characteristics, you know that whenever the power increases, the frequency reduces, right? Not a lot, but it reduces, and that is controlled by AGC. So AGC is related with the frequency. AVR is related with the voltage regulation. And what is the voltage regulation? Voltage regulation is E no load, like voltage regulation is magnitude of V no load minus magnitude of V full load upon magnitude of V full load, right? And what is magnitude of V no load? No load, if I assume there is no load, that means IA, armature current, is 0. That means your VT will be equals to EF, the excitation voltage. So your AVR, automatic voltage control regulator, will be controlling the excitation voltage. Okay. So AVR controls the excitation voltage to maintain the terminal voltage, right? So AGC response has a local effect on frequency, while AVR response has a global effect on voltage. Okay, this is wrong. AGC, right, will have a global effect on frequency because frequency is a global parameter that is controlled globally, right? Because frequency must be same of every generator, otherwise they will not operate in parallel. So frequency, AGC will have a global effect, it will not have a local effect. AVR response has a local effect on voltage. Why? Because AVR controls the excitation voltage, your AGC controls the frequency, so it will have a global effect. So this option is certainly correct. This was a MSQ. AGC regulates the field current of the synchronous generator. No, AGC regulates the steam power input, right? That is given here, mechanical power input to the generator. And AVR regulates the field current because we know your EF is what? EF is 4.44 root 2 pi F phi m into N, right? And phi m is nothing but dependent on the field current. So if I increase the field current, the induced EMF can increase, right? So your AVR regulates the field current. So option D is also correct. Okay, so option B and D will be correct. I do agree. How do you understand option B? Now you know, right? That's how. So you have to study this, and now you know that frequency is a global parameter and AGC has a global effect on frequency. AVR, it controls the locally the induced EMF, right? This frequency is a global parameter to maintain synchronism, right? Okay, so with this we are done with our power system, and I hope you have revised power system a lot. We have covered almost most of the topics. Few topics are left out, like in distribution few topics are left out, especially the underground cable part, then the reflection of lightning surges, right? Lightning surges, reflection coefficient, all those things we did not see any questions much, but those are also important. So make sure you go through this and revise by yourself. I hope you have enjoyed this video. If you have, make sure to hit the like button and let us know in the comments below how you felt regarding this video. I will meet you in another lecture. Until then, happy learning.